Welcome to my complete natural language processing masterclass. Hi, my name is Nidia and it would be my pleasure to be your instructor. I am a developer and NLP researcher based in the United Kingdom. My undergrad studies were in engineering and computer science. I have been a developer for over 4 years and my NLP research concentrates on security and social science applications. I am furthering this specialty as I am enrolled at King's College London to commence my postgraduate studies. My objective is for you to feel confident with NLP by the end of this course. You would be able to use Python for NLP, execute sentiment analysis on social media tweets, build a fake news detector chatbot, text classifiers for news headlines and product reviews, produce predictive recommendation systems like on Netflix, and create your very own speech recognition program to convert audio to text. Furthermore, you benefit by using Python in the Google Colab environment, which is a top choice for modern data scientists. The syllabus has a gentle start with linguistic theory concepts like tokenization. Then we get into supervised and unsupervised learning, topic modeling, text classification, deep learning with LSTM recurrent neural networks, and pre-trained word models with the machine learning platform TensorFlow. Then we switch things up with acoustic speech phonetics and speech recognition. This course was designed for any beginner, regardless of your background, to give you an opportunity to learn a computer science field without feeling lost. You can explore my free preview videos to see how much thought I have put into creating this for you, and then I invite you to join my NLP course. Welcome to my NLP course. Let's get started as I introduce you to the wonderful world of natural language processing. When it comes to communication, computers are generally not designed to understand when we communicate as humans do. Computers speak in code using long lines of ones and zeros, so that when it comes to humans, the way you and I would speak, it's much more complicated because when we speak, we use things like phraseology and sarcasm. Quite often, when a human is communicating with another, a human may have a hard time in determining if that was sarcasm or was it a joke. So far more for the computer. But what does this have to do with NLP? With NLP, think of it as how can a computer understand human language? It would appear that humans and computer can't truly connect, but as we know, they have already made that connection, and computers respond daily to our search terms, voice commands, and many more forms of interaction. And this is all thanks to NLP. So what exactly is NLP? Essentially, NLP involves giving computers the ability to process human language. So think of it as text data being converted into integers so that the computer can recognize the word. But not only that, more importantly, it is so that the computer can understand the context and the meaning to these words. You would often hear NLP, data science, machine learning, and AI used within the same realm. But are they the same? Or what exactly is that relation? With respect to data science, this is the study of data. It is multidisciplinary, and NLP is a sub-branch of data science. And NLP creates a bridge between human language and data science. I will explain this a bit more shortly. But for now, let's look at machine learning. Machine learning is part of data science. You would quite often find machine learning being used interchangeably with data science, but don't be mistaken. It is a part of data science. We already established that data science is multidisciplinary, machine learning being one of those many disciplines. Now, all machine learning algorithms work with numbers. So you can see now where NLP comes in. These algorithms depend on NLP to be able to work with text data, because if a machine learning algorithm wants to do an analysis on Amazon reviews, It can look at the review number, which would be a review from 1 to 5 stars, and it can do an analysis on that data. However, if you want to run an analysis on the Amazon text reviews, where I go and I write a review of how much I like this product, then the machine learning algorithm can't do anything with that. So NLP has to find a way to convert those text-based reviews into numeric form and then feed that into our machine learning algorithm. On the topic of artificial intelligence, NLP, again, it is a branch of AI giving machines the ability to read and derive meaning from human text language. Okay, brilliant. Now that we have sorted out these common misunderstandings, join me in the upcoming video as we discuss data science in the real world. In this lecture, we will be getting an idea of data science and NLP in the real world. First of all, let's take a look at the average salaries for either an NLP engineer, an NLP data scientist, or data scientist would range usually between £5,000 to $6,600 US per month. And of course, this depends on your level of capabilities, the employing company, and on another note, if you offer your services on contract, your hourly rate can actually be higher, depending on skill level, of course. Like I mentioned, data science is the study of data. But yeah, it can still seem rather abstract because it encompasses statistics, mathematics, information science, and computer science, and it could leave you wondering, how is it even used in the real world? And I assure you, you would be surprised to know how often you would come into contact with products and services that exist because of data science. And even though I showed you the average salaries, I'm sure you're still wondering, would I ever need data science skills? I mean, what company would actually employ me for these skills? But data science is all around us, and some common examples where we interact with data science would be in the entertainment industry, for instance, with Netflix, online retail, with our online shopping, and supply chain management with logistics and transport. And I'm going to expand a little bit into each one of these for you. Let's take a look at Netflix. Netflix is actually a tech company, and their main objective is to study their viewers' behavior. They like to be able to predict how much you would like a movie, and then based on your previously watched. Traditional TV stations just never had the luxury that Netflix has, this luxury of gigantic loads of data, and this data describes the behavior of their viewers. And it's very, very valuable. And I'm not simply referring to data only on a previously watched show. The study of their data is extensive, and we are talking about data on moments when you pause, rewind, fast forward, and when you resume actually watching that show, what day, time of the week, where you live, whether you watch Netflix on your tablet, television, mobile phone, and when you do pause your content, if and when you do resume that TV show. They even have data on what movies you search for and if you ever watch it, and when you do, at what point in time you actually do watch it. Even more data on how you browse and scroll through the search lists. So it's rather extensive, and the machine learning algorithms that learned your behavior over time has been quite successful because Netflix is now so ingrained in our television watching behavior. And these predictions was able to ensure customer retention. Customer retention in marketing means that when you start using Netflix with their subscription plan, it is very difficult to lose a customer, and not just lose a customer, they were able to change a habit that has been around for decades with watching television from regular TV stations. And now our behavior, because of data science, is geared toward a television platform based on tech and data science. Moving on to online retail, think of Amazon and their personalized recommendation system, which is based on machine learning and NLP. This valuable data has changed the way we shop and improved business analytics by studying consumer behavior using big data. Some of the elements of this big data includes tracking the user to understand your mindset. It can track so many things, starting from your needs, what you have searched for, what you will need in the future, your personal details like contact number, address, and your address is actually used to try to figure out the income level of the user so that they can offer things that you may most likely be able to afford. And then we come into predictive analysis when you are doing your online shopping. Predictive analysis helps out Amazon or your retail supplier to be able to look at your past buying patterns, but not just that, it helps them be able to keep track of their stock items, to predict when and how much they need to stock. And predictive analysis also works great for ensuring that packages arrive on time. It's part of what you call the anticipatory shipping model. Now, another thing with online shopping is that there's something called price optimization that big data and machine learning plays a heavy role in, that the price changes a few times a day, actually in some instances every 10 minutes. So the prices are set according to your activity on a certain website or competitors' pricing, product availability, item references, order history, expected profit margins on certain items. So as a result of these algorithms used by Amazon typically offers discounts on best-selling items. And would you believe that they tend to earn larger profits on less popular items? On the topic of shipping, let us speak about logistics and transport. Machine learning engineers predict optimal routes for shipment of goods. Now, this may seem not that important, but trust me, it's significant. This is crucially important for the supply chain management industry. They are usually plagued with rising costs, demanding clients, demanding that, we need our product now, and uncertain geographic conditions. So machine learning engineers help logistics and transport globally overall reduce costs, maintain efficiency, will improve efficiency in this very huge industry. And how they comprehend this language and also how they produce it. But you don't need to really bother yourself too much about this. Now, aside from Netflix and Amazon, NLP in the real world is used in countless industries, which is why data science and NLP open up so much employment options. So one of the most common applications of NLP in the real world that you use all the time is autocomplete. Autocomplete is when you go to Google or any search engine and you enter SANF and you get San Francisco weather, San Francisco Valley, San Francisco hotels. That autocomplete is based on NLP. Similarly, spell check and autocorrect, heavily based on NLP, and we use it all the time. I have absolutely no idea how my life would be without spell check. Also, we interact with our Gmail, all emails that you have a spam filter. And also, if you're familiar with Gmail, it's not only a spam filter, you have an email classifier where Google where Google classifies your primary, social, and promotion emails. So that is also another aspect of NLP, using classifiers on your emails. And a not so common thing you're going to think about when you think of NLP applications in the real world is the application of NLP in aircraft maintenance. Yeah, what am I talking about? Aircraft maintenance, these mechanics usually have to read loads and loads of long manuals, and NLP can help mechanics to synthesize the information from enormous aircraft manuals, and it can also find meaning in the description of problems reported either verbally or handwritten from pilots and other humans. I don't know about you, but when I first found out about this application in particular, I was like, whoa, I would have never guessed. I hope you're starting to see more interesting uses of NLP, and it's gauging your interest a bit more. Siri is actually based on two main technologies, that being speech recognition and NLP, so that when you speak into your mobile, Siri asks you, what do you like to know today? And you talk into your mobile and you ask Siri, what is the temperature today in London? And Siri tells you it's raining at a temperature of 10 degrees Celsius. Of course, it's not really a big surprise if it's raining in London, but so that's an example of speech recognition from audio acoustic to text, and then convert it to numeric form for Siri to understand. Then we have Amazon Alexa, that a lot of people are concerned about, that Alexa spies on you. And I mean, yeah, to an extent, Alexa does spy on you. And one really nice application for NLP that's really irreplaceable, and one of the most, is NLP's ability to improve the quality of life for individuals who are disadvantaged in society. And one of the most popular ones is Stephen Hawking's, as he was unable to communicate, so he needed his device to be able to speak for him. So his machine used text-to-speech capability, which was built on text-to-speech synthesizers. And then also we have speech-to-text also being popular with video games, electronics, and human-to-computer interaction research. Another example of improving life, which not as popular as Stephen Hawking's, there's an app called Livox app, which was a father who created it for his daughter who had cerebral palsy, and she was unable to communicate verbally. And then we also have another app called Signal, which converts sign language into text using computer vision and NLP, which is, I think it's remarkable. And then we get into my favorite application of NLP in the defense forces and international or national security and intelligence. And popular intelligence bodies are British intelligence, MI5, MI6. Then in America we have the CIA, and then there's the Israeli Mossad, as well as the American NSA, using NLP to go through vocals and text data to anticipate terrorism or pockets of radicalization and crime. Okay, great. So after talking so much about NLP, I hope I was able to motivate you even more to learn this wonderful field. So now it's time to follow me, and let's jump straight into our course. Welcome again to another lecture, and this section would allow you to conceptualize the general idea of NLP. So we get a good overview of not just the course flow, but how NLP starts you off from one stage where you have your raw text, and then to the point where it goes from one stage to the next, to the point where we can feed that data somehow to our machine learning model and have our desired output. So essentially, this entire NLP world, like Super Mario World, would start you off from stage 1, where we have our Amazon text reviews, for instance, and then you go through a series of worlds, which in our case would be a series of NLP methods, to prepare our text data to a form that our machine learning model at some point, to a point where it is able to use the Amazon text reviews and then eventually give us an output to let us know if a certain review was negative or positive. That's just the general gist of it. This diagram would make you understand it a bit better. This is a nice way to illustrate the entire NLP process that we would be going through step by step throughout the course, and then you would understand why I'm teaching the lectures in such an order. So first of all, you always have to do some sort of text wrangling or pre-processing, and then text normalization, and these two go together. And don't worry, by the way, I will be teaching each one of these in detail at great length. So this chapter is only a brief overview of everything, so you can conceptualize everything that we will be doing, and I just want you to be able to be familiar enough with the terms until we get into further detail. So like I said, the text normalization and text pre-processing, these usually go together, so we can lump them together and call it text pre-processing. Just know that the text normalization follows a certain amount of other text pre-processing as well too. Yeah, and then after we do that pre-processing, then that leaves us to word embedding. That actually is I think, one of my favorite things to teach, and I do hope you like it. It's really important for the entire basis of NLP. And then we go to build our model, initialize it, train it, test it, so we can test to see, okay, if we had a review that was positive, an Amazon review, we can test to see if our model figured out that it was actually positive, or if it told us that, oh no, it's negative, so it was incorrect. And then we evaluate the model. How accurate is it? Is it something I can propose that a company uses for their marketing? So essentially, that's our NLP world. This is a basic model of the general steps we will be taking throughout our NLP course. And not just our NLP course, but when you perform NLP tasks. I have actually provided the slides for you in the resources part of this lecture, so you can download these slides and you can keep them for future study, especially this diagram if you ever feel lost when we're doing NLP methods. And it's nice to just look at it and realize, oh, we're doing initializing or transfer learning, so this is where we are in the NLP pipeline. So yeah, so you can be sure to download those resources. So text pre-processing, which is the first part of our little diagram here. Now, when it comes to pre-processing, you'll generally hear a lot of times we're talking about cleaning our data, processing our data, pre-processing our data, sorry. So what we mean when we want to clean up our data is that most of the time in the real world, and this is not limited to only NLP, but for data science in general, data can be really messy. And in our case, data can be highly unstructured. Text data is particularly highly unstructured. So while learning NLP, you would notice that the datasets require pre-processing, but usually not to the extent to if you were to go creating your own datasets from scratch. Nevertheless, I will ensure that you get really good practice with cleaning some very, very dirty data, especially some of the data that I scraped myself from websites. So in some of my lessons, I'm sharing with you some of my own original datasets. To get a better idea of what I mean about cleaning or pre-processing your text, I want you to consider tweets. Let's imagine, in our case, we are doing data science analysis on tweets. We want to be able to determine if a tweet is negative or positive. And I'm using tweets in particular because tweets are kind of really messy. And if you look at this tweet here, it looks pretty good, pretty clean. Looking for a new show to binge, what's everyone watching? And that's fairly clean and simple. But let me show you how tweets look in a dataset that was created from scraping tweets with the hashtag Coachella. If you are familiar with Coachella, it's a huge concert that happens once a year for a few days. So I'm going to show you how tweets look when you perform web scraping and then you save that to your dataset. This is my Google Colab notebook. It's an example of what we will be working in quite often. So this is my Colab notebook named Text Preprocessing for Coachella Tweets. This is a sample of my dataset. It shows only the first 5 entries of that dataset. In this case, you notice our rows and columns. This is typically how a data set looks. And for our Coachella tweets, the main part we're concerned with is right here, because for this column text, these are our tweets listed out here, and it's a bit jumbled here because you're not seeing the whole thing. So I wrote a statement here in Python to show you the entire output, which would be the entire tweet here. These are for the first 3 tweets. And look at this tweet. It's RT at this person who wrote, wait, this is absolute fire, hashtag Coachella 2005, and there is a URL. Then for the second one, there's Coachella 2015, VIP passes secured, see you there bitches. Then in the third one, you're getting an idea of how messy this is when we actually import and scrape our data from the internet. Because if we were to train your algorithm on this, and this, it's not going to be possible to really make sense of this because there are too many interruptions, it's not flowing, this is not part of the sentence, it's a hashtag. So yeah, these were the hashtags that were scraped concerning Coachella for that period of time in 2015. So now that you have an idea of how messy this is, now you see why part of the pre-processing for the tweets included to extract the hashtags. So in this case, what that means is that, you see here we have hashtag Coachella 2015, hashtag VIP, and then hashtag Coachella again here, and then another one here. So what we're doing is that one of the first steps would be to extract these hashtags and then dump them in a brand new column. So the first thing we would do would be to extract these hashtags, and then the piece of text without the hashtags, you will take this piece only and then dump that into a brand new column. So that's the first part, and then clean the URLs. Then we go and you look, oh yeah, we identify what a URL is, and then clean that. So in this case, we would have taken out the hashtag and then the URL. So then this piece will be dumped out into a brand new column. Then we have our mentions, emojis, smileys, digits, punctuations, and stop words. Each one of these, like the digits, punctuation, emojis, like these, they would have to be removed. And then the third step now, when those emojis are removed, then the little bit of text alone that was remaining would go in another column. Okay, but what you can do, you can conduct all of those 4 things I just mentioned all in one, and then just create one column with it all. And then when you are left with just the words alone, for instance, in this case, we'll be left with only wait, this is absolute fire, right? Now, with the stop words are words in our sentence that don't add much meaning at all. So they are words like a, an, in, this, and this list can be very, very long. You can customize these lists as well too. Of course, I'm going to show you how to do all of this. So in this case where we have wait, this is absolute fire, when you remove your stop words, you may get wait, absolute, and fire only. So we'll remove this and is. So our pre-processed text for this tweet would end up, instead of all this jumble, we would have just ended up with wait, absolute fire. But you notice it gives the general gist of what it's trying to say. So now that you have a good example of pre-processing with this really nice example with tweets, let's head into text normalization. Now that brings us to text normalization. Text normalization deals with converting text into a single canonical form. In computer science, the context of canonical means that you want the text to be converted into some form of standard state. Standard state, or a type of uniform behavior of an attribute, so that we are putting the text into a structure that conforms to well-established patterns. So the text normalization tasks that we perform with NLP, some examples are tokenization, stemming, lemmatization, sentence segmentation, and spell correction. Tokenization is actually the most utilized form of text normalization. Each one of these will be explained at great length, both in theory and practical, I promise you, during this course. Okay, great. So let us jump immediately to the next lecture and take a look at word embedding. It's time for our word embeddings overview as we continue within this chapter from this diagram that we started up with, and we are right here at the point of word embeddings. So word embeddings, before I get into any formal definition or explanation, where I tell you that word embeddings deal with words being represented as a vector or something like that, I'm not going to start with that because you can get that definition or that explanation in so many different places on the internet, other courses, and textbooks. But I said before that word embeddings is one of my favorite parts of NLP, and for this reason I want to break it down for you in a way that you can really imagine it, because some elements of word embeddings truly is a bit magical. So to conceptualize word embeddings, I want you to do me a favor first. Let us look at this image. And I want you to think about space and dimensions from a flat piece of paper being 2D, and then to visualize something to 3D. And then when we have our 3D idea of space, and in this entire universe, we have all these stars. Each different glow here represents a star, and each star has its own position. So this star would have a certain distance to this star, and this star as well too is closer to this star than it is to this star. And I like this diagram because it gives you really nice sort of a 3D feel. Same thing for this image. Picture yourself in this world, in this universe. You can conceptualize all these stars all around you. Remember what I said with one star being closer to the other compared to how this star would be to this star, and imagine this feel of that 3D space. Okay, so now let's go back to our word embeddings, because word embeddings has a lot to do with a sort of word universe, a word space. And instead of our stars in this dimensional space, we have words instead of our stars. So the aim of word embeddings is to encode words into a vector that exists at some position in this word space. And when I say the aim is to encode these words, not just words, these normalized words, it's the normalized words that we spoke of before when it came to our tokenization and stemming lemmatization, that sort of stuff. So those normalized words we want to encode them with a form of numeric representation, but in a system that is like this word space. And similarly, like how I said that one star has a relationship to another star in terms of distance, so it's further from this star as it is to this star. That sense of relativity and distance is very similar to how we look at our word similarity situation. The word similarity part, for me, this is where the magic happens. And do you know that quote, magic is just science that we don't yet understand? That's actually why I consider it magic, because it truly is based on some magical stuff, but it's actually mathematically proven and it works out mathematically. During the course, I would actually show you some of the math principles, because it's highly based on principles such as cosine and the Euclidean distance, because that distance I spoke of with the stars from one to the other, we will be using a form of calculation with cosine and Euclidean distance to work out how relatively close one word is to another. This is the core understanding of word embeddings. And trust me, the math works out. And the first time that I understood this and actually saw the calculations, the calculus behind word embeddings, that was what made me realize, like, whoa, this is incredible. And everything here with word embeddings is based on calculus. So when I spoke of similarity, so think of these sentences. Man is to king as woman is to what? What if we had this blank? Okay, so I adjusted it for you so you can visualize it better. So man is to king as woman is to queen. We know this because of our wonderful sense of vocabulary and that knowledge that we accomplished over years. Now, the computer has to figure out what we want to say here, so it has to make a prediction. So it has to predict based on the sentence, man is to king, woman is to what? And just keep in mind that this is a quick overview of word embeddings. We get into this in greater detail later on. I just want to give you an idea of it now. So look at it here. Man is to king as woman is to queen. And you can see that from this diagram, the word man, by the way, picture these images, they're actually words, but I use the images to understand it better. So the distance between the man and the king, you can see that it's very similar to the distance between the woman and the queen compared to man and jellyfish. So in a case where you want to relate man and king to woman and something, you will equate that relationship to a distance that's similar to man and king. So you wouldn't think that woman is related to jellyfish. No, that's too far. That makes no sense. And we work this out with Euclidean distances and cosine, but don't worry, I'll show you that later on. So essentially, just understand that it has something to do with the distance. So man is to king as woman is to queen, and these distances are similar. And when you look at word associations, just similarities on the whole, king, is it most similar to jellyfish or prince? We know that he's most similar to prince and even queen. And to an extent, yeah, man. So he's closer to man than he is to jellyfish. So how do we know that man is closer to prince? That is from years and years of learning. But how are we going to get our computer, our machine, to know that when you think of king, a close relative of that would be prince? Our computer has no idea. It's totally independent. He has no idea that king has any relation to prince. To him, king, jellyfish, prince, all independent. And you notice that jellyfish is actually close to octopus and squid because they are related. They have some similarity. So why is it that we find these clusters? And that actually is how word embeddings work. You find clusters of words that are related being close to each other in this word space universe. So our job is to take our words, like for instance in our tweets, clean them up, and then have them encoded to a point where that numeric code is in a form like this, in a layer, where we can actually mathematically quantify the distances and similarity between words. And in NLP, you will become familiar with words such as word2vec and glove. These are examples of word embedding methods that we use in NLP all the time. So that's it for the overview of word embeddings, and join me in the next lecture for a quick overview on building the models. So far in looking at our NLP pipeline, we just completed the word embedding bit, and now we move on to building our model. So when you think of building the model, machine learning involves models, yes. And within these models, like each model, let's take for instance in deep learning, we have the LSTM model. The LSTM itself has its own machine learning pipeline. Essentially, the machine learning pipeline operates with a series of mathematical executions to learn from data in order to estimate the output on unseen data. And an example of this is that if I have a data set with 1,000 Amazon reviews, some of them labeled positive, some labeled negative. At the end of the pipeline, after we go through pipeline part 1, part 2, part 3, part 4, at the end of it, it should be able to predict if an unseen review, meaning one that does not belong to that 1,000 labeled data, another one outside of that 1,000, if the model can look at it for the first time, what we call unseen, and predict if it's negative or positive. So it should be able to look at something and say, I hate this product, don't ever buy it, I do not recommend it. And if it never saw that particular review before, the model at the end of the pipeline would be able to predict, yeah, it's negative. Now, depending on the type of data and the model itself, and if it suits the type of data, then the accuracy would vary. So data exploration, understanding the problem, that's very important. So when it comes to being a data scientist or NLP engineer, when you are in the working world or even the research world, and you are dealing with a real world situation, you have to think about the data that you are using, and not just that, you have to think about what do you need from this study, or what does your client need from this? And then from that, you will be able to realize if this model is giving you favorable results. Should we maybe find or get better data? Should we try a different type of model because maybe it's not suitable for that particular client? Because you can't just do a cookie cutter method and be like, okay, yeah, using BERT is highly recommended for certain things with classification. We'll go ahead and just use that. Because if your data set is too small, for instance, then certain deep learning methods will not work. And then maybe you need to look at support vector machine method to deal with that smaller data set. So when it comes to building your model, you have to think about it a lot. And with time and practice and experience, then you'll be better equipped to work in the working world and then relate the technical aspect to the reality when it comes to implementing that and working with corporate businesses. So off we go. Let us continue, and we look at transfer learning. In our diagram, I have that labeled as initialize the model, and that can entail what we call transfer learning. Think of the simple concept, transferring learning. Now, if my dataset consists of Netflix movie titles, and the movie titles make up my vocabulary, as in my vocabulary is my universe of words in this instance, right? But what if the dataset is not sufficient? It's fairly small, so it's not enough to train my model. In other words, if you are preparing for a test and you don't have all the books, all the learning materials for that test, you wouldn't have enough knowledge to train your brain to be able to perform well in the test. So during the test, you may have to copy from your friends' answers during the test. So that form of transfer and borrowing your friend's knowledge, even though it's unethical, it's my example that I'm using right now for you. So think about transfer learning. It allows your model to use already learned knowledge from a gigantic data set. And this knowledge is transferred from a related task to this new data set. So basically, in this instance, your friend in the exam that you are copying from is significantly smarter or had a lot more knowledge and had all the books to learn from. So that's why it makes sense to copy from that friend. And then your results will be much better. So this is just a brief introduction to what transfer learning is. We also refer to transfer learning as our pre-trained models. After using it in the practicals, you would have a fair understanding of it. So continuing along, we're almost finished training the model. You'll be using this term over and over and over throughout your lifetime in data science and NLP. So what exactly does training the model entail? Simply put, training the model means you are teaching your computer. That's the nicest way I like to think about it. So this is your computer, the brain, and he's working out, getting stronger, getting better. So he's learning on his data, using his data. So if we were to think about the beginning of this chapter, the section, when we spoke about cleaning the text and normalizing the text, think about that cleaned, normalized, pre-processed data that was then converted into a machine-readable integer, like a structured uniform form that we spoke about. So it's after the normalization, after the word embedding, and then we take this data and we are using, think of that data that when it's cleaned as knowledge, and that knowledge is what we're taking to iterate with the brain, or think of it as the computer, the way we would study words repeatedly to learn it. So the same way a human would study certain words over and over repeatedly, then the computer would learn it iteratively, and that is essentially training the model. Keep in mind, it's teaching the computer or teaching the machine. That leads us now to testing and evaluating. This is very important, because how else would you know if you can recommend your model to a client, or is it good enough for my research? So you predict the output. For instance, you predicted the review was negative or positive, but you need to compare it to some sort of data set with the label data so you actually know that it got it correct when the machine assumed that review is negative. So when you take that predicted answer that the review was negative, then during the testing, you would realize if it matched that unseen labeled data. And then after knowing how much of your test data was actually evaluated correctly, like if it got 90% correct, then we realize in evaluation, yeah, it's an acceptable model. But if you got 50% correct, then you realize it was basically just guessing, so your model was very unreliable. And the interpretation of the performance of your model is very important when it comes to giving presentations to clients, the business and corporate world, or even in research, because the performance and the evaluation is where you actually get to see if it's usable and implementable in the real world. And essentially, that's the point of everything we are doing in NLP and data science, is to find ways to be able to implement it with the real world for some sort of improvement. Thank you for going over this NLP overview with me, and join me in the next section. Welcome to a crash course for Python with focus on data science and NLP. If you have no programming language whatsoever, rest assured, because this will be sufficient to take you throughout this course, as it is rated B for beginners. Let's take a look at the top programming language to learn in 2020. That would be Python, Java, JavaScript, C++, PHP, and Perl. Let's take a look at the demand for these languages. The time period would be between 2017 to 2020, and Java maintained quite a high demand of 68,000, and it dropped a bit in 2018, but then steadily went all the way back up, slightly more than 2017, and was about 69,000 in 2020. Or keep in mind that this image was taken from Indeed.com, and it shows the worldwide jobs in numbers. And let's compare Java to Python. And Python, from 41,000 in 2017, nearly doubled to 73,000 in 2020, steadily increasing each year. Even though each one of these are, in a way, significantly lower, especially C++ and PHP, compared to Java and Python, I assure you that they do have their needs in their respective career paths. So it all comes down to what exactly you want to learn a language for. So let's take a brief look. So let's have an overview of each of these languages before we get straight into Python. So first of all, Java. Java is server-side, and one of the main uses for it is in software development. Now, in the real world, some of the most common fields that you would find a Java programmer needed would be for software development, for particularly Android apps. So it's largely used in web and app development, in particular Android, and in the gaming industry as well. But Java is quite commonly used in the finance and banking sector. There's actually some really popular Wall Street trading software. These are server apps that they use in finance that are based on Java. And the average salary per month is approximately $6,100 US in the United States. Now let's take a look at JavaScript. Please don't mix these up. They are two very different languages. So JavaScript is different to Java, and it's client-side. And an example of client-side, so you get a gist of what JavaScript is that it's heavily used in web development. Now, most web browsers that you use are actually compatible with JavaScript. It works with HTML and CSS, and JavaScript works with HTML and CSS when it's time to make creative and interactive websites and apps. And if you're unfamiliar with HTML and CSS, that is where we get into a bit of web and app development. So you can Google HTML and CSS and get a bit familiar with it. It's not related to this course, so you can fulfill your curiosities with that. Some of the typical job fields you would find a JavaScript developer in would be a front-end web development. When I say front-end web development, then you get an idea of what client-side is. Don't get confused if you're not sure what client-side and server-side is, but just keep in mind that your client can be a laptop. Think of it as a laptop. And the server is in the back end, in the server that you as a human, you don't come in contact with, but your device is the one that communicates with the server. So in this case, JavaScript is for front-end development, which is very different to Java, which is for the server-side development. And since it is used with HTML and CSS, usually a lot of web developers know these three, and it's commonly used in the job fields for software development and information security, WordPress developers. So you would be familiar with web development. There's an array of web templates you can use on prefabricated websites built on a WordPress platform. So WordPress platforms are built largely on JavaScript. And if you were to get a job as a coder on Shopify, or with Shopify, you would be expected to be a JavaScript software developer. The average salary per month in the United States with 1 to 4 years experience is about $7,000 per month. So basically with JavaScript, anything with the .NET platform development, you will need to be versed in JavaScript. Now let's take a look at C++. With C++, this is object-oriented programming, and it is very common in the gaming world. And when it comes to GUIs, which is a graphic user interface system, think of Adobe plugins, and like something like Photoshop. Photoshop it's fully written in C++. So job fields that would need C++ is not just only in the gaming industry. So one, yes, would be a gaming C++ developer, but also in electric engineering, because C++ is commonly used for the software development of a lot of electronic devices. And if you are a hobbyist in Arduino or even interested in Raspberry Pi, they both use C++ and also Python. So you can use either Python or C++ with them. And so that's another positive with Python. It's not only C++ used for these. And something fun that you can even use C++ for when it comes to learning gaming is that you can build your own Super Mario game on C++. And C++ is a very good foundation language to learn as a first language. C++ was one of the first languages that I had to learn as a teenager. And because of that, it actually made the stepping stone to Python quite easy. So for those of you who do have some programming experience before, learning Python as a stepping stone from C++ gives you an advantage. And even if you haven't, Python is very good to learn as a first language as well. So if you're a complete beginner, don't worry about it. And with C++, the average salary in the United States per month is approximately $6,500 US. Now when it comes to PHP, this is called the language of servers. And in the real world, PHP is used, again, similar to Java, as a server-side language, so that server-side websites and web applications, if you have a database for your company where you work, and that database has all your employee information, the staff information, and the inventory for your entire e-commerce website. Now all this information is stored on a database, and if you want to access it or update these records or delete these records via a website, a web interface, your web interface can use PHP to access the company records on the database. In addition, JavaScript can also be used in place of PHP. So you can do the same thing that I just described, using JavaScript. So basically, PHP is used to connect applications with a web service. It's commonly used, most popular, to retrieve web data stored on a database, whether that is a MySQL, Postgres, Oracle. Some of the job fields that this covers, and definitely not limited to, would be a PHP developer. An example of that would be in web development, or to write server-side logic. The average salary per month is about $6,600 US. And last but not least, we come to Python. Now, Python is a general purpose type of language. It is object-oriented. I want to pay attention particularly to the general purpose. Now, unlike JavaScript, Python can be used for software development besides web development. So whether that be back-end development, data science, machine learning, it's quite popular in startups. And fintech, don't confuse fintech with the finance industry, because Java is more popular in the finance trade. But fintech, you would find Python being needed. And even if you jump into scientific research, you'll quite often need Python for certain things in astronomy and neuroscience research. Of course, it's not limited to these. These are just some examples I'm giving you. And apart from just what you may think of as a software developer, in the real world, it's quite an array of job opportunities out there with the use of Python. So job fields with Python goes from, yes, being a Python developer. It can even help you as a product manager, and also quality assurance engineers, where you need to develop automation scripts. An obvious one is as a data analyst, where you can apply your knowledge of Python in quite an array of fields. For instance, marketing, a financial advisor, and even as a data journalist, GIS analyst, where you use it for geographic data or land use planning. And a junior Python developer, a popular job for this would be similar to a PHP developer, where you use your knowledge to connect web apps to databases and third-party devices, or where as a junior Python developer you work at the back end of websites. Keep in mind that this is for a Python junior developer with all the web app development and stuff, and don't forget all the other job fields I just mentioned. And it's not limited to these only. These are only a few I'm naming for you here, but you can see the general purpose of it. It's quite different to the other languages that I described earlier, and it's only a little bit of examples. So we will get into why Python is needed for data science in a bit. And before we do that, the average salary per month in the United States, in US dollars, for the entry level, which is about 1 year experience, can be around average $6,500 per month. An average junior developer is about 7,000 US per month. And then we get to the mid-level after a few years experience, some good quality experience, it can be around 9,000 US. And then when you get to be a senior developer in whether it's one of these fields or whatever, and you're senior qualified with a good bit of quality years behind you, keep in mind, I mean quality years, you can bump up to about 10,000 US dollars per month. So these are not the only reasons that Python was chosen for your NLP course. We will see the even greater reasons for this in the upcoming lectures. In this lecture, we will be discussing Python versus R, which is another programming language. And also I will be outlining why Python will be recommended in our case for NLP and data science. Now, R is a statistical language, whereas, like I mentioned before, Python is a general purpose language. It is highly industry preferred, and R is recommended usually for academia purposes, largely in research. And when it comes to data modeling, which is largely what we need in data science, Python comes with many perfect libraries, ideal for data science, so there's no need for external libraries. I will explain to you what libraries are in the upcoming lectures, so don't worry about that. And data modeling libraries in R, there are, especially in recent times, some better libraries available, but still you would have to resort to some external libraries. So in this case, for data science and NLP, it's not as versatile. With regard to data visualizations, they're both great. R is very, very good actually. But when it comes to visualizations, given the other strengths of Python, just visualizations alone does not make R a better choice for machine learning and data science or NLP, because Python itself has some very powerful libraries that allow you to do some very nice visualizations. With regard to data collection, Python is great and it wins hands down with this because it can do data collection for all formats, but more importantly, also for web-sourced data, for instance, in JSON and SQL. Quickly, what this is, an overview. For instance, if I have a website and on that website, I get a lot of data entered because it's a survey collecting website, and I have all these answers and questions, and my website stores that on a database, and it can be in the form of JSON or SQL. These can be stored on an online database and pulled with Python and used in this format. And that's something that R can do, and it's very important in in data science to be able to do this. And there are many data sets available for training your models. This is one of the irreplaceable things about Python, which is why it's highly recommended for data science. And when it comes to the data collection for R, one of the good things is that, yes, SPSS format can be used, which comes in very handy if you work with statistics. With R, it is based on statistical learning, whereas with Python, you are conducting machine learning, which is a subfield of AI. And this is very useful with software engineering. Hands down, it's Python you're going for, not R when it comes to software engineering. In terms of jobs, because Python is very good with production use, as in it's really good for when you want to integrate whatever algorithm you created with web apps. This is something that R just can't do. And because of this, it's more scalable and better to implement in the real world. So this is why it's more industry preferred and R is more academia preferred. And if you do have a statistics background, a good strong statistics background, R would be very good for you because it would be quite much easier for you to learn. But generally, the data science world and the NLP, machine learning, everything with regard to data science and AI, it's highly recommended to do Python, learn Python, together with a lot of other fields, like I mentioned before, with data journalism, GIS, electrical engineering, and whatnot. So now you have some more justification of why Python is recommended for data science and NLP. So join me in the upcoming lectures to get a better understanding on Python, and then we actually get started with our practicals as we get to use Python. To access Google Colab, I assume you have a Gmail account for your email. If not, go to gmail.com and create a Gmail email, assuming that you have a Gmail account. So you can you can search for Google Drive, and here you'll sign into Google Drive, and you can add it to your bookmark so you can access it easier in future. Now that you are in your Google Drive, go to create a new folder and call that Colab Notebooks, and create. Navigate inside that folder, new, and I'd like you to create some folders so that later on organizing your files would be easier. So click on new, a new folder, create a file called NLP _code along. You can click create. So open this new folder that you just created, NLP _code along, and go to new, click more. You'll see right here Google Colaboratory. So open there and you'll create your new notebook. Welcome to this lecture on how to open an IPYNB file in Google Colab environment. All of our practicals will be done within the Google Colab environment and will look very similar to this. So in order to open these up, I will show you step by step how to do so. Every time that you need to do a practical project, I would provide the necessary resources. So for that particular lecture, for instance, in this case, it's a lecture on tokenization. It's one of the first practicals you would be doing. Kindly go over to the right-hand side here. For the corresponding lecture, it's always highlighted in blue. So when you go to here, you'll see a folder on resources, and you kindly just click on resources. And for each one of these, click on them and download them. So once that's downloaded to your local computer, go over to your Google Drive, go to the Colab Notebooks folder that we just created in the lecture before this, and go to NLP Code Along. And you can just drop that file that you just downloaded into this folder by simply taking that file and dragging it here. Or if you don't want to do that, you can also go to New, File Upload, and go directly to wherever the file is and upload it. I generally prefer to just drag it across. It is very easy if you are using Mac. I'm not sure with Windows, maybe you might prefer to do it this method. So just move it across there. And now to open the resource, your IPYNB file, all you have to do, click on this, double click, and it will prompt you to ask what do you want to open it with, and we want to open it with Google Collaboratory. So just select Google. So select Google Colab, and then you can go ahead to do your Python in your notebook. Now when you use Colab and you follow my tutorials, you will realize that my background is dark, and usually you will always default to this white background. So if you just want to change it to look like mine, you can go to Tools, Settings, and change your theme from light to dark. And you can do adaptive and then it change automatically light or dark depending on the time of the day. So just choose your preference and save it. And as we're going through the Colab options here, if you go to Runtime and you go to Change Runtime Type, you notice here it's Hardware Accelerators None. And this is fine for most of the easy work we will be doing, but later on when we start to actually train models and use larger data sets, or if you yourself start practicing using more intense machine learning algorithms and you want some more power and you don't want to just use, because your computer uses your local system, your local machine. And when you're using your computer, if you're an absolute beginner, the resources in your computer, it's limited. And what's going to happen is that when you use something that's machine learning intensive and you're using a large data set, for instance, over 50,000 comments or over 50,000 news headlines, you will start using up your local resources, and then your computer will slow down, and then you can actually max out, and then your machine can actually stop training the model and it can actually just crash and time out. So if you want more resources, so that's the really nice thing about Colab, because you have the option of not using your local machine to rely on your RAM and your resources. So you can click on Hardware Accelerator, go to GPU, and you can leave the runtime shape as standard. You don't necessarily need to go into needing high RAM for anything we'll be doing. Later on, when we start using more intensive chatbots, then yeah, when we start using maybe bits, for instance, then or those transformer types later on, then I will remind you later on to go back here and change it to GPU. And you can click Save. Yeah, so I forgot to tell you that this GPU that Google Colab provides, it's free. It's not ideal, so when you are doing a lot of the intensive stuff later on, it can help, but there are two accounts. Let me just show you this here, right? So the memory allocation for the free account, which is the regular Google Colab that you would have right now, you get up to that 12 gigabytes of memory. From personal experience, it's generally okay if you're doing straightforward, smaller projects, but it's not, you need the pro account, which is about $9.99 US a month, but you don't need to get this at all for the course. The free one is perfectly fine for the course. But if you want to expand later on and you want a good recommendation, you can sign up for the Pro Collab and you get double amount, 25 gigabytes of memory available to you. And it actually makes a big difference when it comes to training large models. It performs really well. And at the same time, you don't have to compromise any of the resources on your local machine. Before starting this lecture, be sure to download the resource for this lecture, the IPYNB file called Storing Data Values, and at the end of the chapter you will find one called Complete Storing Data Values, and this one will have the finished workbook in it, and the one that you would have downloaded for this class is empty because it's a code along practical. So be sure to download it, store it to your drive, and open it up like I showed you in the previous tutorial. Welcome to this lecture on storing data values and some common words you would find while using Python, and you should become familiar with the concepts of them are variables, lists, and data frames. Before we get into the actual coding examples, let's just get into what exactly is a variable, what is a list, and what is a data frame. So let's have three containers. Container 1, 2, and 3. So these are our three containers. Well, our three buckets. So essentially, conceptualize each one as a variable. Okay, and a variable, like I just said, is a container that's used for storing data. So if each container has a piece of paper and so we have 3 pieces of paper in each bucket, okay, and each paper has a word written on it. So each bucket, which is each variable, has a piece of paper that stores some bit of information. So that is a bucket storing our data. So the bucket or the container is our variable, and our variable is storing some information. So each one has a word written on it. And I'm not going to write the word, but let's say this one is written milk. They're all drinks. So this is milk, this is wine, and this is written water. So essentially, each variable is storing information. So when in Python, you'll see me saying that this is our variable and this is the data in that variable. Think about your container with our information in it. And when we're typing out our code in Python, the code are instructions, and we are instructing Python to do something with our information. So this can be what we always do with Python. You will see we naming our variables. So we might name our variable something x. This can be our variable y, and this can be z. I'm sorry, this is x. Okay, so that sometimes you'll see me say x is equal to milk, and what that would mean that would mean that my container named x, or my variable named x, has the data contains the data milk. That's the information that x has. And then another time you might see me say my variable y is equal to wine, and that would mean that my variable, or that container, stores the information that is wine. So that's my information in here. And these containers, or these variables in Python, you will see that we can name it anything we want. It can be x, you can name it after yourself, you can call it John, you can call it container. Generally, you name it something that relates to the contents. Just it's easier to organize your code that way. So if we want to store more than one bit of data in a variable. So you notice this piece of paper just has 1 in it. This piece of paper has 1 item, this piece of paper has 1 item. But if I were to go to the grocery, and when I go to the grocery, do you want to go to the grocery with 3 completely different pieces of paper? No, you want to go to the grocery with, like, you want to have a piece of paper, and a typical grocery list, you'll have 1, 2, 3, your 3 items on it. Okay, so this one list here is essentially a list. Okay, so we can see that this list here is being used to store that collection of data from our 3 variables. And that's what a list is, because a list is actually a Python collection. That's what it's called. It's a Python collection, and it stores a collection of data. So it has these 3 elements from these 3 different variables. So essentially what we can do is that we can have one bucket, one variable that stores this one piece of paper with the 3 pieces of data in it. So it's one bucket. It can be, this could have been bucket X or bucket Y, or it can be a whole new bucket. So this could, let's say we call this bucket A. Okay, so this is our variable A, and it stores this collection of data. So that is what a variable is, and that is what a list is. So just keep in mind that what we did was that we created a variable, and that variable is storing a list, which is a collection of data. So join me in the next lecture where we actually go to our notebook and we actually use Python to create variables, and you actually see how to code variables and lists. Last lecture, I explained to you that a variable is essentially a container that stores data, so it stores your value. Just remind you that we used 3 containers, 1, 2, and 3. Okay, and let's label each one of these. I'll call this container, container X, container Y, and container Z. Now each one has our data where it's stored, each our piece of paper, right? And this is our data with each word. So it has our word milk, it has wine, and water. Okay, so these are our 3 variables. What we want to do is write out using Python notation what these represent. So let us just do that. So looking at these, we want our 3 variables, which would be X, Y, and Z. So what do we want X to be equal to? Well, X is equal to milk because it's storing that value. And Y will be equal to wine. And Z will be equal to water. So it's the same thing like what we have here, X, Y, and Z. And these are 3 variables. So there are 3 containers that's storing these values. So we run that cell with command return, but you would not see anything happen. So you want to see what you just did. So what we can do is print out our variables. So we can do that with a simple print, and print X, Y, and Z. So we can just copy this and paste it twice. So we print X, Y, and Z. Beautiful. So that's exactly what each variable contains. Milk, wine, and water. So this is our information. And if you want to get the data type, as in this would be a string value because it's not an integer, it's not a digit. But if you want to be able to get the data type, you can actually code that in and be able to get whatever type of data it is. So to do that, it's a similar syntax from here where we have the print x, y, and z. So you can copy all three, paste that in, but the difference is that we're using the function called type. So it's a type function. So I can put that here for you. So it's the function type, and that function type will just be put into the brackets here. So you will do type, and x will be what is in the function. Let me explain that a bit better for you. So if you're using the type function, that's the notation for it. So it's type and brackets, and something goes in the brackets. So the something that goes in the brackets, it's one of our variables. So in the type function, you're passing the variable, which is x, y, or z in our case. So we're passing the variable x in our function type. And then if you want to display those values, you print, let me just make that simpler. When you want to print something, you print and you put that in your brackets. So we want to put whatever value in the brackets that we want to print. So we want to print the type y, right? So you take this and put this in the print function. And then we repeat it for z. So copy and paste that there and just substitute y for z. Then run this cell, and you will see that it tells us that each variable x, y, and z contains strings, in all of them. So that's a data type, milk, wine, and water. It's text-based, so it's string-based. Let me show you another example now. If we were to copy this and paste it, I'm going to show you that variables can store different types of data. It can be letters or numbers, and numbers we call them integers. So now I want to show you that if I put the number 10, that's supposed to be an integer, but it's in the quotations, would it be considered is that correct Python annotation or not? So let's rename them to A, B, and C. A, B, and C. And then run that, create a new cell, and then we want to print out what these new variables are. So you want to print, substitute the x, y, and z to A, B, and C. Right, so why does it tell us that the variable A, B, and C contain string values, even though 10 is an integer and it's not a string? It's because the notation that we use when you're assigning a value to a variable, you notice these are in double quotes. But this one, if you need it to be an integer, numbers are not contained within quotes. You just assign the data to the variable plain as it is when it's a number. So if you run this cell again, run this one again, you notice the change here where it's now an integer. So variable A contains an integer and the other two contains strings. It's simple concepts, and later on when you get more into data science and we get a little more into NLP work, you will understand sometimes why it's really important to know the differences in data types, because you can get errors when you're dealing with large bits of data, and a lot of the times the errors are because of a problem with the data type in your data set. And it will prevent the work from seeming abstract when we get later on into it. Now, like I said here, when should we use single or double quotes? Doesn't matter. So in a case where we have B is equal to wine, actually let's have something new. Let's call it drink. We can call your variables anything. Drink is equal to milk, and then we have food is equal to, in single quotes, you can have rice. And let's see if it works. Does the cell run correctly or not. So let's print them out one time. So let's print drink and also print food. It's correct, milk and rice. So that means that when you are assigning a variable that is a string, you can use either single or double quotes. The only difference is when it's an integer, you use no quotes, because if you do use a quote, it will assign it as a string, and this will become a problem later on if you need to create a visualization or run a type of analysis on the data that's expecting an integer. So with time and experience, a lot of these different instances will pop up, and then it will become more natural to you. And also keep in mind that variables are case sensitive. So let us just look at drink is equal to, let's call it, actually let's call this one snack is equal to cookie. And let's do it twice. So it's snack is equal to cookie, and we have a capital S now. Snack is equal to, let's put juice, and we'll print each one of these. Print snack, which is with the common S, and print snack with the capital S. Now, if variables were not case sensitive, you would have overwriting of one variable on the other. But because it's case sensitive, you do not have overwriting occurring, so that they are two separate variables storing two different pieces of data. So you see, it's not overwritten. We have the two variables, so it's snack, common snack capital, with two pieces of data. So that's it for our intro to variables. Join me in the next lecture where we practice a bit with lists. Hi, and welcome to our lecture on lists. Now, if you want to change the color of your Colab notebook, sometimes you'll notice I use it dark and sometimes I use it white. So you can go to Tools, Settings, and you can change the theme to light or dark, whatever your preference is. So we're going to go with light for now. Remember in the two previous lectures, I described to you making a grocery list and storing it as a variable. So what we did last time was that for this lecture, we will be creating a variable that contains a list. So what we're doing is that we're creating this variable, which is our container. This variable, let's call it, and we will name this bucket, so this variable V contains our list with not just one piece of data, but 3 values. So there's 3 values, and it can be any amount of values. It doesn't have to be 3. Okay, let's do our list with 4 values in it. So this is our list, and it's in our variable called V. So let us write out the syntax for this in Python. So our list is named V, and it's equal to, in the notation that you have to use for this, the syntax, is that a list is contained, the values are stored in square brackets. That's very important that a list uses square brackets, because that's how Python denotes that it's a list. It understands that it's a list, because if I give you a piece of paper with words written on it, you as a human, you recognize what a list looks like, because this has nothing on it. And if I just give you an icon with this, a human brain, you can look at this and know, yes, it's a list. So for Python to understand, for the compiler to understand that, oh yeah, I'm seeing a list, we put it in square brackets. And then for each variable, remember before we had, for instance, milk or rice, and each one was a variable, so each one is a bucket. It's simpler if we use maybe x, y, and z for you to understand. So if we had our three variables x, y, and z, each one has separate data, but we want to put all these into one bucket. So we want to take all these three variables and put it into one called v. So we're taking milk, wine, and water. So we're going to put those three into this one list. So we will put in our quotes, but it can be double or single quotes. We put milk. You separate each value in a list by a comma. So we do milk, we could put anything, we can change it up. We can put milk, tea, and coffee. And actually, we don't need to name this v. I can call it something else. So instead of naming this v, let's be a little friendly with it. So let's call it grocery list. So grocery list is equal to these three values. And if you want to actually see what's in our variable now, we simply call the print function and we print grocery list. Perfect. So this is displaying to you what's in our list: milk, tea, and coffee. So this here is showing you this here. Basically, well, if it's easier for you to understand, I can just rename this V, since that's the name I put here in your drawing. I just didn't like it because it seems so robotic and not humanish. So this is our variable called V, our container, and it contains milk, tea. Oh, sorry, I put 4 items in my drawing for you. So I'll add one more thing. So it's tea, coffee, and water. So we have our 4 values in our list. Now, a list can contain duplicates. So let us just copy this and you paste it here. So we have milk, tea, coffee, and you can actually put milk again and you'll see that it prints it out perfectly fine. It's not that it would only print milk, tea, and coffee alone and this value would be here. No, it's actually different. So the reason that this milk is different to this milk is actually pretty important when you're thinking about lists, because lists are indexed, meaning that each item in the list has its own index, as in this would be 0, 1, 2, and 3. It always starts with 0. That reminds me, like I do like to do training, and a lot of the like army style training, you don't start with counting your reps, your exercise reps from 1, you start with 0. So you, instead of doing maybe 10 reps, you actually really end up doing 11 because you start from 0, 1, 2, 3. So that's a nice way for me to remember that your indexes, you must always start with 0. So that's how you can afford to have duplicates, because each one is assigned a different index. So this is index 1, 0, 1, 2, 3. What that means is that, let me just show you. So if I have each index here, 1, 2, 3, 4, they're actually indexed. So the first one is actually 0. So think about it when you have that list. I'm just going to draw it like this for you. So we have our items 1, 2, 3, 4. So this is the data. So this was milk, tea, coffee, and milk. So this column with your indexes would store 0, 1, 2, and 3. So index 3 refers to this milk, not this milk, so it's different. So keep in mind that list items are indexed. If you want to get the length of a list, you use the length function, which is len brackets. So to get the length of a list, you do len in brackets. So if this is our function, you want to pass your variable in that function. So what we're doing is that we're passing the v variable in the length function in order to determine the length of this variable, which is the length of our list. So if we want to print get the length, of v, put length v, but nothing, you wouldn't see anything because you're not printing it. So let us just print this entire thing, and we'll see what value we get. So we got 4. Excellent, because we have 1, 2, 3, 4 values in our list. So that's a bit of a nutshell for variables and lists. And join me in the next lecture where we understand a bit about data frames. We continue with our if-else statement lesson. The difference today, we will be doing multiple conditions. An example of this is that previously we did if our wallet contained more than or equal to $50, what is going to happen. And then we had another condition in our else statement. Instead of saying if my wallet had $40, but if I wanted to say that if my wallet had between $30 to $40, what is going to happen? So what I need to say is that if it has to be between 30 and 40, we need it to have less than or equal to $40, or wallet must be greater than or equal to $20. Okay, but the syntax for this, keep in mind that we need to put each condition in brackets as well as this one here, but this entire statement is the condition that we need to satisfy for elif. So this entire thing has to also go in another pair of brackets. So the wallet contents in this case is 25, so it does satisfy this condition. So let's see if it works. Right, so the output was my wallet has $40. I would go to the grocery store. Actually, let's change this. My wallet has enough money. I would go to the grocery store. So run that again. My wallet has enough money. I would go to the grocery store because it has between $20 and $40. What exactly is this elif statement saying? It is the condition that we have to satisfy for elif is the wallet has to have less than or equal to 40, or the wallet has to have less than or equal to 20. In this case, we did satisfy the condition, but it just happened to be that it satisfies both because it is less than 40 and it's also more than 20. But the truth is that the contents of our wallet only satisfies really one. I want to show you that what happens if we only satisfy one of these. So in this case, okay, it's less than 40, or it's less than 20, so that's 25, but how about we put $15? So it satisfies this one because it's less than 40, but it does not satisfy this one because it's not more than 20. So let's see what happens. Right, so we get the same output. It says my wallet has enough money. I would go to the grocery store. Now, is this correct? Is that what we want? Because what you want is that if you have between $20 to $40, you want to be able to go to the grocery store. But in this case, it's telling us that if we have $15, we can go to the grocery store, but that's not correct. And why is that not correct? It's because with the OR operator, we are only needing to satisfy one of the conditions in the elif statement, but we need to satisfy both if you want to be able to have between $20 to $40 be your range for your condition to be satisfied. So instead of the OR operator, we change that to AND. And if being AND, we go to run this again, Now it says I am going home. So we went through the if statement. It's the wallet contents is not more than or equal to ticket. Then it carries us to the elif. It is not between 20 and 40. Else, I am going home. That's how it works. You can practice with your own conditions and do different values for wallet and ticket, or for simplicity's sake, you can actually, instead of wallet and ticket, you can use something else. You can even use A is equal to 15, B is equal to 50, instead of wallet and ticket to make it easier. And then remember, every time you change the variable names here, A and B, you need to change wallet to A, ticket to B, and so forth. Ticket to B, wallet to A down here, wallet to A as well. I think that's everything you need to change, right? Practice changing up your conditions and maybe print out something else, and just play with the if statements a bit till you practice and get a better hang of it. Welcome to Python terminology. We will be categorizing common terminologies that we would usually use throughout our Python practicals into Python scripts, modules, packages, and libraries. Now, a script is generally just any Python file that you would like to run. So if I have a Python file that I would like to add 2 numbers and I write that code, and I save that will be saved as my Python script. So it's generally just a Python file so that when you run it, you want it to be able to do something. So that is what a Python script is. I will create a Python script for you, and you can actually code along with me, because the definitions just doesn't make you fully understand everything. So let's go to our Python Google Colab notebook, open a new one, and you can call it script. You can download this script IPYNB notebook attached to this lecture. So remember I said that you want your script to just be able to do something. In this example, you want the script to be able to raise a number to a power. So if we have 2 numbers, 2 and 8, I want to raise 2 to the power of 8, or vice versa, 8 to the power of 2, otherwise meaning 8 by 8 or 8 squared. So it's a basic script we'll write here. So let's import math, and you will always see your Python script starting with some sort of import something. It's always going to be a few imports, and these are importing our libraries. So we'll get to libraries and modules after, but let's just do our sample script. Let's go to a new cell, and let's assign values to 2 variables. One will be the number that we're using, like if it's number 8, and then the second variable will be the value we want to raise it to, the power indice. So the first value, let's say n, or let's actually say x would be equal to 8, and then n will be something that we want to raise it to the power of. So let's say n is equal to 2. So it's basically you want 8 to be squared. And let's just do a new cell, because this is defining our variables. So the notation for power would be equal to x multiply by n. So it's x to the power of n. That's what we're saying here. And remember to run each cell with Command Enter. And if you want to see what we just did here with power, go in a new cell and just type out power. And there we see the result, which is x to the power of n. So it's 8 squared, and we get 64. So it works correctly. But instead of just having the raw output here at 64, let's just present it nicely in the form of a print statement instead. So let's do a print, and the statement we will be printing will be we want x to the power of n and see what the result is. So we will be using the percentage d, which acts as a placeholder. So it's some digit, it's a placeholder, sorry, for a number. So it's some sort of digit here, which in this case it represents x. So percentage d to the power of percentage d again is percentage d. So this is saying some number to the power of some number is some number. So it's 3 placeholders. Don't get confused with it. It's simply just a placeholder because we can't print 8 here. Like for instance, we can't put 8 to the power of 2 is 64, and the reason we can't do that is that this is just hard-coded the string, whatever we want to output. It's not based on any calculation up here. So if we change these variables to 9 and 3, it would still output this 8 to the power of 2, and it's not affecting the calculation because this is just pure text and has nothing to do with these variables. So that's why we put a placeholder, so it will change regardless of what these variables are equal to. Let's put back our placeholders, and then what we actually want to be as the output here would be, the syntax would be percentage, and we put x, n, and power. So remember to have a separate set of brackets for these two. So these are the 3 values, the 3 variables that will be substituted in the placeholders. So let's just run this print statement, and we have exactly what we have up here. So it's 8 to the power of 2 is 64. So the 3 variables were substituted into our statement here. And we can change this to something else. We can change it to 10 to the power of 4, and remember to run it again for each one. And power will be equal to 10,000 because it's 10 by 10 by 10 by 10. And then when we do this here, we have 10 to the power of 4 is 10,000. So that's our really easy example of a Python script to raise a power to a number. Join me in the next lecture as we look at what is a module. We are continuing with our functions lesson, and in this one we will be creating a function to calculate the mean of a string of a set of numbers, and you will get to see how we use return in a function. Now if we were to have a list, and we can have our list would be equal to a list of numbers, and let's put these numbers as 12, 14, 25, 89, 23, 56, and 22. So this is our list, and make sure that it is in square brackets. Now what we want to do is to create a function to calculate the mean of this list. So let's define our function to calculate the mean. The parameter, the argument that we will be passing in here would be list, and what we want this function to do at the end of the function, we need to return the mean. So we want a value to be returned at the end of the calculation. So we add the return statement here, and what we want to calculate would be, we're using 2 other built-in functions called sum and len, L-E-N. So that is sum, because the first thing you need to do when you calculate mean is to calculate the sum of all the numbers. So we create the sum of list, and then you divide that by the number of numbers. So then that is what the len function does. Len tells you how many we have here. Len of our list, right? Yeah, that's it. So we run this, and then we call our function. So we call calculate mean, and what you need to do to calculate mean is that you have to pass in the variable, and in this case the variable is list. Actually, I don't want to confuse you. just because the name of the variable is list does not mean that's why we chose to name the parameter list. They're not the same. I'm sorry about that. So let's put just here our numbers is equal to these. So our our function name calculate mean is passing in some sort of parameter, which can be list or x or y. It can be named anything, and we want to return the sum of whatever is the list of numbers in here, and then the length of all these numbers here. So we want to calculate the mean of these numbers here. So we are calling this function on these numbers. So we're calling it and passing numbers into this function. And let's see, remember to run each cell. Okay, great. So we did get the mean of these numbers. So it's the total of this divided by how many numbers there are. And we have calculated the mean of the numbers. And with the return value, it returned that value. As simple as that. And for practice, let's just do one more function. And we will be using the if-else statements that we used previously. So you get an example to see using if-else, but in the form of a function. So this will be if-else in a function. So what we want to do is any number that's entered, we want to output the positive value, meaning the absolute value of the number. So in mathematics, you have absolute values for integers, so that's what our function is going to be doing. So let's define the name of our function, and let's call it absolute. And the parameter that we're passing in would be number, colon. Then I'm not going to bother to put the optional text, we'll go straight into it. And then we do our if statement. So if a number is more than or equal to 0, remember the conditions we used last time, the more than and equal to. So this is our condition, is more than or equal to 0, colon. We are telling it what we want to happen if this condition is met. We are returning the number, whatever number is in here. But if that condition is not satisfied, we do an else. Remember to align else with the indentation of if. So it's else. You want to return. Now, if it's not more than 0, that means that it's less than 0, so it's a negative number. But if we want to return the absolute number, meaning we need it to be positive, as in if our number was minus 5, the absolute value of minus 5 is actually 5. So in order to do that, you put minus number, so that would become, for instance, minus 5, and then you get plus, because minus and minus would be a plus in basic mathematics. So this return statement at the end of the else, that's the end of our function. So run that cell, and then what we want to do is to call the absolute function and print out whatever our number is. So let us create a variable for the number, and let's say n is equal to 10, so it's more than 0 in this case. So let us pass this value, this variable, into our function now. So let's do absolute. The parameter will be n. That's all. Okay, and run each cell. Oh, my mistake. This is if number. If number, because it's our parameter. So if number is more than 0, so let's run that cell again to make sure it's correct. And now there's not really much of a change, because n is more than 0, and it will just return the same number that we has a variable here. But if we, alright, let's do another example. If n was actually equal to minus 20, and we ran it again, Great, so we got a positive number. It's a positive 20 because of this minus sign, and this is the absolute value. Okay, so that's it for this lecture. Join me in the next one. Welcome to Python terminology. We will be categorizing common terminologies that we would usually use throughout our Python practicals into Python scripts, modules, packages, and libraries. Now, a script is generally just any Python file that you would like to run. So if I have a Python file that I would like to add 2 numbers and I write that code, and I save that will be saved as my Python script. So it's generally just a Python file so that when you run it, you want it to be able to do something. So that is what a Python script is. I will create a Python script for you and you can actually code along with me because the definitions just doesn't make you fully understand everything. So let's go to our Python Google Colab notebook. Open a new one and you can call it script. You can download this script IPYNB notebook attached to this lecture. So remember I said that you want your script to just be able to do something. In this example, you want the script to be able to raise a number to a power. So if we have 2 numbers, 2 and 8, I want to raise 2 to the power of 8. Or vice versa, 8 to the power of 2. Otherwise meaning 8 by 8 or 8 squared. So it's a basic script we'll write here. So let's import math, and you will always see your Python script starting with some sort of import something. It's always going to be a few imports, and these are importing our libraries. So we'll get to libraries and modules after, but let's just do our sample script. Let's go to a new cell and let's assign values to 2 variables. One will be the number that we're using, like if it's number 8, and then the second variable will be the value we want to raise it to, the power indice. So the first value, let's say n, or let's actually say x would be equal to 8, and then n will be something that we want to raise it to the power of. So let's say n is equal to 2. So it's basically you want 8 to be squared. And let's just do a new cell because this is defining our variables. So the notation for power would be equal to x multiply by n. So it's x to the power of n. That's what we're saying here. Can remember to run each cell with Command Enter. And if you want to see what we just did here with power, go in a new cell and just type out power. And there we see the result, which is x to the power of n. So it's 8 squared and we get 64. So it works correctly. But instead of just having the raw output here at 64, let's just present it nicely in the form of a print statement instead. So let's do a print, and the statement we will be printing will be we want x to the power of n and see what the result is. So we will be using the percentage d, which acts as a placeholder. So it's some digit, it's a placeholder, for a number. So it's some sort of digit here, which in this case it represents x. So percentage d to the power of percentage d again is percentage d. So this is saying some number to the power of some number is some number. So it's 3 placeholders. Don't get confused with it. It's simply just a placeholder because we can't print 8 here. Like for instance, we can't put 8 to the power of 2 is 64, and the reason we can't do that is that this is just hard-coded the string whatever we want to output. It's not based on any calculation up here. So if we change these variables to 9 and 3, it would still output this a to the power of 2, and it's not affecting the calculation because this is just pure text and has nothing to do with these variables. So that's why we put a placeholder, so it will change regardless of what these variables are equal to. Let's put back our placeholders, and then what we actually want to be as the output here would be, the syntax would be percentage, and we put x, n, and power. So remember to have a separate set of brackets for these two. So these are the three values, the three variables that will be substituted in the placeholders. So let's just run this print statement, and we have exactly what we have up here. So it's 8 to the power of 2 is 64. So the three variables were substituted into our statement here, and we can change this to something else. We can change it to 10 to the power of 4, and remember to run it again for each one, and power will be equal to 10,000 because it's 10 by 10 by 10 by 10. And then when we do this here, we have 10 to the power of 4 is 10,000. So that's our really easy example of a Python script to raise a power to a number. Join me in the next lecture as we look at what is a module. In this lesson, we will be looking at modules. It's a Python terminology that we would be using all the time, and in the last lecture, we looked at Python scripts. And if you recall that in the last lecture, we started the last script in the last lecture with import math, and that's a library. We're importing a library here. But before we get to what's a library, let's consider what's a module. So the module is a Python file that you want to import into a script later on to perform a function that your application requires. And then we have packages here. So a package is a collection of modules, but it's not just any module. And a package has a bunch of modules that are related to each other. So for instance, in NLP, we would use NLTK package, and that has a bunch of functions in it. And then you have libraries, and a library is actually a loose term for a bunch of code, and a library can actually be consisting of thousands. And the reason we use libraries in Python is that libraries save us from writing all this code from scratch. Because if I have a library that consists of thousands of modules, and each module consists of a bunch of scripts, and these are created by wonderful people who create these scripts and these libraries and let them be available via the internet in an open source manner. Open source meaning it's free to access, and they created this for us. It seems, too good to be true, but that's how Python works. Let's jump into the other lecture and we'll actually create a module of our own. In this lecture, we will be creating a module and saving that module and then importing that module into our own script. So it's a really basic module. So let's define our function. So it's define chat greeting to name. That's our first parameter, and all we want this function to do would be to print out hello and whatever name that we want to print out. So it can be any name, and to print hello space, because you don't, if you don't put a space, whatever name we put will be hello and the name here without a space. So put the space, and then what we want to be following hello would be whatever parameter we place when we call the function and we pass the function onto. So I'll show you how it works, and it's as simple as you get. And in reality, the modules that we will be importing into our scripts are extremely long. I will actually show you some of the common modules and packages that we will be using for NLP. So let us name this first module. And in order for it to be a module, we need to save it as a .py file. And a .py file is simply a program file, or what we just call a script, written in Python. So let's save this. Actually, we want to download it. Download .py, not IPYNB. Download .py. I'm just saving that in my downloads folder. You can save it anywhere you like. Just remember where it is. And I'm naming it first module. Save. Right, so we have our first module.py saved to our local drive. Now let us go on to open a brand new Colab notebook called module.ipynb. From the first Colab notebook here, you can just go to File and New Notebook. When you open that new notebook, you can actually name it module.ipynb, and the first thing we need to do is that go to your Google Drive, and from your Google Drive, I want you to create a new folder called Module Lecture, and just click Create. And if we go to that folder, you'll see that it's empty. But what I want to do is that the first module.py that we saved to our local hard drive, you want to place it here. So let me just drop this file here. So you can go to New File, Upload, and go to wherever you saved your first module.py, and just upload it to here. So here's our module, our script that we saved before, and what we want to do now is that we want to import our module, but we need to change the location to make sure that we are working within this directory in our Google Drive. So the first thing we need to do is to mount our Colab notebook onto our Google Drive. Go directly navigate to this directory so it will be able to locate the module, so it will be able to find this file. So let us go back to module.ipynb and mount our notebook to our drive. So we do from google.colab import drive.mount, and the location that we are mounting here would be /content/G drive. When you run that cell, I will show you what happens. So you go to this URL, choose your Google Drive account, allow, and then you get an access code in the next step. So you just copy this, you can close it off, and then just paste it into here so you get your authorization code. So now we have mounted our drive. We have mounted our Colab notebook to our Google Drive, and to see what happened, if you click this little folder here, you will now see that we have G Drive here. Because actually, if you were to check this folder before mounting it to a drive, you will not see G Drive here. The Colab notebook will not know that Google Drive is there. So because we ran this, now we're able to access our Google Drive from the notebook. And if you click this little arrow, you see My Drive, and you'll notice it's the same directory navigation. So we have My Drive, and then from My Drive, we have all our folders located here. And then here we have our module lecture. So similarly, from our notebook, we navigate from Google Drive to My Drive. Then we see the same entire list here that we have in our entire Google Drive here. So from this, we can see module lectures right here, and we have our first module.py lecture right here. And let me show you another way of navigating this directory. If we do !ls, which is to provide a list within our Google Drive, it shows us these same two folders that I showed you above here. So we see Google Drive and sample data, but we actually want to get into the working directory module lecture. So we want to get into My Drive, and then we want to get into module lecture. So we do a cd, which is a change directory, %, cd, which is change directory, /content, /g drive, /my drive, and then /module lecture. So we're saying that we want to change the drive, we want to change our location, to here. So change our location. So now we are working in this directory, and if we do the ls again, now we see that we're actually, the only file that's listed in our folder is firstmodule.php. So this is exactly where we want to be. In a new cell, we want to import our first module and make sure that this is the same name of whatever we named our script as, our module. So we're importing the first module. So by importing it with this line, we are importing this bit of code. And if our module is super huge with hundreds of lines long in code, and we import it, we will be importing all of that functionality. So we're importing our little baby module right now. Run that with Command Enter and create a new cell. You can close this because we no longer need to see it. And the function in our module name was chat greeting. So we are able to call that function in our script without defining that function in our script. So essentially, if you have really long, complicated functions written by someone else and they saved that module for you, and you get it off the internet and you import their module, they save you from having to write all that code. You don't have to go write it anymore. So all you do is you call that module here, first module dot, and then you call the name of the function, in our case it's chat greeting, and then you pass whatever parameter you want to pass into that function. And in this case, we want to pass the name Nydia into it because the parameters that was in our brackets, our parentheses, was name. So we pass the name into our function. And if we do that, it prints out hello Nydia. And you notice we didn't have to put any print statement here, literally nothing. So what happened was that in the module that says, in that defined function named chat greeting that passes in a name, we want to print pure text hello and whatever name was passed in here. So that's why we printed hello and the name that was passed into the function. And that function was part of that module named first module that we imported here. So we did not need to write any more code. So that's how the import module works in Python. Over the next few sections, we will be looking at language syntax, part of speech, and parse trees. Now in some of the lectures, we get a bit really into the linguistics part of it, learning about language rules and grammar. Don't get me wrong, we will be doing quite a bit of practicals in between all the theory. So generally the structure will be some theory, a practical based on that theory lesson, so you can really get your hands on the concept and understand what's going on, and then also get some practice in learning how to use the Python functions and the Python libraries. For instance, there are Python libraries that will be creating our parse trees, would be conducting parts of speech analysis. Being able to code and use the Python libraries and Python functions for these language type processes does not mean that you understand the linguistics behind the NLP processes that Python is doing so nicely and making our lives a lot easier. But it's not good to be using the Python functions and have no idea of the concepts behind it. So the lectures based on language syntax, parts of speech, and parse trees are heavily needed when it comes to really cool applications like generative text. And generative text is used, for instance, in question answer chatbots. So if I, the human, were to ask a question, the bot has to figure out what I'm seeing, and some of the concepts based on these fundamentals are reasons why the bot is able to understand what I typed, and then furthermore understand how to generate that text answer for the human. Familiar examples that we use all the time would be Google autocompletes, grammar check, and speech recognition. Look at this example here. This sentence, I can see the door. Now, how would it know that SEA was incorrect and that the correct answer is SEE? So that is part of where part of speech comes in. And tree parsers will parse trees. So I will show you how these are related and how it actually works with Python and the concepts coming up shortly. Now, considering predictive text while we're chatting or using text messages, when we type the new, in this example, you see the three options that come up here for us. So it's the new strain, or the new one, or the new version. The new strain, obviously this is related to COVID. The new one or the new version. Three typical words that may be coming up after these two. So these three words are recommended to most likely follow these other two words called the new. So one of the tools needed to help us understand what word comes next would be, for instance, part of speech. Because if we were to just think about another concept, if you are to try to figure out the weather later today, this is a new analogy, and you want to know if tonight there's a chance that it will be rainy or clear skies, one of the best things to consider would be the weather now, or the weather right before tonight. So we need to learn as much as possible about the weather now, the cloud cover, humidity levels, wind direction. So finding out as much as possible right now, the conditions right now, gives us the best case to understand the type of weather that we can expect later. Very similarly, in order for us to predict the next word that will come, we need to learn as much as possible, as much information as possible on the word or the words that came before. So one of the things that we need to learn that will help us know the type of word that precedes the one that we are expecting, that we are predicting, would be the predictive text, if this is a noun or a verb. And it sounds really boring and really simple or basic, but it's very important. And so join me in the upcoming lectures as we go through these concepts, and then do some practicals, and then use the Python functions to actually execute these fundamental processes. In this section, we will be looking at language syntax. Now, why in a natural language processing Python course am I going to be talking about language syntax and linguistics at the depth of looking at how language is structured? Because before learning how to convert text data into machine-readable structured numeric data, we need to understand that language itself is structured. Now, you'll typically hear when you're learning Python or computer language, we'll always talk about syntax, especially when you have to run your code and you get a syntax error. So you generally associate syntax with computer programming, but syntax is the structure of any language, in our case, the English language. So what exactly is syntax? So syntax actually comes from the Greek word syntaxis. I'm not even sure if I'm pronouncing that correctly, but what's important is that we know the meaning. It means arrangement, and this refers to the way that words are arranged. So that it makes sense that syntax refers to the arrangement and how language is structured. So how are words structured? How are they arranged? Now, there are different ideas for how to categorize how to categorize these structures and these arrangements. So one way we classify how words are arranged is by grouping words together as they behave as one single unit or phrase, and we call this one single unit or phrase a constituent. But to get a clearer idea on what a constituent is, a constituent, that single phrase or that single unit, an example of a constituent, is a noun phrase. We all know what nouns are, and in this case, the constituent, which is our noun phrase, is a simple phrase that is built around a noun. So this simple phrase that is built around a noun acts as a single unit. And I'll show you what this means. We understand these things, we understand how simple these things are when you just look at the basic examples. So in this case, the noun phrase, it combines a noun and a determiner. So for example, we have a tree. This is a basic noun phrase. Some sweets, or the boat. So we have a determiner and a noun. The noun is tree, sweets, and the boat. Just to give you an idea on what a determiner is, a determiner goes together with a noun. So look at these two birds, they're paired up. This is the noun, this is the determiner. They go together. So it is, now the reason I'm teaching you these things is it will become important later on when we do topics such as parts of speech tagging, and you create a program that can take an entire text, an article, and pull out that Washington, D.C. is a noun, and it's a noun that refers to a geographic place. So it will get more detailed and complicated later on, but in order to know what your function is doing, when we have to go through all these texts and your computer is able to pull out what is a noun or what is a verb and then put that into context, trust me, these fundamentals are very important if you want to become great in natural language processing. So now we would abbreviate determiner commonly as DET, both in linguistics world and both in natural language processing data science world. So it is a word, phrase, or affix that occurs together with a noun or noun phrase. So like I said, it goes together with a noun or the noun phrase. So these are some examples. The girl is a student. So the noun is student and the other noun is girl. So the accompanying bit to girl is the. So this is the determiner. And a accompanies student. So this is the pair. So determiner is a. Another determiner in this case is, okay, I've lost my keys. The noun is keys. So what goes together with keys? My. So it's a possessive type of determiner because the noun keys belongs to me. So that's why it's a possessive type of determiner. And in this example, which book is that? What is the determiner? Is it which or is it that? Okay, maybe it's that. But it's not, because that accompanies is, which is a verb. Look for the noun in the statement, and the noun is book. So what word goes together with a noun? That would be which. And it is an interrogative type of determiner, meaning that it hints to asking a question, to interrogate. So it's which book is that? And then let's take an example of another determiner. I'll take this one. It's demonstrative. So in this case, it's this one, and it's showing, like in this case, I'm showing you it's this one. So I'm demonstrating that it's this one. That's why it's demonstrative. So this is the determiner in this example. For this one, both windows are open. Windows is the noun, so what is the determiner? I gave you a hint, it's a quantifier determiner. So in this case, both is the determiner. Both windows, because both goes together, it occurs with the noun windows. So if you remember the point of learning what a determiner is, it occurs with a noun or noun phrase to form a constituent. So a constituency occurs where we have a group of words that behave as a single unit. So now you see that when we look at this example here, I'll take this one. This is essentially can be grouped together, this one, because it's this is one group, a constituent. So I'll take, and you can separate it with this one. So we see that they go together as a single unit. Some sweets, that's a unit, so they belong together. So you can see that pattern as opposed to if you just have an entire jumble of words that just randomly go together. We need to have that structure. So if we know what a determinant is, we know what a noun is, you see that structure. So when we look at our examples, we see a structure in this sentence. Which book? This would be our constituent with a noun, and so you look for a pattern. When you find a noun, you see the word that occurs together with it, and then you find your constituent. So this is a constituent in the sentence. We previously looked at constituents, and the aim of this entire course, Natural Language Processing, is to take our human language, our human text language, and convert that into a machine-readable language. So yes, we spoke about converting text to integers so that the machine can read it. But what does this have to do with natural language processing? Essentially, I'm teaching you the fundamentals of what we call context-free grammar. And CFG is actually a very common and popular mathematical system used for modeling constituent structure. So continuing on the topic of grouping words together and these having these group of words that behave as a single unit, for instance, the noun phrase, let us continue on to other types of word groups. So we have the noun phrases, but we also have something called a verb phrase and also prepositional phrases. So we abbreviate this to NP and verb phrases to VB and VP and prepositional phrases to PP. But here we have determinant plus nominal. Don't get confused, that's very simple, it's straightforward actually. A nominal, now remember a noun phrase can have a sequence of words. It doesn't have to be something as simple as an airport. We can have more words involved with that. So if we were to have, let me just break this down for you. A noun phrase, an example of it from what we said earlier, can be a car. Or another noun phrase, the race. But we can have a sentence where we say the race car from Europe. So in that sentence, we would remove this A here. So this forms a sentence, the race car. So when we have this whole sentence here, this entire noun phrase, the race car, race and car, they are two nouns. So together they would form a nominal. So this nominal would have to be broken down into its two forms, which would be its two nouns. So I'll show you what that means. I will show you how that splits up in the next lecture where we look at parse trees. But for now, let's just stick to just looking at the different types of word groups. So that is our noun phrase. And now let's look at a verb phrase. Now a verb phrase consists of a verb plus a range of other phrases. It can be, you can have a verb phrase being equal to, so a verb phrase can actually be equal to, or consisting of, a verb plus a noun phrase. But it doesn't have to be restricted to that. It can actually also be a verb plus a prepositional phrase, or even a verb plus a noun phrase plus a prepositional phrase. An example of a verb phrase is eating the pancakes. So let's have our verb, which will be eating, and our noun phrase is the pancakes. So this entire thing is our verb phrase because it consists of a verb and our noun phrase. And similarly, a prepositional phrase it usually consists of a preposition plus a noun phrase. Well, not just plus, it's usually a case of a preposition followed by a noun phrase. So an example of this can be from, like from, the arrow is showing you from. And the noun phrase here would be the restaurant. So in a nutshell, a noun phrase is a group of words consisting of at least one noun and a determinant, so it can be the race or the race car. A verb phrase consists of a few different combinations where we have a verb involved together with maybe a noun phrase or a prepositional phrase, and that brings us to what a prepositional phrase is. It's a preposition usually followed by a noun phrase. I want us to return to this slide where we spoke about the different constituent types, the noun phrase and the word groups, because I want to show you how these parts of sentences go together without context being part of it. So I will show you how a sentence structure can be context free. So this is our noun phrase, the race car, but I'm going to change it to our noun phrase example to be the boy. And you'll see why. So you can just ignore the cartoon for now, and I'm going to change this to the boy, and I will change our verb, and I will change our verb actually not to eat, to the past tense of eat, to ate the pancakes. So this is our verb phrase, ate the pancakes, and noun phrase the boy, and prepositional phrase from the restaurant. So we can actually have a sentence that is equal to a noun phrase plus a verb phrase plus a prepositional phrase, and we can actually put it in brackets, meaning that we can fill this essentially with any different prepositional phrase. So it's, you can fill it with whatever interchangeable text that suits this type of word group, and I'll show you what that means. So we can actually put, like, substitute NP for our actual group of words. So we put the boy, and then we can substitute our VP for ate the pancakes, and then we'll add in the prepositional phrase here as well too, and we can actually just put from the restaurant. So the boy ate the pancakes. I'm not going to write it out fully, but yeah, I'll do it. It'll look nice so that we ate the pancakes from the restaurant. So this entire sentence here is represented by this, by this. So this is equal to the sentence, but that's actually not the important part of this lesson. The whole point I'm trying to show you here is that I know I'm going a bit too detailed into this, but I just need you to understand the difference and the significance of a context-free grammatical lexical structure, because the computer does not understand when it looks at the boy ate the pancakes from the restaurant. That makes no sense. So we structurally, grammatically, we can take linguistic theory and start to form a structure from language that has nothing to do with computer programming. It's just how languages are structured. So this prepositional phrase here, let's substitute it, and instead of saying from the restaurant, another example of a prepositional phrase can be, okay, let's give an example of a preposition which is under. So that's the P part of it. So the prepositional phrase consists of a preposition plus a noun phrase. So let's add in a noun phrase. So a noun phrase can be a table, because this is our determinant and this is our noun. So this is our noun phrase and this is our preposition. So that gives us P plus NP, which is equal to our prepositional phrase. So under a table can be substituted inside here. We have a new sentence called the boy ate the pancakes under a table. And that makes grammatical sense, is grammatically correct. So the nice part of this lecture that I want to show you is that we have grammatical rules. And okay, so if you were to type a sentence in Grammarly that said the boy ate the pancakes under and not a table, let us say he ate the pancakes under jumping table. Grammarly will highlight for you this and tell you it's not correct. How would Grammarly know that something is not right here? It's because the syntax is incorrect. Why is the syntax incorrect? The syntax is incorrect because we have a noun phrase followed by a verb phrase followed by a preposition which is under, but the preposition in this case is followed by a verb and then a noun. So essentially this verb and noun forms a verb phrase, but after a preposition you would usually have your noun phrase, so it's expecting a different structure. So under jumping table, now to us it does not make sense in context, but according to syntax we're not using context, so we don't know that this is wrong because it makes no sense under jumping table. Yeah, it makes no actual context sense, but it makes no syntax sense because the preposition is not expecting, but it grammatically forms that structure together with a noun phrase. So instead of jumping table, let's change this now into a noun phrase and use, instead of jumping table, a noun phrase can be, you can put a table or the door. Now look at this one. If we were to put the boy ate the pancakes under the door, that makes syntax sense. So according to grammatical syntax, context-free syntax, that is correct syntactically. So it is correct according to that, but that's why we need to go further now into understanding how to add context and assess context, or find a way to have a word association so you know that under the door does not make sense. So that is where the word embedding part of it comes in later. So I just want you to understand the difference between the context-free structure. So that's the magical part of NLP. When you look at all these things we use from a day-to-day basis, when we speak and we talk and our brain understands the context, we can look at a sentence and know when it's wrong. That is what we are teaching the natural language processing algorithm to do in the upcoming lectures. So thank you for your patience and join me in the next lecture. You can detect the difference between the subject, which is what songs, and British music bands, then you will know that we want a list of songs, not a list of music bands. So that's an example of when you type in something for a question answering system or a search engine. This is one of the many steps involved in figuring out what context is going on there, what is being asked. And one more useful application we look at, well, two really, would be information extraction and also parsing as one of the fundamental, before we get to opinion mining and sentiment analysis. So take this example for information extraction. If we have this sentence in a newspaper, and we're going through articles in many newspapers, and you get this sentence: yesterday, New York-based Monsters Inc. announced their acquisition of Disney Corp. And you want to be able to extract information so that you can figure out what companies are merging. So you want it in this structure. So you want this structure: company 1, company 2, and date. So from this text, you have to figure out that yesterday means a date, and then Monsters Inc. and Disney Corp are the company 1 and company 2. Now you can say that if we were to extract our entities, we can realize that, okay, maybe we look at the capital letters, but it's not as simple as that, because how do we differentiate Monsters Inc. from New York as being a company? Why is New York not a company? How does it know that New York is a location? So these are all essential parts of parsing that is needed in the background for information extraction. Then when we move on to opinion mining and sentiment analysis, when we look at parts of speech and syntactic parsing, they're used to extract noun phrases. And like I just gave you an example here where we extracted the noun phrase, what songs? Okay, so say for instance we have Amazon reviews, and you want to figure out if the review is negative or positive. We break down the review, we extract noun phrases and figure out what's a noun, what's the subject of the sentence, so we know what the sentence may be asking, or the main thing the sentence is saying. And then we look for the descriptive word on the noun. So if the descriptive word that relates to the noun is excellent or poor, then we classify the opinion based on it, because of these pattern-based approaches in extracting the phrases. So that is it for this lecture. Join me in the upcoming one. Today's lesson will be tokenization. So before we get into tokenization, let's just remember that this is part of our pre-processing to prep the data, and the whole reason for this is that the machine can't read the way we do, so this is considered unstructured data. So we're making it machine readable, so then after this cleaning process, we'll be able to use that new structured data for our NLP models. So what is a token? We can think of a word as being a token in a sentence, and a sentence being a token in a paragraph. So basically, a sentence is a chunk of these tokens put together, and a basic example of pre-processing to turn the non-structured data to become readable to the machine is to make a structure for the machine to recognize what exactly constitutes a word. And in the English language in particular, we use what we call a space to separate our words. So my brain recognizes that between the word we and can, the space shows me that these are two separate words. Now, it's a bit different for certain languages. For instance, Chinese, it's not always that clear-cut. So essentially, breaking down data into small chunks is what we call tokenization. So a really simple example is that we would have here, hello, how are you today? And we tokenize it by separating these slashes, which show a separation, hello, how are you today? These are separate words, and the slashes represent a break in this entire sentence. So each one of them represents a token. Now in tokenization, another way to call this would be word or sentence segmentation. Now we're going to look at an example here of a method of tokenization or word segmentation using white space. So what we're doing would be segmenting sequenced text, and I'm calling it sequenced text, but this can be a sentence or a paragraph, a chapter in a book. So we're taking these sequence text and trying to break them down into chunks of sentences and then further into words. Now this may seem straightforward, and in English as a human using white space to separate into words with that special space character is pretty straightforward, and it may seem ideal for word tokenization to use white space for splitting up a sentence into words, but with closer examination, white space will prove to be insufficient. Take a look at this example. He said, "I need new gloves." The shopkeeper replied, "Those are no good. These are better. They cost £4 and 5 pennies. We're going to segment using only white space. So, some examples of what we're going to get would be said with a comma, "I, gloves," replied with a comma. And you notice that the words aren't alone in these cases. We're getting the white space dividing it, yes, but we're getting our token together with these unwanted punctuation marks. Now, as a human, I know this is fine, I know what this means. Said, those, good. But as a computer, I go on the character, and said, S-A-I-D, comma, is not the same as S-A-I-D. So my understanding would be these are two completely separate words. The desired output we want would be this clean case of perfect separated tokens where we obtain purely the word only, with the characters only belonging to that word without the unnecessary punctuation. So let's see if there's another way to do this that can give us the desired output we want. So let's see if this is going to help. What if we use a word boundary where we combine both punctuation and white space, right? Now, this will bring up a problem because punctuation frequently occurs inside words, and this is due to what we call cliticization. Let's just jump ahead so I'll show you what cliticization is. Welcome to this lecture on how to open an IPYNB file in Google Colab environment. All of our practicals will be done within the Google Colab environment and will look very similar to this. So in order to open these up, I will show you step by step how to do so. Every time that you need to do a practical project, I would provide the necessary resources. So for that particular lecture, for instance, in this case, it's a lecture on tokenization. It's one of the first practicals you would be doing. Kindly go over to the right-hand side here. For the corresponding lecture, it's always highlighted in blue. So when you go to here, you'll see a folder on resources, and you kindly just click on resources. And for each one of these, click on them and download them. So once that's downloaded to your local computer, go over to your Google Drive, go to the Colab Notebooks folder that we just created in the lecture before this, and go to NLP Code Along, and you can just drop that file that you just downloaded into this folder by simply taking that file and dragging it here. Or if you don't want to do that, you can also go to New, File Upload, and go directly to wherever the file is and upload it. I generally prefer to just drag it across. It is very easy if you are using Mac. I'm not sure with Windows, maybe you might prefer to do it this method. So just move it across there. And now to open the resource, your IPYNB file, all you have to do, click on this, double click, and it will prompt you to ask what do you want to open it with, and we want to open it with Google Collaboratory. So just select Google. So select Google Colab, and then you can go ahead to do your Python in your notebook. So we just took a look, quick overview of tokenization with NLTK. Now we're going to get into the practical bits of it. So let's jump straight into our notebook, our Google Colab notebook. And I have some headings already made for you here because there's just titles, so that when you're doing your reviews and you want to do some revision, we have some just guidance here, because without the text, sometimes the bits of code can just get a bit, you can get a bit lost in it. So this is our first cell. Okay, so let's create our new cell. So you can either click on the cell and go to plus code. The best way is to just use an abbreviation, your shortcut, and do Control MB for the cell below. So the first thing we're going to do is type import NLTK. So here we're going to be importing our NLTK package, and when you use the hashtag, this is not going to be compiled, so it's just for documentation purposes. And to run our cell, you can either press play here, or it's better to do the shortcut, which is Command Enter, right? And then we add another cell again below, which was Control MB. So we want to download the NLTK package and also unzip it. So to do this, we do from nltk.tokenize, we import word tokenize, and nltk.download. In quotes, you put punct, and we run that cell. Oh, I'm sorry. It's word tokenize. Okay, so there we go. We've downloaded the package punct. So what it does, it allows us to unzip our tokenizers. So let's take a look at how we're going to use Python to break up the sentence, just like the examples we did before on the slides. Okay, so I gave you a sentence here. It's a series of tokens, and this is a sentence, and we want to break this up into tokens. So what we're going to do is just create our new cell below, and we're going to tokenize the sentence. So pull up on our function word tokenize, and what we want to tokenize is our sentence. Okay, so what we want to tokenize is our sentence, and what we do is that we run the cell and sentence, and then we tokenize it, and we see here it's broken up. So we have the he, which is separated from the apostrophe s, which is correct, and we see that shepherd does not take the period together with the word, so it's separated. And yeah, so also dogs, it's not combined with the exclamation mark, which is what we wanted. And similarly, now let's do the sentence tokenization example. So I gave you this series, this sequence of text, and it's an article with more than one sentence. So there's sentence 1, sentence 2, sentence 3, and so what you're going to do, we're going to do the same. So before, remember we had word tokenize being our function, right? And here we downloaded word tokenize, right? So we're going to do it similarly for sentence tokenize. So from NLTK dot tokenize, we are going to import the sent tokenize method, and then we're going to run the method. So that would be sent tokenize, and we're going to tokenize the article. So remember to run our cells, and let's see what happens. Great. So we have sentence 1, which is separated. So this is our first sentence. Did you know that World War I brought German Shepherds to the Western Hemisphere? And the second one, which is Rin Tin Tin, was a German Shepherd who was rescued from World War I, which is true, and they are some of the smartest dogs. So this is some sentence extraction for you, and so yeah, that's it for your basic introduction to word and sentence tokenization with NLTK. And because later on we're going to be using this more complicated NLP, and I don't want you to be lost, so just practice it for now, and it's okay if you don't remember it. Later on when you see it, you'll just know that you're familiar with it, so you won't be lost. Now, moving on to what the intended video is about, is the regex method to substitute, which is re.sub. So I've provided you with the string already, and the string is 1 and 2 and 3 and 4 and 5. We did this earlier in our theory slides, and what we want to do, if you remember, is to replace these spaces with a dash between each one of them. Okay, so how are we going to do that? Using our regex sub method. What we want to do is just name our variable anything you want. Result will equal to re.sub. That's our method of regex, and we want to put in parentheses a space, right? Because what we're looking for is our initial space, then comma, and the second term here is what we want to substitute it with, and we want this to be done in our variable name string. Okay, if we had this named anything else, like substitute, this would be changed to substitute, right? And let's just run that as it is. And I'm sorry, let's just print it out one time. Print result. Great. So we have here, every time there's a space, we got a substitute with a dash. And just to recall what the notation here means, we have a variable, we called it our regex sub method, and our first instance was the original thing that we want to change, and the second notation is what we want it to become, and we just remember to put our comma and call in this variable. Okay, so that's essentially the substitute method. Join me in the upcoming video where we learn the search method, which was my favorite in these methods because it's basically something we use quite often. So join me in the other video. So we just learned how to do our regex substitute method, and now we're moving along to our regex search method. So what this search function does is that it takes a pattern and a string and it scans it from whatever text that we input, and let me just show you how this works. So we're gonna do for whatever pattern that we want, right? We call that variable pattern wanted, and we equal to our square brackets. We put what we're looking for. NLP course, that's one of the patterns we're looking for. And the second one would be advanced. And that's the pattern that we want. And the string of text that we're looking for it in, which can be usually like chapter or whatnot, but for simplicity's sake, let's just call it a basic sentence. Our string would be the best NLP course for beginners come up with awesome practical projects. And right, so what this means is that we have this pattern that we want, either NLP course or advanced, and we're calling it a pattern, but it's what we refer to as a phrase or a term that we're going to enter in our search bar to look for. And this is the body of text that we want to find this pattern. So that's the pattern and string that I was talking about. And then we go to for pattern in pattern wanted, colon, print. We're going to just put some text. You can put anything here you want. I'm putting looking for, and we're looking for something specific, which is put in quotes, double quotes, which would be our pattern, right? In double quotes again, our desired string, and we end that, and you just put another percentage sign here, and we specify. It's very important that we specify our pattern and string order again. Close that off, and we end it with our space, continuing with our if statement for our searches. If regex.search for our pattern that we want in the string that we specified with colon, you print something positive. You can put success, or you can print yay search successful. If not, if the pattern is not in the string, then we else indent print, oh no, I'm sad, we did not find anything. Okay, so let's see what we get from this, right? And don't forget your colon here, and let's run that. Right, so it outputted looking for NLP course, which was looking for our pattern, right? Looking for our pattern in our string, in this string here, right? And here it says, yes, this search was successful because NLP course is in that string. Now, this is a bit jumbled, so let's put this on a new line. So right after our looking for, but within these parentheses, you put colon \n, and that means new line in Python. So we want to just copy that and also put it at the end of this. Yeah, right? So let's run that again. See, it's much cleaner there. So now for the second one, for our else, so it's if the pattern is not found in the string, right? You would print, oh no, we did not find anything, which is what happened here, because the second pattern that we're looking for, advanced, my spelling is off there. Either way, it's not in this sentence, so advanced, it's nowhere in our string, so it outputted, oh no, we did not find anything. So that's the gist of how regex search works. So you can make up your own strings and your own patterns and play with this a bit for your own self, so you remember the syntax and the patterns, and it's a bit of practice for you for Python if this is brand new for you. And take your time on that, play around with it, and then join me in the next lecture where we look at regex find all. Continuing from our last video where we learned regex.search method, let's now look at regex.find all. Now, in comparing the search and find all, you may think it's rather similar. Well, you may not even see the difference between both of them, but take in consideration that the search module will only return the first occurrence that matches the specified pattern. What that means is that in this case, we're searching for the specified pattern NLP course. We don't know if this is present once, twice, or 10 times in a document. All it knows is that positive or negative, yes or no, if this term, this pattern is in this string. So in this case, the NLP course could have also been a second case here and also second inserted here, but the search would just tell you a yes or no binary. Yeah, search was successful, it's in the document. Now if we want to find all, this is more useful, it's beneficial in a case where you want to extract information. And information extraction later on in NLP, you'll realize it's very, very important for a lot of different NLP applications in various fields. And the find all method will iterate over all the lines of the file and retain all those matches. So let's take a look and see how the find all method differs to the search method. So we'll create our variable called contact details and put a bunch of contact details here meshed together with no proper order. So we're just going to put some names like Duke Richards. Let's put his phone number, and how about let's put his email address, duke@dukeemail.com. And how about someone else, Mr. Joe Denver? We notice we're just putting it randomly, it's not in any specific order. And let's put the date that he signed up to do a brand new course, January 5th of 2020. And his email contact would be joe@mrdenver@gmail.com. And let's put someone else randomly, and it can be in any order. So let's put his date, 2020, that the course is going to finish on the 10th of December. How about let's have some fun, it's Christmas Eve, and a name, John Black, and his phone number, +44 784 5640, some random numbers. And right, so that's our contact details. Right, actually we're not running that. We want to put now what we want, right? This is our entire file here, right? And this is the file that I'm telling you about that we want to search, right? And what we want to extract information, right? So let's call this our example, our information extraction example, right? So what we want to do is that we want to find the email addresses in our contact details. Now, when we look at this as a human, I know that this is not the email address, and neither this. I can differentiate that this is some numbers, phone number most likely, this is a date, and obviously this is my email. Now, before we were doing segments for words and sentences based on punctuation, and we know that they were going to have problems later on when we have punctuations in between text. In this case, we don't want to split here because this is not a demarcation between two tokens. This is our whole token that we want, but this token has symbols and periods. But so how are we going to get around that, right? How can we split it into tokens, or put a series of different symbols to show how would our machine know what an email address is? So let's take a look at that. Join me in the upcoming video to complete this exercise in extracting the email addresses from the contact details. Welcome to our new lesson where we are continuing from the same code along tokenization regex.ipynb notebook that we have been using throughout this chapter, and we are continuing with our task of trying to extract the email addresses from this entire bit of contact details. So to do that, we just to remind you, we're using the regex method of the find all function. So continuing, let's type out email info, which is our variable, equal to our function find all. Now, before I type this, I don't want to scare you. It's very, very basic. It's simple, but it may look complicated. Essentially, an email address is simply some alphanumeric characters that are found directly before the @ symbol and directly after that @ symbol. And for an email address, we can, let me just add another one as well too. Let's say my name at hotmail.com. Actually, I wanted to show you with the underscore. So my name _77 at hotmail.com. And these email addresses, they are a string of letters or numbers or underscores that are placed directly before the @ symbol and directly after. When it's after, it always has a dot, right? So we can see that there's a pattern here. We want to try to mimic this pattern with a formula that are understood when using regular expression languages. Now remember this little note here for future when we're using NLP in more advanced methods and you see something with an R. What I mean is that in regular expressions, we have been using the / character, and it's always used, this / character, to indicate special forms. But there's an instance where backslashes are not handled in any special way in a string literal prefix with an R. So let me show you what this means. Open parentheses, put the letter R in our apostrophe, and then we put open and close our parentheses here where we use the same W from before. W that I have a note earlier that we went through where we use W to represent any word character that is alphanumeric which includes letters, numbers, and underscore, right? Keeping that in mind, we are looking for alphanumeric before the @ symbol, but it's not only alphanumeric with the underscore and numbers and letters, right? We would also like to include the period symbol and dashes, and we also want to put a plus symbol like before where we use that in order to keep searching, right? If we go in order of the format of an email, we have that bunch of alphanumeric characters followed by an @ symbol. We do not want this @ symbol to demarcate an end of a token, for instance, the end of a sentence or the end of a word, because this is the entire token that we want. So in this case, we must include the @ symbol in our formula or our regular expression, and then we simply repeat the same part of the formula, right? But make sure it's in between your parentheses. So basically this is a regular expression to represent the equivalent of an email. You can see it here where we have alphanumeric before and after our @ symbol, remember to put that same plus sign there from before, comma, and we call our variable from here, that's contact details. Okay, and let's write our for loop. So for email in email info, we would like to print email, and that's it. Let's see what happens. Excellent. We get our 3 email addresses only and nothing else from the contact details. So just to recap, we used a regular expression to be able to find and extract only the email addresses from this cumbersome, complicated list of contact details, and it's all nicely laid out here for us. And you can go over this some more, and if you have any questions, always just feel free to send them my way and I'll be happy to answer them. That's it for this lecture, and join me in the other video. Thank you. Welcome to our lesson where we learn about grammar rules. We take it for granted how important automatic grammar correcting is. We use it all the time for Microsoft Word and Grammarly, for instance. I don't even know if I would have passed uni without it. Understanding the language syntax is one of the first steps needed by the algorithm in order to detect whether grammar is correct or not. The algorithm needs to know if the rule is being broken, if this grammar rule is being broken, without any consideration whatsoever of the context. So these are context-free, so ensure that you always remember that it's context-free grammar rules, so that it doesn't matter what the sentence is saying. As a human, you will know that something sounds right or wrong based on the context that it's not making sense to you. But to the algorithm, it's purely looking at grammar rules. An example of how a grammar rule can be written with grammar rule notation, you would commonly see something like S with an arrow and then parts of a sentence. So like you may see NP and VP. If you recall, when we looked at the constituents of a sentence, we looked at NP and VP, the noun phrase and the verb phrase. What is S? S is purely a designated start symbol, so it shows the starting sentence node. So just consider it the starting symbol that we use to show that this is the sentence node, and you talk it out to say that, okay, this sentence is made up of a noun phrase followed by a verb phrase. So essentially all this is telling you is that we have a rule. This is one example of a grammar rule, of the grammar syntax. So this one rule is showing us that a sentence can be made up of a noun phrase followed by a verb phrase. So the order is actually important. So it tells you that any sort of noun phrase would generally have a verb phrase following, and when you have this pair, it's syntactically correct. So keeping in mind this sentence, this grammar rule of NP being followed by a verb phrase, an example of this will make it a lot clearer. So if the example for this entire sentence can be, I want a morning flight we break this up to the noun phrase and a verb phrase. And if you remember correctly, the verb phrase one of the combinations a verb phrase can consist of would be a verb, which is want, followed by a noun phrase. Because we have our determinant and we have our group pair, our two nouns. So this is both of them combined here. Now this is our verb phrase, and here would be the noun phrase. let's keep in mind the example I used. I want a morning flight. But the sentence can have different language rules applied to it and have a different types of structure, different parts of the sentence based on different types of syntax that follow the same grammar rule of NP and VP, and I'm going to show you some examples about that. Let's look at the noun phrase first. Now the noun phrase can actually have a few different variations, and that can be, you can have, I'll put the examples here for you. First example is that the noun phrase, we had it split so that we had I. And if we used I in this case, the noun phrase would be only a pronoun. But if you recall, when we looked at the constituents of sentences, so this verb phrase, want a morning flight, can be structured differently with correct syntax. We can form another sentence where the verb phrase consists of a verb, a noun phrase, and a prepositional phrase. And in this case, an example can be, instead of I want a morning flight only, it can be I want a morning flight from Manchester. So from Manchester is now our prepositional phrase. Our noun phrase is a morning flight, and the entire verb phrase would be this want a morning flight from Manchester. So another part of our noun phrase can actually be, instead of a pronoun, we can have a proper noun. And in this case, the example of our proper noun would be Manchester. Or simply, if I were to say I want a flight, so that can be I want a flight. This verb phrase is made up of this noun phrase, and this noun phrase has its determinant and the proper noun here. So we can also have another example here being the determinant nominal, and this would be a flight. And now that I mentioned nominal, you have the nominal noun and also just a straight out noun. And a nominal noun would be, in this case, our morning flight, because these flight on its own is a noun, and flight is a noun and morning as well. So together this is our nominal noun. So this can be our example, which will be morning plus flight. And then our noun alone can be flight or flights. Okay, let's put flights for now. So what I'm showing you here is that we have examples of pieces of a sentence that we can stick in to sentences. The algorithm would recognize it like that. So in this case, I want a morning flight from Manchester. It actually sees it as noun phrase, verb phrase, and then it breaks it down into verb, noun phrase, and prepositional phrase, and it has that order. So it looks for that rule. So this sort of context, that rule, and that rule is broken down into more rules, which is the verb, noun phrase, and prepositional phrase. I mentioned to you here the prepositional phrase, an example being from Manchester. So we can write it here if you want to take a note of your sentence structure, the types of syntax. So the prepositional phrase, if you recall, I talked about this in the constituents lecture before, but the prepositional phrase generally consists of a preposition. And a good example of that would be our example here with from Manchester. So we can have from, which is our preposition, and then it adds on, it goes together with a noun phrase. In this case, the noun phrase is purely our noun, and that, purely our proper noun, and that would just be from Manchester. Let us take a note of the verb phrase. And the verb phrase, some examples, like how we break this up into the syntax portions, can be, we can have a verb, and the verb in the verb phrase can simply be do, or it can actually be consisting of a verb and a noun phrase, like we mentioned before, and that can be an example: want a flight. Same as above. So we have want, then we have a flight. Or we can have the verb plus the noun phrase plus the prepositional phrase, like we mentioned before as well. And in this case, we can have want a morning flight from Manchester, or we can even have leave, which is a verb, leave, and then we have the noun phrase and the prepositional phrase. So the noun phrase here would be, I want to leave Manchester and then we have the prepositional phrase, which will be in the morning. Or one last example, we can have a structure where the verb phrase is a verb plus prepositional phrase. In this case, we don't have the noun phrase. An example of that can be on Friday. So this is a preposition and this is our noun. So this is our prepositional phrase. So what I'm showing you here is that we can actually substitute some of these together like in allocated slots, and it would make sense perfectly, not based on context but based on syntax. So we can mix this up so that we can have, instead of I, we can have he, and our sentence can become, he wants a flight on Friday. So in that case, we have our noun phrase, he, and a verb phrase, wants a flight on Friday, and that consists of our verb. Our verb phrase consists of our verb. He wants a flight on Friday, so it's the verb plus the prepositional phrase, and it's the same thing, but it's a totally different sentence. He wants a flight on Friday. It follows that same structure, so it's syntactically correct. And if we are to mix up different noun phrases with different prepositional phrases and different verb phrases, we can use that same S consists of the rule where we have an NP followed by a VP. You can create different versions of noun phrases and different versions of verb phrases and put them together side by side like this to form the syntax, the correct syntax, and you'll notice that the grammar is correct based purely on the syntax. It may not always make sense, but it's syntactically correct. And later on in the course, we will realize how we step further from just the syntax of it, and then how we start making sense of it, like how we can figure out if a word belongs there or not, or why it doesn't belong there, because it does not make sense, it's not related to the topic or to the context of the sentence. We'll get to that after, when we start looking at similarity. But for now, keep in mind that we are looking at context-free syntax, where it seems basically like a formula. So this is the structure. And it's not the only example of a grammar rule. I'm just giving you one example of a type of grammar rule. Join me in the next lecture and I show you another example. Welcome to the lecture on parse trees. Another way to call a parse tree can be a constituency-based parse tree. It's basically the same thing. If you remember in the last lecture, right before this one, we did an example, well, actually quite a few examples, of a sentence node having the grammar rule of a noun phrase followed by a verb phrase. And we had a few examples of noun phrases that could be followed by verb phrases, and the verb phrases had combinations of verbs and noun phrases and prepositional phrases and mixes of these. So what we want to do now is that we want to construct this and represent our rule in the form of a parse tree. And it's not just the rule that would be in the form of the parse tree, it would be the actual sentence. Because in everything we do in NLP, our algorithm has to be able to take our words and break it down into a parse tree. And yes, we use algorithms to do this, but of course we must know the theory behind it. So how our parse tree starts off with would be the same way it is here with S to the noun phrase and a verb phrase, but we started off like this, where we start with S at the top of the tree, and we do a first split. And the first thing we split here would be like this. So it would be I, which in this case was our noun, or our noun phrase, basically. And then on this side, we have our verb phrase. And here, we don't have to go any further because we're not breaking this down into anything more. And we can just label this as I. But this one needs to get further broken down because this consists of a verb and our noun phrase. So that's exactly how we will do it. We will split this now into our verb and then also the noun phrase. And we don't need to split this one anymore. So that means that we have our verb, which would be want. But the noun phrase has to split these two. So it would be A and flight, because A is actually the determinant and the flight is the actual noun. So the determinant is simply A and the noun is flight. So if we take these off, I just put the labels here for you to understand it, but basically the entire tree is purely S, NP, VP, and V and NP. So this is how we break it down. Oh, I'm sorry, right? And we have two more here, which would be the determinant and the noun. So this here is the parse tree and how we represent our sentence using the constituents, and these constituents make sense, grammatically correct, because they are part of this grammar rule, the NP followed by the VP. Let's go to the other lecture and let's do one more example of a parse tree. 2 lectures before this one, we did this example, I want a morning flight, and I showed you the language syntax of the NP followed by VP. And we are going to do a parse tree to represent this. It's very similar to the parse tree we drew in the previous example, and this one is just a slightly more elements in the parse tree, so let's just do it for some practice. So let's start as usual with the starting node S, and we are going to split this up into our noun phrase, which would be, okay, so this would be our noun phrase, and in this case our noun phrase is I, and the pronoun is I. I'm just putting it in a different color so that we wouldn't, we'll be able to focus on the tree. That would be in blue. Right, so this part now, the verb phrase. We have our verb and then we have the entire phrase. So we have verb and then we split that into our entire noun phrase, and the verb is simply want, and what we have to do is split up the noun phrase into a, and it's morning flight this time. The difference in the last lecture, we used I want a flight. So we stopped here because we had just put a and then our other noun, which was flight. But with a slight complication where we added morning flight, yes, in this case we have the determinant, and that determinant is a, but now we have to break it into our morning flight. And the morning flight is actually our nominal, and the nominal is broken down into morning. Sorry, it's actually right. So it's not right. So it's broken down into our noun and another noun. So which is basically the same thing in this case. So this noun is morning, and this one is flight. So this in blue is our parse tree for the sentence. Join me in the upcoming lecture where we use Python to do a practical and we create our parse tree in our Google Colab notebook. Welcome. In this lecture, we will be doing a practical project consisting of parts of speech tagging, but the main objective of this lecture would be to construct a parse tree. The parse tree would be created at the end of the project, and essentially this is what you will be making. This will be the output of the project, and you notice it's very similar. It's the same thing like what we drew by hand in the previous lecture. We created it from the S node, and then we worked our way through the sentence to break it up into the determinant and the nouns and the verb phrase and so forth. You can download the parser lecture.ipynb notebook associated with this lecture. Then open it up, and I've put some bare notes for you, and we're going to fill it out as usual, starting with our imports. The first thing we import would be NLTK, because the parser that we will be using, it is called the Perceptron tagger, and it's actually part of NLTK, the library, and I've attached a resource here for you. I've included that, so you can always click on this link and it would take you to the NLTK module, the resource, and there's a lot of source code here if you want to look at it and get familiar with what exactly from NLTK that we are importing. Okay, so this is just a brief idea of the NLTK Perceptron module. Let's get back to our imports, right? So this is why we are importing NLTK, so we can use all that cool stuff that they gave us through source code, through open source. And right now that we import NLTK, we want to download the relevant packages that we want. So what we need would be to download Punkt first of all. The reason we are doing that is because we need to tokenize, and we will be tokenizing with the use of Punkt that we download through NLTK. And the second thing we need to download would be the averaged perceptron tagger that I just mentioned. So averaged perceptron. And after downloading that, we just need to do a from nltk.tokenize. We want to import word tokenize. Then from NLTK as well, we also need .tag, import parts of speech tag, POSTG. Lastly, from NLTK, import parts of speech tag, word tokenize, and regex p parser. The reason we are downloading Punkt, just so you remember, would be because NLTK, this package includes a pre-trained tokenizer, and that pre-trained tokenizer is called punct. And the reason we need the averaged perceptron tagger is that the perceptron part-of-speech tagger, it implements part-of-speech tagging via a method called the averaged structured perceptron algorithm. So we are using this perceptron algorithm to help us figure out what needs to be tagged with what part of speech. Essentially, the structured perceptron, we use it for part of speech tagging, and if you want to think about it, the simplest approach for part of speech tagging using a structured perceptron algorithm is to break down your sentence into a sort of per token tagging, and you go from left to right. So in this case, look at this sentence, and you can take any sentence, and this entire sentence is our big problem. And what we want to do is to break down this big problem into individual tokens, and then we tag from left to right. So as you can see, it makes perfect sense as to why we downloaded these packages from the module NLTK, because punct, first of all, we need to look at our big problem, which is our entire sentence, and break that problem up into tokens, and that's where punct comes in. And then we need to find a way to weigh these tokens and figure out the parts of speech, and that's where the average perceptron tagger comes in. So it tags from left to right in that order. Moving along, we want to have let's have our sample text, and I'm using some text from this book. It's actually one of my favorite childhood stories, still is a favorite story, and our sample text would be: a shoemaker and his wife were very poor. Now we want to find the parts of speech tags for the sentence. So tags would be equal to parts of speech tag, which is what we imported here, and we will pass word tokenize onto our sample text. So we are taking our sample text, which is here, and passing that into the word tokenize function, and in turn we are passing that now, after we tokenize it, we are passing it into the parts of speech function to tag our sentence, to tag the sentence. And we can print our tags just to see what this line did. Great. It took our entire sentence and labeled each token with its respective part of speech tag. So we have A, which is the determinant, shoemaker, which is our noun, and is a coordinated conjunction. His wife were, as we go on, there's poor, which is our adjective, JJ. If you're not sure what these abbreviations mean, you can go down to the IBM Watson resource, and it's a resource that will tell you what each abbreviation is. Here we have each one of them: DT, determiner, CD, cardinal number, and N, singular noun, and an S, plural noun. So if you're not sure when you're going through your own examples, you can always reference this website, and just remember it's right here, IBM Watson resource. Moving along, we will be using now the regex parser. The reason we are doing this now is that this isn't sufficient. This part of speech tagging is not enough. We need to take it a step further and do something called, you can call it partial parsing, but it's more known as chunk extraction, because what we want to do is that in order to create our parse tree, we need to figure out the phrases themselves, not just the individual parts of speech tag, because these don't tell us if something is a verb phrase or a noun phrase. And this is the first step, yes, But remember to do the grammar rule. For instance, the NP plus followed by the VP, it has to be in that order. But how do we know what an NP is and what a VP is if all we have is the individual part of speech tag? So we need a way to not just extract the individual tags, but to extract the small phrases. For instance, your noun phrase or your verb phrase. So we need to code in with a regex formula, a regex pattern, what is a noun phrase or what is a verb. So we need to put that in a form that it can recognize these small phrases, and that's what we refer to as chunk extraction. So let us call our variable chunker, and it's equal to, we are using our regex parser and parsing that using our hard-coded set formulas, and just put 1, 2, 3. Let us define our NP. Actually, before I type it here, I included here NLTK chunking notes. It is a link that has some of the examples of your regex patterns that you need for chunking, and in this case the one we will be using would be the pattern to find a noun phrase. And there are some more examples if you want to read through, but it may be easiest for now to go through the lecture with me. So just so you know where I got the pattern from, it's a regex pattern, and it's fairly simple because it's a determinant that may or may not have an adjective followed by a noun, and this can simply be like, so the determinant can be a, and the noun can be burger, so we can have a burger, so we don't need to have the adjective. But if we were to have the adjective, we can put a large burger, and that is our regex pattern. And if we had an entire long problem, in our case it would be an entire long sentence, this formula would go into that entire sentence and extract only that phrase, which would give us the NP, the noun phrase. Okay, so the NP would be equal to, well, colon, sorry, and you put in curly brackets because curly brackets are used to identify a chunk. So we put in our curly brackets DT, which is our determinant, question mark, because we may or may not have an adjective, it's not necessary, and also it must be followed by our noun or nominal noun. So it can be a nominal noun, which was like our morning flight. So morning would be split separately from flight because it's two different nouns together. So you close it off with your brackets, and this is essentially, I will put this note here, so it will be to extract the noun phrase. And then we need to do the same thing for prepositions in the curly brackets, and the preposition will be IN, and how I got IN, it's the abbreviation. If you go to the same IB Watson resource, you'll see all of these notations there for you. And then what we are doing here is extracting the prepositions. The verb, it's the same pattern with the curly brackets and the arrows. Then you put V and multiply, close that off with the brackets, right? So here we extract verbs, and what else should we do? PP, which is to extract our prepositions, our preposition phrase. Copy that here, extracting preposition phrase. Curly brackets, and a preposition phrase, if you recall, starts with a preposition and it's followed by a noun phrase. That's the grammar rule. So we have our a preposition followed by our noun phrase. And last but not least, we have the verb phrase, and that follows the pattern of a verb associated with a noun phrase or a prepositional phrase and a noun phrase, so it can have either or. So let's put that in the regex pattern notation, and that would be first starting off with our verb, and then we can have our noun phrase and or. Don't necessarily have to have it, so we put pipe and prepositional phrase, so we may or may not have that, greater than sign and asterisk. Right, so this would be to copy and paste, extract our verb phrase. Right, and close off our function. The result we are looking for, we're taking our chunker, right? So let's chunker dot, and we are using the function dot parse and parsing in the whatever info we had here that this variable tags, whatever this variable stores, we want to pass that into this. So essentially, we have our text, and our text is being passed into, not parsed, but passed. So our text is being passed into the word tokenizer. So it's being split up into words. So the sentence is being split up into words, and then we are tagging it with our parse of speech tagging function. Then we have this output, but we need to take this output and pass it into the parsing function. And after it's parsed, then we need to put it into this pattern. So that's where the chunker dot parse comes into. So we take all of this and then we figure out the phrases. So from this, the result is supposed to tell us if something was a noun phrase or a verb phrase and so forth. So let's do our little print line, our parse notation, and put a colon and put a new line. You'll see why we're putting a new line, because it will get pretty jumbled. And what we are printing is actually the result. So we want to print the result. So print the result, and this is just a statement of text that we want to put before the result. So you can actually, if you don't want to confuse yourself, you can just put result here. And if we run it, we get the S, which is our start node, and each one now is broken up into not the parts of speech only, it's broken up into the mini phrases. And I'll just show you here my output that I wanted to put instead. And here the only difference is that we have a sentence here telling you what it is, so you don't have to put it. So here we have the parse notation telling you that the phrase, the noun phrase, is this. It's a shoemaker. So here we have the noun phrase being a shoemaker, so that it's A is the determinant and shoemaker is the noun. Then we have and, which is the same here with the conjunction, but here we have his, which is the preposition, NP with the wife, the other noun phrase, and which is only wife, which is one noun. And then we have the verb phrase, which is only one word. In this case, it's only a verb. The verb phrase is simple, it's just one word, one token. Then we have very, and then there's poor. So the only phrase we really got out of this one was the a shoemaker, which is a noun phrase. So we can actually try one more sentence. Let us do the example I gave you with actually this note here is actually supposed to be up here. Okay, right, because this is just telling you that this bracketed way is a way of representing a parse tree. So it's basically the same as a parse tree, but it's just in a different form. It's a bracketed notation. I obviously prefer the parse tree because it's so nice visually and easy to understand. Yeah, so these are your resources. Let's do one more example, and let's change this from a shoemaker and his wife were very poor, and we'll change the text to the boy ate the pancakes from the restaurant. So let's look at it quickly. We can see that there's some sort of prepositional phrase here, verb phrase, noun phrase, and so let's just run that. We don't need to do it manually. We understand the theory, so let's just let Python do the hard work for us. So remember to run each one again. Let's see what the notation gives us. Great, so the sentence node starts off at the top, and then we have the noun phrase, a verb phrase, and a prepositional phrase. So the prepositional phrase is from the restaurant, because from is the preposition, and the restaurant is the noun phrase with the determinant and the noun phrase. There's a function called .draw. If we want to output our results, which is the bracketed notation, we can do a result.draw. However, you'll get an error when you try this in Google Colab, because this function does not work on Google Colab. But I will run this for you using my Jupyter notebook, and it's the exact same code here like we have in our lecture. Nothing is different. It's using the Jupyter notebook. If you want to do the Jupyter notebook, there's the Jupyter installation lecture, section at the bottom of this course, at the end. So there's an optional software installation where we do the full setup and installs with Anaconda and everything to be able to run Jupyter Notebook and have Python run on your local machine. So you can do that option and do this parse tree, or you can just take a look at it here with me. So this notation here, if you were to run result.draw in a Jupyter Notebook, you see here's the same output. We have the same output with S and the bracketed notation for the boy ate the pancakes from the restaurant. The only difference is that on Jupyter Notebook, when you run the cell output.draw, it automatically pops up this window and you get the diagram. So this is the same thing that you would have to draw if you were to structure out that sentence. So here we have the noun phrase. It's really nice when you work it through here instead of looking at the bracketed output, because it's nicer to follow. So from our sentence node, we break up the boy into our noun phrase, and then that further breaks down into the determinant and the noun phrase. Then the verb phrase breaks down into ate, which was the verb alone, and then it also breaks down the pancakes determinant and a plural noun, so it's NNS. Then we break down the last part, which is the prepositional phrase, and it grouped it correctly from the restaurant, so it's the IN, DT, and NN. So that's essentially how we do a parse tree extraction, how we draw a parse tree or create a parse tree from your text. And in the future, when we start doing more complicated algorithms and modeling, most of the time you do all these NLP processes like parse trees and stuff in one line of code, and you would have no idea that you did all of this, but in the background this is what is happening. So a lot of times you might just do simply put a dot tokenize or dot tag or regex parser dot or something with your chunking. You just have like one line, and you're actually not going to realize that all of this the algorithm is doing in the background, so that he or she can understand the syntax rules to make sure that it's grammatically correct or not. So I hope you had fun, and I will see you in the next class. Welcome to another lecture where we look at stemming. Stemming will be used throughout in all your NLP projects. It involves the theory parts on morphology, and then later on in the chapter we will jump into our Python where we practice stemming methods, and you see how it can be used in things like information retrieval. Now, morphology. What is English morphology, and why does it even matter in stemming? I mean, this is an NLP data science course and you're wondering what's with all this theory, but it's very important, and so just bear with me. So, morphology is the study of how things are put together, right? It can be when we look at the makeup of plants and animals, and with linguistics, it's the study of the structure of words. And it's the way words are built up from these small units, and these small units we refer to as morphemes. Keep in mind that morphemes must bear meaning, so it has to make some sort of sense. It's not just simply cutting up words into smaller pieces. So the morpheme is generally, I said morphine, the morpheme is generally, it is the smallest unit that you can have a word exist in, that where we still retain some sort of meaning. And we usually have two classes of morphemes, which is a stem and the affix. And you see where we come with the stems here, and later on you will see where we get into stemming. So a basic example, the word dogs has two morphemes. First morpheme, dog, and the second morpheme, s. So put them together and it changes the meaning from putting this together with the s, it changes this one doggy into plural, where we can have the meaning more than one dog. An example of a word that is equivalent of one morpheme would be the word fox. So fox is made up of one morpheme, and foxes is made up of two morphemes. So let's take a look at affixes quickly. I'm pretty sure everyone knows what an affix is. We may not have known that the definition of affix, but it's broken down into these four elements. The first element or type of affix would be a prefix, then the suffix, infix, and circumfix. Prefixes, very basic. It's the beginning of the stem. The suffix is the last part of the stem, is attached to the last part of the stem. The stem, keep in mind that the stem is the main morpheme of the word, and it supplies the main meaning, right? And the main meaning here is kind, and our prefix is unkind. So suffix and then also the infix. The original word it comes from cupful. So a cupful of something, a cupful of sugar, a cupful of flour. And if we want to change the meaning of it slightly and we have a cups full, then that S here is the infix because it's in the middle of our word, of our stem. The circumfix has a combination of an attachment at the beginning and an attachment at the ending. So this is our stem, light, with the two attachments on either side of the stem. Some examples of stems and affixes. Just keep in mind that when we remove the affix, we're left with a stem, and the stem has to provide some level of meaning. This will come in more, you'll see the importance of this when we start using stemming in our algorithm. Because the reason I'm mentioning it here is that you'll see with some methods with Python, you can overstem the cutting of the word to the point where it doesn't really have much meaning and it's not useful. So generally, stemming is the stripping off of these affixes. And like before when we looked at the prefix, just keep in mind that prefixes can make the stem become an opposite meaning, so that if our stem was usual, adding on means opposite, and D makes it mean opposite as well. So what is usual becomes unusual. So what is normal became abnormal. If we wanted to activate something as opposed to deactivate the system, then we also have prefixes that can alter the meaning differently to a stem, not just the opposite. So here we have heterosexual, where hetero means different, and homosexual, homo means the same. So in this case, we refer to the same gender, and in this one, we refer to different gender. In the next video, we will actually see the use of stemming using Python in Google Colab. So go ahead and open up this file in Google Colab and join me in the next video. Now in this video, we will move along into a practical using NLTK. So first thing is to open your stemming_lemma.ipynb file, and let's go straight into Google Colab and start playing with this notebook. So now that your Google Colab stemming_lemma notebook is open, we'll be using NLTK today, and our stemming methods that we're going to be looking at will be using these modules: Porter stemmer, Lancaster stemmer, and Snowball. We'll compare how each one works, and then we see the result of the type of stems that we get. Just to remember that what we're going to be doing is stripping the affixes from the token and retaining the stem. And before, when we mentioned tokenization, remember that the token, that string, is the token that is going to be stemmed. So before, we took sentences and paragraphs and we broke them up into smaller tokens, and now we've taken a step further in our pre-processing of our data to strip off these affixes from these tokens. And let's see what we mean. First thing, let's just get a block of code in, and we'll be importing. It's a comment, so remember to put your hashtag. We're importing the NLTK package. So it's just straight import NLTK. Run that. Now, the first one we're going to be looking at would be the Porter stemmer algorithm. And the Porter stemmer algorithm is an algorithm for suffix stripping. And it is one of the most widely used stemming algorithms because it's very easy to use and it's very efficient. But there is an issue with it because you'll see later on what happens. But for now, let's just play with it a bit and then we'll get to that part. So how it works is that the foundation of the Porter stemmer algorithm is that it uses a series of rules. And what it does is that it's like a cascade and it's based on a series of simple cascaded rewrite rules. And take a look at some of the some examples of these rules. If you look at the ending, which is a suffix of a word, when you have a word with this suffix, with ational, which was something you may see in rational or national, so the suffix is ational, so we will consider this to be shortened and stripped down to just ate. So an example here is relational, and you'll get relate because we stripped off the ational. Another rule you can take another very common rule would be ing. Anything ending with ing, like falling, would result with fall, and motoring would result in motor. Another rule where you have a double S followed by es, which is a plural. In this case, grasses, you will get the suffix being stripped off, which is the affix, to become grass. It's very simple, and it's a gentle algorithm, meaning that it doesn't overstem, so you're not going to end up with, I'll show you what overstemming means later on, but for now, just keep in mind that it's a gentle algorithm. However, it's not ideal for precision, so let's just do some examples right now. So we're importing our class. So it'll be from NLTK dot stem import porter stemmer, and we're going to assign something shorter. We'll assign porter to our porter stemmer module, and brackets. Let's do an example of how porter stemmer works. Very simply, we print porter dot stem, and let's put our word here. Let's put bundle. Dot stem, another set of parentheses, our word bundle, and remember to close these off. Let's just run that. You see it's shortened from bundle to bundle without the E. And if we were to make this plural, you will get the same thing. So it reduced it to the stem. It's not the word bundle we know with the E, but the stem of it, it's bundle. So for another example, let's just Control C and Control V. Substitute this word with another example. It's jumping, and remember before here we said one of the rules is with ing, it will just simply remove that suffix, and we'll just be left with jump. And moving along with just one more. Let's substitute this with the word illustrator. Now, long ago, we didn't have the program, the Adobe Program Illustrator. So this would have merely just meant Illustrator. So what happens here is that it reduces it down to the root stem of the word illustrate. But in modern day times, there is quite often you'll find text where this is actually a proper noun that refers to our program Illustrator, which you would not actually want to reduce down to this. So this is something that we will address in chapters later on. I will remind you of this, so just keep this in mind. Now let's move on to the second stemmer, which is the Lancaster model. And now this is a word stemmer based on the Lancaster stemming algorithm. The difference compared to the Porter stemmer is that the Lancaster stemmer, it's an iterative algorithm. Now it uses rules, and yes, Porter stemmer uses rules as well, but it's different now because of the iterative factor. There are about 120 rules based on that the Lancaster module is based on, and these are indexed by the last letter of a suffix, and with each iteration, it tries to find the relevant, the applicable rule by the last character of whatever word it is. So if you had the word eatery, that's E-A-T, is the stem of it, which is the word eat. Now one of the rules here is that if a word starts with a vowel, and there are only two other letters left, that would be where it stops iterating. But if these rules aren't met, it will continue repeating the iteration until it finds one of the rules that will allow it to stop the, so it's very aggressive because of this iterative factor. And because of this, in some cases, you can get a bit low precision. And we'll compare the results from Lancaster to Porter stemmer and Snowball very shortly. So let's just get into it and see some examples. I'm going to print, just as we did before. I'm sorry. We have to do our import. So from NLTK dot stem import Lancaster stemmer, and then we'll just assign Lancaster to the Lancaster stemmer module, and let's just run that and create a new cell right below. And let's do some of our examples. So we're going to print using Lancaster stem, open up our parentheses, and in quotes put our example. In this case we will do organization. Run that, and it shortens it to org, right? And let's go up to our Porter stemma to just do a comparison. I'll just copy this, so it's porter.stem. We're going to do a new line right here and change Illustrator to organization. I'll just make it the same, and I'll put this in a common overview, and we got organ. So you see how it was more aggressive and it shortened it to org. Let's just do one more example of the Lancaster stem, and let's just take a word. What about the word bunny? Bunnies. It actually didn't just shorten it, so it didn't simply just take the affix and drop it off with the es plural and left it at bunny. It actually changed the affix and added the y for singular for bunny. That's the difference with Lancaster to Porter, that just strips off the suffix without ever altering the word itself. Okay, so let's jump into the third example, which is Snowball. And Snowball was actually made by the same guy who created the Porter stemma, and indeed it's a modified version of the Porter stemma. You will see a lot of similarities in the way they shorten words into the root stem, and they are very precise in large data sets. And because right now we're using examples of individual words or short data sets, you may not see a big difference between Snowball and Porter stemma, but just keep in mind that for larger data sets, you'll find more precision. Just add a little bit of code here, and let's just copy this from NLTK.stem. And what we're going to do is just remember to change the Lancaster stemma module into our Snowball stemma, and we're going to make snow equal to our Snowball stemma module. But there's a slight difference here with Snowball, which is a good advantage for it. You can choose your language, and there are some really good examples that you can use if you're fluent or your native language is not English. Or you're fluent in a good second language, in French, German, Hindi, Spanish. So you can, I'll provide in the slide after this, I will provide a slide right after this lesson with a link where you can experiment using Snowball stemma, but for other languages, for Arabic and all those sorts. So you can have some fun with it after we do the English example. So let us run this and then create our new cell right under, and just as we did before, we're going to print some examples using snow stemma, and we can use the same organization. And to make it faster this time, I will just do all in one here for you. We don't want organization, so let's change this to digitize. Third example, favorable, and this one would be limitation. So just remember to copy and paste accurately and run that. So we got organization being shortened to organ, digit, favor, and join me in the following video where we just do a summary to compare these three methods. Continuing from our last video where we looked at stemming methods with NLTK, we looked at three different methods: Snowball, Porter stemma, and Lancaster. So to sum up, this video will just be creating a table where we have 4 columns with the 3 stemmers, and we get to compare the results. So let's continue quickly with that. And so put your hashtag for a comment, just to explain what we're doing. We're creating a list of words, and from that list we will be comparing the 3 stemming methods. Let's create our word list here. Let's name that bundle. So the word list name is bundle with square brackets, and each word will be in quotations. So our first word, we're going to do 10 altogether. So the first word is bunnies, second, organization, third, polarize, fourth, jaguar, quotes right there. Okay, close this one time. Stabilize, destabilize, democratic, and the last 3, what about kingdoms, dramatic. You can use other words after to see what other results you get. Dramatic. And last one, favorable. And you can choose whatever spelling you prefer for favorable. This is the English version with a U, and the American is without the U, and they're both correct. Close up with those square brackets. And right, so we want to print our format in the structure of columns. So I'll show you how to do that. It's very simple. So in quotes, we put our padding. This is the spacing that we'll put between column to column. So for the first column in curly brackets, we put our first column, which will start at 0 for that tuple, and that will go at 20 for our padding. That should be sufficient. I'll show you what happens when we change that padding. So for now, let's go at 20. 1, 2, 3. So paste that out into 4 different ones and change this to 1, 2, and 3. What that is that this is the first column, second, third, fourth, starting with number 0. So don't get confused with that, because the normal way you iterate would be 1, 2, 3, 4, but we always start our rows with 0 when dealing with arrays and data frames. And remembering that what we want to do now is format this in the form of columns. So remember, we want to format this, and how we are doing that is that the first column we're naming the first column would be our word in our bundle, and after that we'll call our next column. The first column would be Porter, which will be for the Porter stemming method, and the second, of course, was the Lancaster method, and thirdly was the snowball. Right, and that should be it for the formatting for the columns themselves. Okay, and we just need to do one more bit, which is a for loop, where we have for word in our list, unnamed bundle, we want to print out the actual results when we feed that word into the stemmer for each time. So what we're doing here is exactly that, printing out the actual results, because before, we printed out the column names, and now we need to put stuff in that column. So in our curly brackets, we will paste the same thing from here. So instead of retyping it, let's just copy that and remove that and paste it in. Make sure the quotations, everything lines up right. And we format it again. But this time, the word that we're feeding in from here, okay, would be in the first column, and then the other columns will be the results from when we run the port stem through it for that particular word, and then we just repeat it for the other stems. So I'll just copy this twice. 1, 2. And this one will be our Lancaster. Last one, snow. Okay, that should be it. And just clean this up a bit. Make sure your brackets and everything is balanced. So we have an issue here. I'm sorry. This is porter, not port. I do love the port wine. It's Portuguese wine. It's amazing for those of you who are who are into wines. You can give it a shot, and if you are into wines, I'm pretty sure you're a fan of port wine as well. Anyway, moving along, yep, so that was corrected, and let's safely run that. Great, this is exactly what we want, and let's take a look here. We have, before we get into the results of the stemmer, if you're new to Python and stuff, let me just show you the difference with the padding for each tuple. So that would be, if we change this to only 10, let me show you what's going to happen. What do you think is going to happen? You see what I mean? The space is not big enough, and it's just, it's too jumbled, so we need more space. So let's bump up our padding again to 20. You didn't need to do that just now. I was just showing you what it is we've just done, in case you're unfamiliar with the formatting method. So now moving along to the actual stemming results of it. We did some of these earlier, but it's nice to look at it side by side, and plus you got to learn a bit about formatting a bit again. It's always good to practice your Python. So these are the words we chose, right, from our list called bundle. And for the porter stem, you notice for bunnies, it removed the plural with es, and very similarly snowball. Remember, snowball and porter stem was designed by the same guy. They're very similar, as in snowball was built as a modification of porter stem, and you'll start seeing the difference mainly when you use larger data sets. So right now, like I said, we wouldn't see a big difference with snowball and porter stem, but just keep in mind, snowball for larger data sets is has more precision. So note one thing here with Lancaster's method with bunny. You notice it actually changed the word. It didn't just only slice off that affix, because for porter stem you're accustomed to just dropping off and slicing off that affix to give you your root stem, but Lancaster not only removes the affix, but in this case it takes off the suffix and actually changes the word back into the singular form bunny, which is not what you may always want, but it's just one of the differences with Lancaster and porter stem, how it actually changes the word. Porter stem never does, because it just slices off the suffix and that's it. It just cuts it off. And now for our word organization, this is a good example now to show you the difference in porter stem and Lancaster and even snowball. They both dropped it down to the root word of organ. And remember I said Lancaster is more aggressive, so it iterated again. From first iteration, Lancaster would have given you organ, but then it iterated again and realized, oh wait, we can get even smaller, and in this case you were left with one vowel followed by two more characters, which signals your Lancaster iteration to stop. And that can be an example of when you can over-iterate until you meet the Lancaster's set rules that we mentioned before. Again, same thing happened here with polarize. You got polar, and POL, pole. But if you're summarizing this and you tokenize your sentence and polarize was one of your tokens. Now polar would make sense linguistically, but pole doesn't. So you can see why you have to be a bit careful when you're choosing to use the Lancaster method, and why porter stem is usually more popular than Lancaster for the precision. And again with Jaguar, porter stem and snowball just left it as it is. It didn't slice off any other suffixes. But Lancaster changed it to Jagu, again, which would not make as much language sense to when you're doing your stemming. And again, you see destabilize and democratic with the same problem. Actually, look at stabilize. With stabilize, we have stable and stable, the same thing, but stable. Now, when you think about it with this way, the word stable, S-T-A-B-L-E, you would actually think that this was short from stable, S-T-A-B-L-E. And with stabilize, it's actually different a bit. So you see the aggressive stemming with Lancaster, and it's a bit more obvious with the destabilized one. Destable would still make sense and be recognizable, but dest, as a root stem, it's too vague because that can be destination. So this is an example of the overstemming that Lancaster is famous for. Again, with Democrats, overstemming here. This one did a pretty good job. Kingdom was the same for all because it was a plural, and we got rid of that suffix, and we're just left with the root word kingdom, which is fine for all three. Same overstemming here with dramatic and favorable. Again, they were both fine with the root words, but Lancaster showed the overstemming. So that's it for our NLTK and our introduction to using Python with stemming. So join me in our next lecture where we start to look a bit into lemmatization. In the previous lecture, we were looking at stemming, and now we progress from stemming into lemmatization because there's some overlap with the two. So lemmatization is part of lexical semantics, which is a big theory topic area in NLP. And exactly what is lemmatization? What it is that, now, for this entire lecture, we're going to look at some different points, and understanding lemmatization is the first part. And a lemma is the grammatical form that is used to represent the smallest part of, the smallest minimal unit of a lexicon in a language that has some sort of meaning. It's very simple. Rocket, for instance, is the lemma for rockets. And you remember from stemming, we can say that if we were to strip off a suffix, the affix for rockets, it would give us rockets, or even further, rock maybe. And you see some similarities there with lemmatization and stemming. So now that process of mapping the word form, which is rockets, to the lemma, which is rocket, that is lemmatization. Now let me just jump ahead to the other slide to show you something. What is the difference between lemmatization and stemming? How are they even different? Now, they overlap because both of them have the same aim, right? And that aim is to reduce the inflections of each word into a root. And what exactly is an inflection? In linguistics, and throughout NLP, a lot of it is based on this, but in linguistics, an inflection refers to the change in the form of a word to mark distinctions. So what this means in simple terms is that, so if the root word was study, and then we add a tense to it so that it is studied. Studied becomes the past tense, and if we want to lemmatize studied, you will bring that down and cut it off and reduce it to that small lemma of the root word, which is study. And I'll show you some more examples of this in the next slide. When we remember what we learned in the Porter stemmer, right? So stemming in general, you would remember that with the Porter stemmer, let me just recap on this for you. So with the Porter stemmer, typical of stemming, we relied on these cascaded rules. So when you have certain suffix with this, we change it or we reduce it to only this part. So if you remember that, it's based on rules, but in a case where the word was bundles, we remove it based on the rule where we remove the ES and we got bundle. And the same thing for bunnies, we remove the plural ES and we get bunny. But the correct thing, if you were to look at it in a dictionary, you will never find in an English dictionary this, you'll find BUNNY. In this case, it was correct because ing leaves the correct root word jump. And there you see the difference now. If you want to be grammatically correct, which is very important in certain types of searches and uses on NLP, you will understand why we need the lexicon to really tell us what this word is. So let's go back. And so basically, a portostemma, stemming, for instance, is based on an input-output lexicon-free stemma. That's why it's so fast to use, because you don't have to, it just has an input. Like in this case, the word bunnies would be the input. Quickly apply whatever relevant rule. In this case, it's the suffix es, and it just gives us an output bunny. And let me show you the difference. So just remember that stemming, for instance, portostemma, is a lexicon-free input-output stemma. And if we were to now look at more examples, see the difference in stemming and lemmatization, we just did the example for bunnies, but same thing for spies. In stemming, we would remove only the es with the rules and output spy, which is grammatically not correct because it's not in the dictionary. And a lexicon basically is your vocabulary that you use, your dictionary. So if you are Danish, you would use a Danish lexicon, which is different to English and Spanish. And then if you are using English, British English, that's actually different to chat English. So your chatting language. So that would require another lexicon that includes slang as well as standard English. So we'll get into more practice with lexicons as we go on. So another example here with niñas, with stemming, it removes the as and it leaves you with nen, which again in Spanish would not be grammatically correct. And lemmatization, what it does instead, like I said, it considers the morphological analysis of the word. What this means is that if we have our word examples, spies and niñas, the morphological information is looked up. It's referred to in this large lexicon, this large dictionary, and we're able now to pull out the morphological information and provide a morphological analysis. So in this case, the word spies and niñas. Let's look at spies. It is the plural number because it's more than one spy, and it is in the present tense of a verb to spy. So it's like, it's present day, it's happening now, like he spies, or like spying. And the niñas, the word niñas, it's the feminine plural, but it stems from the root word in Spanish, niño. And in this case, it's very incorrect because niñas is output nin, when the correct lemma, the grammatical lexical word, is niño. So this makes grammatical sense. It's grammatically correct. And a lemma differentiates from a stem because the stem does not always end up being grammatically correct or something that you'll find in a lexicon or dictionary. And a lemma must always be belonging to a dictionary. So it would make a lot more sense and give better results depending on certain NLP models that we'll be looking at. So just to go back to this first slide where I was just showing you what we're doing today, the meaning itself of lemma. Now, remember I just said that it must have some meaning bearing in the word when it's reduced to a lemma. Now, this reflects to something called word sense. A word sense relates to the meaning of that lemma. Now take this example. We would have the lemma, bank, and we can have the extended word with a suffix being banker or banks, and then we would reduce that bankers or banks to its lemma, which would be purely bank. But if I use this in a sentence, I can be talking about a riverbank or a bank where I have my bank account, my money. And this means that the word itself, bank, has two senses. And you may think this is sort of pointless, but in NLP, if your computer is reading a sentence, you and I can figure out the context of the word bank. If I said I went fishing along the riverbank, but how would your NLP algorithm be able to determine the difference and the meaning of that word bank? So that's why it's important to appreciate these theories right now. Then later on we'll get into a little bit of word nets, and this is just a database of lexical relations, and you'll understand it a little better when we start using it. For now I just want you to be familiar with it. And the most commonly used resource for the English sense relations, and WordNet sort of is made up of like 4 subsets where we have nouns, adjectives, verbs, and adverbs. So now that we have a good idea on what lemmatization is and how it's similar and different to stemming, let's jump into our practical right now and head over to Google Colab and open up this Google Colab notebook and join me in the practical in our next video. Welcome again to another lecture. We just finished the intro to lemmatization, and I do hope that you've opened up your lemmatization.ipynb notebook, and I'm going to jump straight into it right now, where we start using the NLTK library to demonstrate how lemmatization works. So as usual, let's just import our NLTK package, our NLTK library, and from nltk.stem import WordNet lemmatizer. And what we need to do as well we need to actually download our WordNet. So it's nltk.download WordNet. And before we go any further, let's just run that. And she's downloading package WordNet, and now it's already ready to use. And if you remember in our last lecture, I said that WordNet is actually it's a lexicon with nouns, verbs, and whatnot. So your lemmatizer is able to get that morphological information from the WordNet. So let me just give you an example of how a WordNet actually looks, basically like a dictionary. If you forward to the other lecture, I provided a resource for you. So you can just click here and it will lead you to this website. If you don't want to go over to the next lecture, you can just remember this website here, but it's easier if you just click to this resource. Right, now that you've opened it up, let's just play with our WordNet. It's an online WordNet, and if you enter a word like we had before, spies in our example, search WordNet, we get our results. So it tells you that the semantic relations of this word, when we reduce the suffix, we don't just get SPI, it actually corrects it and matches this word with the base lemma, which is spy, and it tells us that it has different forms. It has a noun, another noun, and also it can be used in the term of a verb, where you can spy on someone. But in this case, I am a spy, or my spy told me some information. So in those cases, it's a noun. Now you're wondering, okay, this is all well and good. And remember we said before that the difference with the stemmer and the lemmatization is that the stemmer just matches some rules, and the lemmatization actually goes into this large WordNet and is able to figure out exactly the word that it's coming. So you may wonder, how is this actually useful? Now think of it in a case where we go to our Porter stemmer, and for instance, if you were using an e-commerce website, and that e-commerce website has their search based on a Porter stemmer method. So when you enter in that search bar, if you were to enter that you wanted to buy stockings, okay, this is what happens. The stem actually breaks it down and chops off this suffix and leaves you with the word stock. So when you go to enter stockings on that e-commerce website, the program in the background, the algorithm, would not know the difference between the stockings you want and stock, and that may give you chicken stock or beef stock, soup stock. It also doesn't differentiate stock from stocks in the trade industry. So what is going to happen if you use a harsh or an incorrect stemming method as opposed to lemmatization? When you search, you're going to get search results that are going to be giving you stockings for clothing items and chicken and soup stock. So how do we stop this from happening? Now, if we go to our lemmatization, I'll show you an example. So now that we've loaded up our WordNet and do our imports, we need to create an object, and that object, let's name that object lem. And what we're doing with this object is that it is an object of the word lemmatizer class. So the word lemmatizer class, right, is now being used with our object. So this is an object of the WordNet lemmatizer class. So this is equal to, let me just copy WordNet lemmatizer class, and let's just give an example of the token. Let's just name it token because it's a token that we want to break down into its root form, our lemma. So the token that we want to break down would be spies, and then we would now equate lemma that we want. This is the lemma that we want, right? The lemma that we want from this. The lemma is equal to lem, which is our object, dot lemmatize token. And we just want to print that result. So we want to print this token here, okay? I'm just going to put a little, graphic here for you. And that looks a bit off. I'll put equal sign, much better, and comma, because this is separate. This is just some little graphic here for you, and lemma. Right, so we're going to print out spies and whatever the result is, okay? So this is a bit confusing. So let me put result lemma so it's less confusing. Okay, run it. Okay, so we get our lemma, which is spy. And for instance, what I just spoke about with stockings, okay, if we were to see this example, stockings correctly only remove the plural, which is S, and you leave our noun as it is, stocking. So if I were to search on my e-commerce website, I would only, and I entered stockings, it would be interpreted by the lemmatizer that it's stocking is the root word, and look up only stockings for me, as opposed to giving me soup and, soup and stockings, which is a bit ridiculous. So that's a way for you to understand the importance of lemmatization and of having a WordNet so that your lemmatizer actually uses the WordNet and figures out, like if we go to do it manually, stockings, manually we get the same result that we did with our algorithm, which is great because we get that it's a noun, it came from this root word, and it did not give us stock, which was the incorrect stemming method. So just to recap what happened here, in case you're not familiar with Python, just to teach you a bit more of what goes on here, is that the word that we need to be lemmatized is actually passed to the lemmatize method of the WordNet lemmatizer object, which is lem. Join me in the next video where we continue directly where we leave off from this notebook. So leave this lemmatization.ipynb notebook open and let's go straight into using some other NLP libraries for lemmatization that include spaCy and TextBlob. Hi, welcome to another lecture. We just started out some lemmatization in our previous video. If you're now starting up this notebook again, remember to open your Google Colab lemmatization.ipynb. We had just lemmatized single words, and for this video we will be lemmatizing an entire sentence, well, a few of them. So if you scroll down to this yellow heading, lemmatize an entire sentence, this is where we will be working for this video. I have already provided you with two strings. The first one has two sentences, the second has two sentences as well. The first is the girls sang louder. The bankers banked at other banks. These were better shoes for her feet. The grocer was stocking the shelves at the grocery. So before we get into lemmatization, let's first do a recap and go to tokenization. If you recall tokenization, we would first break up this entire sentence, well, the entire string here, into individual tokens. So we're going to do that first. So this is normally how you would do it in NLP. We tokenize and lemmatize. So this is some good practice for it. As usual, we import NLT key, and from NLT key dot tokenize, we import word tokenize, if you remember doing that before, and we do NLT key dot download punct. Right, so run that for it. It's right, you downloaded your package, and we continue along to do our tokenization. So remember, we have string number one. We're only looking at string number one. So our tokens, which will be our objects, nltk.word tokenize. We want to tokenize string 1, and the output that we want would be print word tokenize, and let's just temporarily see what that gives us. So we got it split up into tokens. The girl sang louder, the period is also not attached to louder. There we go. I wouldn't spend too long on this because we already got a lot of practice with tokenization before. And actually, let's continue along right here so we wouldn't split it up. I just want to put an extra line here. Let's just print an extra line. It's just an introductory title, so it's the tokenized sentence. So it's just a header telling us what we're getting here. Right? Close that off because I want to continue. So now we lemmatize the tokenized sentences or object. Let's call our object lemmatized tokens equal to quote space dot join lem dot lemmatize w for w in tokens. In the same way, we have a nice introductory header. Let's copy this, print, paste it, and this is to give us our lemmatized sentence. And what it's actually pointing toward will be printing lemmatized tokens. Okay, so if you understand what's going on here is that the object that we're passing through to the lemmatized method would be also joining the fact that we split up each token before. So we're joining that now and passing that into lemmatized for W in tokens. Tokens meaning the already tokenized sentence. So we're no longer lemmatizing this entire string. We're actually lemmatizing the tokenized string. Okay, so let's output that. Okay, nice. We have our tokenized sentence labeled "the girls sang louder, the bankers banked at other banks." Keep in mind that this is the tokenized sentence, and this here shows the lemmatized sentence. Lemmatized sentence on this here, you notice we're joined again. So here you're looking at individual tokens, and here we were able to join them up together to get back two sentences with dot join. So we got girls was lemmatized to girl, and banks was lemmatized to bank. Okay. However, I just want to show you one thing so we can appreciate the use of tokenization. Without the tokenization, just look at what happens. We are lemmatizing the output from the tokenization here, but let's change this from tokens to string 1 and run that again. Notice this time girls did not lemmatize, it was left at plural. Banks also did not lemmatize, it remained the same from before. So this shows you the accuracy is much better if we use the tokenized info to do our lemmatization on. So let's just return this to tokens, get our desired output. Now we have a bit of a problem here. Problem being that our lemmatized output is not as precise as we thought it would have been. Now we lemmatized the word bank, for instance, or banks to bank. Yeah, so it removed the S, and that's correct. But if we look a bit closer to some of the other words that would lemmatize, it's not precise. So join me in the other video where I explain what the problem is. This video is a direct continuation from our previous video, so please open the same lemmatization notebook in Google Colab, and let's continue from where we left off after lemmatization of the sentences, and I will continue to explain now what exactly was the problem with the precision for the output that was produced. Because if you look at bank, banked, and banker, now this was correct in the sense that banks was correctly lemmatized to bank, which is its smallest lemma. Well, it's lemma, but when you look a bit further now, it's not as good as we would like. We actually need a better quality and precision for our output. For instance, sang. If you don't trust me, let's take a look at our WordNet. If we want to look at the word sang to get our lemma, and we're using here our lexicon, our WordNet lexicon, sang gives us, it tells us here that it's a verb, and the word it comes from is sing. So it comes from the word to sing. So the actual lemma for sang is not sang, it's actually sing. So this was not precise. The lemmatization actually has, some issues here. Later on, we'll improve on this as we go along. And in this instance here, I have some notes here so you can remember when you review your notebook. Banker is a noun, banked is a verb, and banks is also a noun. Now it correctly removed the suffix, so it was we were left with our lemma, noun. Well, we were left with the correct lemma, bank. However, with banked, which was a verb, it left us with the same thing, banked. But let's take a look again. With the verb banked, now here's an entire list of the semantic relations, and the verb banked gives us a root lemma named bank. Okay, but if we were to look at banker, which is a noun, it's so similar because the suffix, this affix, is basically the same two-letter addition to the same root word. And remember earlier when we spoke about word senses, and some words have more than one word sense? Bank was one of those examples with more than one word sense. And even further now, when we look into parts of speech, a part of speech where we have a difference between a noun and a verb, they give rise to a different lemma because they actually come from a different meaning. So, let me just repeat in case I lost you. Banked, I banked on something. That means that I banked on something. Let's search that word net. Bank is a verb with its lemma being bank, but with the same suffix, banker, which is a noun, gives us banker as in its entirety as our root lemma. And let's just quickly look at banks. Banks can be two things. Look at it here. Banks can actually be the plural of bank, which is a noun, or it can be a common name. It can be someone's name, or it can be a verb. So it can be banks as in the pilot had to bank the aircraft, and then we say the pilot banks the aircraft. And so in that case, banks can be treated as a noun and lemmatized to bank. And as well as if it's a verb, it will also be lemmatized as bank. So let's just return to this. And I'm sorry if I'm confusing you there, but for instance, again, the girls sang louder. The girls sang louder. Correctly lemmatize the plural of girls from girls to girl, as girl as the root word, but sang, what is the root word of sang? The lemma of sang. Now if we were to use Porter Stemmer, or even Lancaster Library, it would give us the shortest cutoff. When we keep slicing off anything, we would get sang as sang. And the same thing for lemmatization, where sang gives us an output. It's supposed to give us an output of sing, okay? Because if you correctly go through a word net and you know that we mean this as a verb, the word net would have known, okay, yeah, we're talking about sang, the verb, and yeah, the lemmatizer would know that this was supposed to be sing. So now as a human, we know that sang is a verb, and because of that, we're able to correctly identify and lemmatize ourselves, lemmatize sang to sing. And that same order, we can lemmatize banker as banker and banked as bank. Now, how would we get the algorithm to do a more precise output upon lemmatization? Before we get to that, I just want to do one more example. So I'm going to copy this entire thing, okay, and just paste it in here. And the difference we're going to do is that we're going to tokenize string 2 just to see another demonstration, and we will call this tokens 2. So we're going to print tokens 2 and lematize and join tokens 2. Change this as well to lemmatized tokens 2 as well as here. Okay, got that? Just run that nicely. Really nice output. And okay, great. So our sentence was, these were better shoes for her feet. This is great. Look, we lemmatized it correctly to foot, because feet comes from the stem but from the stem root, the root of foot. But if we were just doing a stemmer, the stemmer would have just left this alone, right? And now this is an issue here. You would think this is correct, okay? We would be like, okay, great. We changed shoes, lemmatized it to shoe. We dropped off that affix, that plural affix, and we changed feet to foot, which is great. And also, look at the grocer was stocking the shelf at the grocery. Let's look at one sentence at a time. What's the problem here? The problem is that when you lemmatized this verb, you're actually not supposed to get were. Let me show you some evidence of what I'm saying in case you don't believe me. When we look at what the root of were is, we get be. This comes from to be. If we were to conjugate in the English language, the verb to be is actually the root for were. So if we were to correctly lemmatize this, were would be lemmatized to be, okay? And let me just put this correct sentence, what it was supposed to be for you. It would be, these be better shoe for her foot. Okay, so that's what it's supposed to be. So we need this more precise output that can only be given if the algorithm knew that were was actually a verb. Continuing, let's look at this second sentence. The grocer was stocking the shelves at the grocery. You notice this stocking is different to our stockings. Stockings here was a piece of clothing. It's an item. It's a noun. So it was lemmatized correctly to stocking, which is a singular version of the plural noun. However, when you look at the verb stocking, the verb is very different because it comes from the root word stock, to stock something. Again, let's just look over here. Stocking. We have two differences here. We have the noun and we have the verb. The noun was what we did initially with the clothing if we wanted to shop online, and we had a difference with the soups and the clothing. Now there's another differentiation with a verb, to stock, to carry something, or to pack a shelf and to stock the shelves. And how would we know the difference? So in this case, it was an inaccurate lemmatization because this was supposed to be lemmatized to stock. So the correct thing here would have been the grocer be stock the shelf at the grocery. So you notice as well, was and were, like I have a note for you here, was and were supposed to be lemmatized to be. Are is also supposed to be lemmatized to be. And yeah, so, and stocking here, verb and noun, That's where we differentiated. So the verb was supposed to be lemmatized to stock and the noun was supposed to be stocking to maintain the accurate grammatic meaning of the word. Okay, so we don't want to get an incorrect meaning, because then what are we doing this for? We want to get a good, accurate meaning. So the algorithm has to take in consideration the part of speech, meaning is it a noun, or verb, an adverb, an adjective? So there are things we can do to add a second argument to this lemmatized function, and that new argument will include something called parts of speech, which will be telling our algorithm that, okay, you know what, foot is a noun, were is a verb. That is called parts of speech tagging. So I will show you how to use our parts of speech arguments within our algorithm for lemmatization. And we will not only do it for NLTK, but we will do some lemmatization using spaCy, TextBlob, Pattern, and the Stanford CoreNLP, all using tokenization, putting it together with lemmatization and parts of speech. So let's move forward on to our next chapter, where we start piecing things together a bit more nicely. I hope you enjoyed what we've been covering so far, and rest assured we will get to the fun NLP projects very soon. I know you can't wait to get to that. I know this is not the most exciting part of NLP, but just be patient and then we will get into those very fun projects. Thank you. Welcome to this new section where we get a little more detailed into cleaning text data. So this section is focused particularly on cleaning tweets. Now I know that in the past few lectures we've done some work on preprocessing with regard to tokenization, stemming, and lemmatization, which is important to understand the linguistics and semantics behind it. But even though we did a few practicals with Colab notebooks, that's not how the cleaning and data would be in the real world. So from this section, we will start to get a bit more hands-on experience with being able to look at dirty data and figure out how to clean them. There's a particular reason I started off with tweets. One of the main differences with the text content with tweets is the hashtag. And we all know that life would not be the same without Twitter, and it's difficult to even picture life without it anymore. And there's this quote that I stumbled upon for you guys. It's from this writer. She's a screenwriter called Shonda Rhimes. She wrote some very popular American Netflix shows, Grey's Anatomy and Scandal, and a few others, I think How to Get Away with Murder, and that's besides the point. The point is that she made a quote that said, a hashtag is not helping. A hashtag is not a movement. A hashtag does not make you Dr. King. A hashtag does not change anything. It's a hashtag. Now, I understand her point of view because she's looking at it in a sense if you want to make a statement and be a lobbyist or an activist or something. But as a data scientist, we look at hashtags and tweets very, very differently. NLP engineer, you are going to look at hashtags very, very differently to her. And even further, there's this other quote by Dick Costolo, who is the founder of FeedBurner. FeedBurner was a web management software company that was acquired by Google. Yeah, that's a tech person's dream, to be acquired by Google. And what he said was that I was in Shanghai recently where Twitter is blocked, and yet there were ads and billboards across town with hashtags on them. Hashtags say a lot. We use it in marketing for political messages. It carries a lot of weight. So it's not something you want to discard. So unlike what Miss Shonda Rhimes said, hashtags say a lot to NLP engineers, so it's not something that we want to put in the garbage. And hashtags are quite often used for text analysis to see what's trending, to do sentiment analysis on it. And intelligence work, actually, they have data sets available where tweets were used for people who were in certain terrorist organizations, where one example is Fanboys, and they did topic modeling for these tweets from these persons, and you see you get to understand a lot about these groups from it. So intelligence and security, and even marketing and political strategy, the text analysis of hashtags are very important. So why is it that we don't want to put our hashtags in the garbage? Before I continue on this slide, I just want to show you something. The general process of text cleaning involves either all or some of this. So we would remove HTML tags, for instance, if you are cleaning email content, which I did just last night, and then you remove accented characters, depending if it's Spanish, Portuguese, French, and then you split and expand the clitics. For instance, if for the word I'm, which is I''M, that would split to I space AM. We touched on some of this in earlier lectures. We also remove special characters, remove digits, separate the punctuation from the words. We discussed stemming, lemmatization. But think about this. If we were to do each one of these things, like remove special characters, then the hashtag in the text will become lost. So if I wanted to look at the trending sentiment for a certain football game, for the World Cup final, and I needed to get the hashtags for hashtag World Cup final or hashtag Argentina versus Germany or something like that, then when these special characters are removed, those hashtags merely become World Cup 2020. But if we were to remove the special characters, for instance, the hashtag in front of the actual hashtag word, we can no longer sort or do further analysis with the help of the hashtag. So that's actually why I chose this practical for you, because quite often you learn text cleaning, but then in reality, when you come and you get some really dirty text data from tweets that you scrape, and it's important for whether it's your job or your project, you may get a tutorial or a typical text cleaning procedure that did not cater the fact that you are dealing with tweets, and then you actually remove a lot of useful information. So we agree that hashtags contain important words that should not be deleted during pre-processing. And for instance, usernames, like my username at Nadir Sajar, that does not contribute to the meaning of a tweet if I were to tweet something. So part of the cleaning for tweet cleaning would be to remove the username, which is very easy. You find the text with the @ and then you just remove that. So that's fine. But when it comes to the hashtag, the best practice would be to only delete the symbol hashtag only, and then we preserve the text of the hashtag and then save that to a new column when we can label the title for that column hashtags, and then we can use that to contribute to sorting and analysis. So enough of me talking, let us go into our practical and play with our Coachella dataset and clean up some tweets. So the first thing we want to do is to find all the hashtags within our tweet. Now, you may think cleaning tweets or cleaning text, the pre-processing, is a bit boring. Now, actually, when I now started NLP, I thought this was so dry, this was so boring. I wanted to get to the really cool stuff. And now, I don't know what's wrong with me. I don't know if it's the COVID sort of lockdowns where I don't have as much freedom to socialize. I actually do think the pre-processing and all these little bits of cleaning is quite fun. So maybe I do need to start by getting a bit of a social life. So let's just start with defining our function named hashtags. And we are doing this on our text. We'll call that object hash is equal to re.findAll into, this is our expression, r quotes hashtag to brackets \w plus brackets, and make sure your quotes were closed off, and then we return hash. Now for this re.findAll and this expression, you can revert to our regex completed notebook, and there I explain this \w and the plus, and also I went through the regex findAll function. This was for our example with extracting emails, but it's the exact same concept over here. So it's really basic. Don't let these things confuse you. Just look it through step by step and even look at the cheat sheet, and you will realize it's very simple and it's very straightforward. So essentially, all we are doing is that this W, the backslash W, it represents any word character, meaning letters, numbers, or underscore. And the plus means that it would keep repeating, it would keep searching for that character. And so in this case, we want to find everything, all the alphanumeric characters after, that is positioned after a hashtag. So that way we'll only find the hashtags. So before we get all, detailed and run this on our data set, let's just do it on some basic sample data. So let's do a sample tweet. So our now this would be we want to run this on all our text for our tweets, right? But before we do that, all I'm doing now is that we're doing a sample tweet. Okay, so our sample tweet equals to, put anything you like, just make sure it has a hashtag. I'm putting hashtag Game of Thrones is one of the best ever. And then in between, I'm also going to put a hashtag GOT. So that's our sample tweet. And then, actually, let us put one more hashtag, Emilia Clarke, because I absolutely love her. So it's Emilia Clarke. Right, so that's it for our sample tweet. And our hash is equal to RE. Sorry, we don't need to type this out. It's the same thing up here, it's just a sample. So just copy this and paste it in. Okay, so that's our expression. And then we want to run that on this sample tweet. So you just call this object right here. And we want to print that. It's really basic. And let's see what we get. Excellent. You notice we extracted only the hashtag, so it's Game of Thrones, GOT, even if it's in the middle of all this text, and the end, Emilia Clarke. So we're able to extract only the hashtags. The reason we are extracting these is because later on we are going to use this function to create a new column and dump these into that new column. Okay, so let's jump directly to the following lecture, where we remove the tweeted at username. Welcome as we continue directly from our last lecture within the same IPYNB CodeChilder Tweets notebook, and we are about to remove the tweeted at, which is our at username. So let's get started on that. So let's define our function called remove users tweet, and then let's go into our tweet is equal to re.sub. If you remember the dot substitute expressions that we did as an example in the regex section. So this expression is a tad long, but it's very simple. So just type it out with me and then we'll break it down simply. So re.sub into our A to Z capitals and A to Z common, and close those square brackets off, and plus square brackets, close that one time, the same capital A to Z, common A to Z, so it's our alphanumerics, and then we do 0 to 9, we do a dash and also underscore, and outside of square brackets we just have a plus. Immediately after this apostrophe, this quote, you'd put a comma, blank, and then on the desired input, the desired text we want to run this expression on. And the most important part, now ideally what we want to do here is that we want to remove the tweeted at name. It always comes with a format, at, and username. So you notice here we have our alphanumeric content, which is a name or name with a number. But does this make sense? Because we want to remove this format. So of course this does not make sense. We should have something with the at symbol involved. So exactly so, we need to put the @ symbol here. So very simply, what we are doing is that we are looking for a scenario where we have this format, the @ symbol, followed by these alphanumeric keys. And when we have this format within our tweet, or whatever text we have, we want to take this entire thing and have it substituted with a blank. So we are removing our tweet, essentially. So just do a return tweet, okay? And to do a trial on this, to do some sample tweets before getting to our dataset, just like we did in the last lecture, let us copy the sample tweet from up here and paste it down here. But let us make some adjustments to that. Now after copy pasting it, remember to change this object that we're calling here. Instead of tweet, we want it to be sample tweet for this sample tweet. And because we want to remove a username, let us just make an adjustment to our sample text and put @username. Okay, so let's run. Okay, great. So notice we have nothing to do with this function. It has nothing to do with the hashtag removal. It's only this bit. So we managed to completely remove our username only. Great. And we're left with the hashtags and everything else. So that's what we want. Later on, we will fuse all the functions together and nicely clean up our data sets. And for instance, if we were to run both of these functions, we would remove the hashtag and the username, but we will get to that after. Let's just do piece by piece now. So let's move on to this little part with remove links. So let's define that function, remove underscore links, tweet, colon, and then we are taking a string and then removing the web links from it. That's essentially all we are doing. So tweet is equal to re.sub into r, and in quotes you have http:/s plus comma blank, and then on our tweet here. So this line we are removing the http links, and then one more line, tweet equals to tweet.strip to square brackets link. What this does is that simply it's stripping the tweet from any links. So we have our HTTP removed and all our links. That's basically it for this. So it's return tweet, and to do our sample tweet, you can just copy this again. You can change the tweet if you just want to do something less boring, just not have the same thing over and over. So let us change our sample tweet and do something with COVID. Hashtag COVID-19, hashtag vaccine. Many companies are researching. We can put our hyperlink. So let's put our link, http gmail.com. Okay, good, we have our link, but remember to substitute the regex expression with the regex expression for this section, remove links, okay? So copy this, actually copy both of them. Copy and delete this bit. So we want our define function within our sample. Okay, make sure that's okay. Right, run it. The only thing that's stripped is our URL. So actually, to make this less confusing, why don't you rename this to URL, and leave that as tweet because that's here, and make sure to change this one to URL. So that's it, okay? Then copy this and just paste it there. I'm sorry for having you do this twice. Okay, just run it again so you see that it definitely works. And our URL is gone. We are left with our hashtags. Okay, let's go into the section. It's a very easy, simple, short section again. We are removing our non-ASCII characters, and I remind you that the non-ASCII characters, well, ASCII characters are basically characters in the English language. So the non-ASCII characters are, for instance, in Arabic or Hindi, and these languages where the characters are actually not using our English-based characters, our alphanumeric keys characters. So we want to remove all those non-ASCII keys. So let's define non-ASCII into S colon and return space quote and then dot join into I for I in S if order is I less than 128. And what this is something called the order function, and what it does is that it accepts a string of a length 1, and you want it to retain a representation. An example of this that makes it really simple is, I put a note here for you, is that if you had, instead of I, with order I, that can make it look more complicated for you. So if you had order and B, and you get a retain of 66, what that means is that this character B has a Unicode point of 66. So in our case, the reason for choosing 128 is that the first 128 Unicode code point values are actually the same as ASCII. So picture our ASCII code all within 128. So we want anything that is within that range, and anything out of that range is not an ASCII code. So it can be something that represents A in Arabic, for instance. So if it has surpassed that range, it's a non-ASCII code, so we want to have it, so that's why we have the blank. One more line of code and put a comment saying that we are removing, and put lowercase because we are going to make everything lowercase. So let's define our lower text colon, and this is really short, so it's just going to retain text dot lower. That function just automatically makes everything lowercase. And yeah, so these two, let us run our example to remove anything that's non-ASCII and then make everything lowercase. Also, you should note that if we are doing an analysis where we actually need the other languages and then we intend to do some translations on that, then you would skip this function, because if we were to run this function on it, we would be deleting a lot of very valuable stuff that we would need to translate. So just keep that in mind. That's why sometimes you can't always do a cookie cutter process when it comes to text cleaning. So you need to pay attention to what your data is and what is it that you need to get out of your data. Okay, so now that we've had our functions created for our non-ASCII keys and our text to make everything lowercase, let me show you an example of how we just do some sample non-ASCII removal and then make everything lowercase. However, I don't have any non-ASCII keys I can type for you. So let's just quickly head over to our search engine and just enter something like Greek letters. Yeah, I use DuckDuckGo most times over Google. You can give it a shot if you haven't tried it yet. And okay, so let's just go to Wikipedia. Just copy any portion of these Greek letters and then head back straight to our notebook and go to a new line, and then let's just put our sample text is equal to I am very hungry and I want to have dinner, which is very true right now. So yeah, so that's our sample text, and let us just simply run our function on this text. So let's do non-ASCII into our text. That's all. So be sure to run this function, and I'm sorry, we need to paste in our Greek letters. So let's paste it in the middle, right? And remove one of the commas. Okay, so run that. Excellent. So we're left with everything, even the comma separators, and all the symbols, sigma, phi, omega, they have been removed, and we are just left with everything else. So let's quickly jump to our lowercase example. And yeah, I'm actually hungry, which I usually tend to lose a lot of my concentration, so I'm doing pretty well considering. So let's do a new cell and do some random text again. And let's do our sample text and equal that to, let's add some capital letters to this. I am wondering what to eat. Hashtag Coachella, and party will be like a sample tweet that we may get. Then don't forget to call our function lower on our sample text and just run that in simply lowercase everything magically. So remember to run the cell face because I did not just now, and then okay, great, magically every single thing, even the letter that was within a hashtag, the hashtag didn't bother, it would lowercase things even within the string. So every single thing was magically lowercase. So let's jump into our next lecture immediately where we remove our stop words, see an example, and don't worry, I know it seems a bit tedious, we're doing one or two things after each other and we're not doing anything with our major data set, but we're just going through everything step by step, and then we'll bring it all together and then we'll be able to clean our dataset. So see you in the next lecture. Continuing with our text cleaning practical, using our Coachella Tweets dataset, we have just performed some examples of the previous functions we wrote, and this time up we will be doing our stop word removal and then to find and remove all the email addresses contained in our text data as well. Before we get started on our stop words function, if you see the difference here where in order to run our lowercase or even our ASCII function on our sample text, all we did was that we merely had to call our function. In this case, our function name was non-ASCII, and we just called that function and ran it on our selected text. Same for this, our function's name lower was just lower was the name of it, our function, and then we ran that on our sample text. And you may wonder why we didn't just do this in the beginning, where right here in this case, when we had our sample tweet for COVID, the vaccine and whatnot, we copied our function and placed it here and then printed out the result instead of just calling the function name. And this is just one way where there's not one hard and fast way to do something when it comes to writing an algorithm. So I may write a function in a certain way using, and it works, but then there's another way you can do it. So it's not one hard and fast rule, that's not the only way to do it. It's just that this is the easier way and it's faster to do as opposed to this. So here we go with our stop words function. So let's start with defining remove stop words, our tweet. And keep in mind that this is not restricted to only tweets. This function can be used for removing stop words in any other type of text, whether it's emails or articles from blogs or whatnot. So now we are going to select all the stop words in this compilation named English. Stops equals to set stop words dot words. This stop words is what we imported the NLTK stop words from the beginning. Here, that's exactly what we are talking about. And this is what we are using. We're using the English stop words. And this line is not mandatory, but I'm showing you it because you would like to, in the future, have custom stop word lists. And for instance, if the stop words list with the English stop words did not contain certain slang words, and in our results you're seeing too many tweets with those words and it's getting in the way of our analysis, and it's best if we just remove those words that do not contribute to the meaning of the tweet, because it's basically useless to add the custom words. And after getting your results at the end, if there are stop words that you don't want to see keep coming up in your cleaned tweets, you can come back up here, readjust this new list of custom words, run the stop words function again, and then you will have them being removed later on. I'll show you an example of this later on in the lectures, but for now let's just continue with removing our stop words and doing the custom bit. Stops.update, because when we add these custom words, we want to update it we want our stop words list to be updated. We don't want only these words to be used as our stop words, because that would be a disaster. An instance of this was that I was doing some email cleaning, text cleaning for a client for email classification. In the most common words later on in the analysis, I kept getting mail to, because that's in all emails. So that was not part of the standard English stop words list. So I had to manually go here and put mail to as one of my custom words. And this would depend on the type of text you have. So let's put BRB, it, this, and YOLO. New tweet equals to space dot join. Make sure that this is a space, okay? Join into word for word in text dot split if word not in stops. Now the reason I told you to make sure that there's a space between these two quotes here is that what is happening here is that if we had a sentence, let me just type a sentence for you. This concert is wicked awesome and it is just so fun and lovely. Okay, so we want to remove the stop words this is and it is and also so and. Now, yeah, we want to get rid of those, but initially what we want to do is split the text. If you remember in our tokenization and regex practicals that we learned earlier, we would have broken up each one of these into separate tokens. So it's no longer an entire sentence. It would be tokens that are separated so that we can identify the stop words. And once the stop words are identified and they are removed, what you want to do is rejoin these tokens so that they are in this form once again. But when they are rejoined, if we don't have this space, they would be rejoined like this. And this is not what you want. So that's why that space is there. And now one last line to retain this result. Oh, my mistake. I'm still thinking that we are just splitting our text. So yes, we are splitting up our text into tokens, but we have actually named that text as tweet. So in this case, we are needing to change this from text to tweet. Just make that quick adjustment. Now for our last line for stop words, so we return our new tweet. Okay, that's it for our stop words function. Then let's do a quick sample. I love this concert and I do not want to leave. Hashtag music. And then we just call our function remove stop words onto our sample. Great. So you can see that we ended up with love, concert, want, leave, and music. So it removed I, this, and I do, also not, and to. So we were left with the same value and the same context of the sample. So that's essentially what stop words do. It's very simple, yet very important. Let's do one more example with the custom bit. Now, if in our text, in our tweets, or in another instance when you are removing stop words, and after you've removed your stop words, you realize that you're still getting a case where instead of yours, people are typing URS quite often. So let's have an addition to the sentence called I love yours. And when doing our text analysis, one of the most frequent words that we're getting is yours, URS, and it's getting in the way of our most popular bigrams and trigrams. So we want to remove URS, yours. I want to show you how the result would be with yours. Now here we have it. It removes everything else except yours, and yours is actually considered a stop word, but it's just not in our English list. So this would be a case where we want to add this to our custom words. So we add yours here. Run that function again, and then rerun this a second time. Great, so now we've removed our custom text, and you see how this one line worked. So that's it for stop words, and moving on in the next lecture for removing email addresses. As we continue with our text pre-processing lesson, join me as we remove email addresses. Removing email addresses from text is not restricted only to tweets. This can happen if you need to analyze emails, classify emails, or lots of other documents. In some cases, you may not need to remove the email addresses, you merely need to find the email addresses, and in our regex lecture, we actually found email addresses using regex find all. And in this lecture, it will be quite similar to this one, but the only difference is that for this one, we wanted to just extract the information. We just wanted to find the email addresses and extract them. The difference is, in this case, is that we want to find them and remove them. So we're not using the find all, but we are going to use this same regex expression. So getting started on our email removal function, it's called define email address of our text colon email is equal to re.compile. The difference in that is that this time we are using re.compile, whereas before we had used re.find all. And it's the same regex expression from our previous lecture on regex email removal, and that will be, so again, it's the same formula from here, but let's type it out just to remember and understand if in case you forgot. Square brackets, and in this first square brackets, we are putting the characters before the @ symbol. So if my email address is my email at gmail.com, you notice that before the @ symbol, we always have a string of alphanumeric keys, characters. So it can be my email _ 1990, and this would be anything before the @ is what we want in this first part of the formula, the regex expression. We have \w, \dot, dash, that's the end of that, and add the @ symbol. So this is everything before the @ symbol. Then we open up our brackets again, our square brackets, and now for this part we want this side, the right hand side of the @ symbol. So it's the same thing, \w, \dot, dash, and your close brackets, and the plus sign, so we keep continuing as long as there's a letter alphanumeric character that follows. So this, in regex expression form, is representing this, just our email. So I'll leave that note there, and what we're doing now is just one last line. It's so quick. It's a nice little function. Return email dot sub, because we're substituting R into blank and text. So what we are doing here is that when we get our email, when we find our email in a tweet or text, whatever text body you're using, because you can use this. So in our text, whatever our sample text or text, whatever it is, when we find the email in this text, we are replacing it with a blank. So that's getting rid of it. So you see the difference. In the first time, we did not have this substitute use of regex, because we are not substituting it with the blank. And in this case, we want to keep the email address because we wanted to output the email address. In this case, we just put a blank to get rid of it. So let us do a sample to see how this works. Sample email #order customer service hashtag contact and have contact 1990 at gmail.com. Then we call our function email address, and we want this to be experimented on our sample email text. Run this cell and then try this out. So let us run this cell and try this one. Okay, great. So everything we have here is present except our email address. So in future, if you need to clean up text and for some reason there are or can be emails, you can simply use this useful function. For this lecture, we will be using regex again, continuing from where we left off. We just learned how to remove email addresses, and in this case, we are going to run a tokenizer in order to actually remove unnecessary punctuation. So to do this, let us start off. I'm going to put a text note here. So we are going to use regex tokenizer. Regex p tokenizer, and we can make it pretty. You can put the font color. I use this number 00CEC9, but you can use all sorts of different. This is the hex code, and you can Google hex codes for color and you'll get a whole range of colors. And if you don't want to go through this trouble, you can always type blue or pink. It really doesn't matter. So to start this function off, we go to def punctuation, and then punctuation for our text. Then our token will be equal to regex p tokenizer, and we want this expression to represent what we want to do, which is to form tokens out of alphabetic sequences. So I'm going to write that out, the expression, which is simply backslash w plus sign. That's all, there's nothing else to it. So that's our regex expression. I'll put a note here, regex expression to form tokens out of alphabetic sequences. Our text is equal to token.tokenize into, so we are doing this on our text from here, whichever text we choose to run this function on. The text is equal to space dot join, and then return our text. So let's do an example again to see how this all works out. Sample text is equal to, we're going to a party. We want to run our new function on that sample text. Let's try it out. Okay, so that's exactly what's expected. The apostrophe was removed because everything was tokenized. But when we did find something that was not a sequence, but that was not an alphabetic sequence, which in this case is not the alphabetic sequence, we remove it and then replace it with a space, which is what happened here. And we can try it again, where we're going to a party, are you going? Question mark, and try it again. See, it's the same thing with the space here from before, and also the question mark has been removed. So that's very simple, and now we go into removing digits, followed by removing special characters. So let's do the same thing with a text block here. So you do font, color, equals to, quotes, pink, forward sign. We're going to remove digits. To remove digits, we write a basic function. So let's define that function, remove digits from our text. Pattern equals to r apostrophe square brackets hat symbol a to z capital and common dot comma exclamation mark question mark forward slash colon semicolon backslash quotation mark backslash apostrophe backslash and S. Now don't be confused by this. It's rather simple. What you need to pay attention to would be this. That is the caret symbol. Some people call it the hat symbol, but I like to call it caret. All this is telling you is that now there are two ways to do your expression. When either the caret is either inside these square brackets or if it's on the outside. In this case, as it's on the inside, whenever you see the caret on the inside here, what we are looking for, we are looking for any character that does not match what we stated in here. So remember, we want to remove digits. Do you see any digits in here? Not at all. So in here we have all our characters between A to Z, both capital and common. Then we also have some of the symbols that we use, some of the punctuation, which is our question marks, exclamation marks, commas, because these are parts of the context that's needed, and sometimes how we talk, it gives us an idea of the context. We don't want to remove everybody. But what we don't have here are numbers, no digits. So whatever is inside here and the caret is inside here, we want to match in our string of text everything that is not in here. So if the caret was on the outside, we would actually be getting rid of these guys, which is not what we want, because NLP, we want our text. Because if we put it on the outside, we would have been keeping our digits. Okay, so I'll put a note here for you on what that means. When the caret is on the inside of our square brackets, like in this case, we are matching any character that is not included in this expression within the square brackets. And it's the opposite when the hat is on the outside of the square brackets. That's it for this function. Let's just retain what we want. We want to retain re dot sub, because whenever we find something that does not belong here, meaning it's a digit, we want to substitute that with a blank because we want it to be removed. So on pattern, comma, blank, comma, on our text. That's all. That's all there is to removing digits. Give it a shot. On sample equals to number 5 and 7 were great. Then we want to do our remove digits function on that sample. That's all. Okay, and our digits were removed. Excellent. One more and then that's it for pre-processing. So we are going to do removing special characters. Okay, so let's put another text. Font color equals to turquoise /, and now anything you type would be the color turquoise. We're going to remove special characters. Let's do one quick function. Define remove special characters from our text. So we're going to define the pattern that we want. So character pattern equals to R. Do similar with the caret this time. Common letters, capital letters, 0 to 9, dot, comma, exclamation mark, question mark, /, colon, semicolon, backslash, quotations, backslash, apostrophe, backslash, S. Close those off with our square brackets. So again, our caret is on the inside. So everything here is what we do not want to remove. So everything that is not here is going to be removed. So in this case, we are only focused on special characters, which is why we opted to keep even our digits, because it's specifically a function just to remove characters, special characters. So return re.sub into character pattern, comma, blank, and on our text. Okay, so run this and let's do it on some sample text. Sample special is equal to I saw stars, it was great, hashtag great, and it only costed £3. Let's see what happens when we do our remove special characters function on this sample special text. Okay, so the exclamation mark stayed as planned because it is within our expression here. So exclamation marks, question marks, all those are in it. And so it's still there, all our letters. The stars were removed. In this case, the hashtag was removed, which is what was relevant with the tweets. So in the case with the tweets, in the first time when we were to find the tweets, the hashtags, and put it in a new column, it would have taken this and copied hashtag great into the new column. But then later on during our pre-processing, it would remove this. So then it would start to add meaning to it, and we would have our cleaned data here. It also removed the pound sign. Okay, so that's all for our mini functions that we were writing one by one. Now it's time to tie it all together, because you may be wondering, okay, we have been writing these functions and then we were doing these sample texts and seeing how our function performs on these one-line answers, but what does that have to do with our data set? So let's go to the new lecture and we'll see how we put all these functions together to do a simple process to clean our data set. Continuing from our last lecture in the same Coachella Tweets IPYNB notebook, we have completed the majority of the work. We wrote all of our functions. Now it's time to put them together and actually see how this works on a data set. So let us insert our new header, font color equals to turquoise. Here we apply pre-processing functions to datasets. Now if you scroll up with me before we continue, remember when we started out with the hashtag function? Now the hashtag function was merely to find the hashtags. We did not want to get rid of them in the cases where we would do a re.sub with a blank. No, we did not do that. We just wanted to find them. And then we want to put them into a new column, but we did not do that yet. All we did from this function was to find them. So now we want to put them in a new column that would be on this side here. So here we want a new column with the header, with the title, hashtags. So let's do that first. And remember that this is the function we created, def hashtags. So the name of this function is hashtags to find our hashtags. So let's go back down. So now we are going to apply that function hashtag. Oh, and one more thing, let's go back up to the data set. Actually, instead of scrolling all the way up to our data set, I'm just going to put it here again for you. So df.head. So let's just take a look at our data set. Remember what we're dealing with, because we haven't seen it for quite a while, because in the last few lectures we were just writing functions and testing them out in our sample data. Now it's to get back into the real world and to get our hands on some real data, nice data set. So just remember how this data set looked. The last column was user time zone, and there's nothing else, no other columns, and we want to put our hashtags column here. So we are going to apply pre-processing functions to the data set. So we are applying the first pre-processing function, which is our pre-processing function hashtag. Okay. Out of our entire data set, which column is it that we are going to be performing the pre-processing on? Which column are we going to take the function and apply it to? Because in this case, we want to apply the function to our data set. But is it to our entire data set? Does that make any sense? Or are we applying the find all hashtag function to a specific column? Think about it. Okay. Now, obviously, we are not performing it on the entire data set, because that would mean on every single one of these columns. But that doesn't make any sense. Now, does it? We want to actually perform the functions on the text column, because in this case, that's where we have the bulk of our text, and that's what we want to analyze, because the text column merely contains our tweets, and we are performing data pre-processing on our tweets. So only this column we are concerned about. So we're doing our functions, we're performing our functions on this column. Remember, it's not only 5, it goes all the way down to almost 4,000 entries. So we're going to do that right now. So head over with me to right here. We are going to do a df into, now what do you think is going to be here? Given the format of this, df, square brackets, and our quotes, this is the column name. It's a new column name. Okay, so basically this format means a new column, and that's the name. So this would be the name of a new column. I'm just putting this as a note for you here, just so you know the general format for a new column. And then I'm going to retype it now as not a comment. So it's df, square brackets, and the name of our new column, let's call it hashtag, because it's going to be a new column called hashtag right here. So it's equal to df dot, and the format for this is df dot the column that we are interested in. So we are interested in the text column. So it will be, for this data frame, df, we are looking at the text column, and then we are going to apply a function, and that function that we are calling is the function hashtags. Don't confuse it with this. Hashtag is just the name of the new column, and hashtags is the function that we are applying to this text column for this data set. So this is a really nice self-explanatory little line of code. And just, I'm sorry if I'm going over this so many times. I just want to make sure you get off on the right foot. So that hashtags I'm talking about is merely the first hashtag we defined in the beginning, where we were to find the hashtags, and then after finding them, we are just going to dump it into this new column. So let's see how this works. I'm going to run this. So let us see if this works. Okay, actually it did not. We have our red squiggles, which I hate, because then it's like, oh yeah, we need to fix a problem. That's fine, we need to get used to this. So, okay, let's look at the error. They always give you hints in the errors. So here it tells you that the findAll function is missing a required potential argument string. Okay, so it's not a problem with this line in particular. It's actually a problem with our function hashtags that we defined higher up, because the findAll function was defined within this. So let's go up there and see what is the missing positional argument, the string that they are referring to. So it's going up to the hashtags function, and you notice that this is the findAll expression that they said has a missing string. And yes, it does have a missing string. I am retarded. So here, this expression is telling you that we want to find all the expressions that has this pattern. So it's all the hashtag patterns. So everything with any hashtag, which like Coachella 2015 or anything like that. So this is the pattern it's looking for, but it has to look for this pattern in some sort of text. So it has to look for the pattern in some sort of, for instance, a tweet. So if this is my tweet, then it has to look for a hashtag or anything of this pattern in this body of text. And it's not positioned here. And that's the string they were talking about. That's not positioned in this findAll expression. So all we need to do is put in that text that has to be defined. So this text in question is what we need to search in. Okay, that's all. So if you run this, it's going to work beautifully. Scroll back down and run this one again. Great, no red squiggles, all is well. And then let's run our data frame again, and let's look at the head to see what has changed after we did this. Okay, so everything is the same if you look at all the columns, except our new column over here. It worked. Our new column named hashtag is now here, and it's not just a new column, it works well too. Our function has extracted the hashtags from our tweets, nicely put them in this new column. And this has been done for the entire data set, all the way to the number 3800 or around that. So let's take a look at the bottom, df.tail, the last 5. So at number 3845, we have the last tweet, and these Coachella 2015 and Impatient. was the last hashtag extracted from our last tweet. So impatient, yeah, so this person was impatient, and it makes sense because their text was like, come on, line up. And yeah, so that means this person just wanted the lineup to get going because, they just couldn't wait anymore. So that was the first bit of us applying our functions to our dataset, but we have a few more lines to go. So we are simply going to take each one of the functions from earlier and apply it in series to our text data. So we wouldn't have to continuously keep doing it one by one. Okay, so I'm going to do all for you in this line. So let us form one more new column, only one more, because we have the hashtags here. And then we want one more new column, which will be our new cleaned tweet. And this new column that we're adding to the right hand side of hashtag will be the column that we use for our text processing. So we will not be using the text from this. It will only be from our brand new pre-processed column. So that would be df into whatever our new column name would be. So let's call it new tweet or cleaned tweet, doesn't matter, and equals to df dot text dot apply. We are applying a function equal to, and which function are we going to use? Let's go up to our function define. So we have the remove users, and then remove links, and then non-ASCII. So let's start with this one. Let's remove the Twitter username. Okay, so let's remove users. So to apply function equal to remove users. And then so I'm going to run this so you can see what happens. I'm going to just delete this to clear it up for you. Let's go to new line, and let's choose this. Let's choose this row number 1, because it has a username in it, Sudsy Buddy. So it's df into, I'm just showing you how it works, df into title, dx into text, and we are looking for the first row. Okay, so let's see what happens. Okay, so this is the output, and you notice that there is a username here. So do you think it did not work? It did, actually. It did. It worked properly. But this is not where you see the output. All this is doing is that this output is just simply showing you the text contained in the first row of this column. So that is never going to change. This will always be RT at Sudsy Buddy, wait, this is absolute fire and whatnot. And it's always going to be the same in this unchanged column. So where indeed did the output go? If we run this df.head again, look, there it is. So what happened was that in the first line of code here, we created a new column called hashtag, and we ran this function, hashtags. So we put all the new hashtags in this new column. But in this time, we created our new column called new tweet. And this is where all the pre-processed tweets will be going. So everything that we take here and clean it after we found the hashtags, saved them. Now we're going to clean everything. So actually, I will put a note here for you. We begin cleaning the text. So you know that there's a separation here. So this new column formed was right here. So if you look at here with RT at Sudsy Buddy, then you notice that after RT, we directly go to wait, this is absolute fire. So we removed the Twitter username because of this pattern. So our function worked beautifully. We still have a few functions to go, so let us continue applying them. So the other function would be, let's do clean HTML. That would be to refresh your memory. If we go up to remove links, and we will be calling this function remove links. So just do same thing, df onto, are we creating a new column in this time? No, we are going to continue cleaning this text data, and each time we run it, we will keep cleaning and putting it back in this column. Okay, so are we going to create a new column? Do we need to? Of course not. We have a new column here, and this tweets is not completely cleaned at all. It has a lot of unusable or non-informative text, so we need to keep cleaning this column until we've ran our functions on it. So we don't need to create a new column, so we use the same new tweet. So what happens here when we use the same column name is that when we run this new line of code, it will update and refresh onto this same column. So it will just revise it with this new function. So this is equal to df dot, what do you think goes here? Before, we were taking the context of text, okay, and cleaning this. But do we need to do that? No. We can actually just take this text and clean it straight away. So we can go to df dot, this column, which is new tweet, and we apply the function equals to remove links. And we need to repeat this for each function that we defined earlier. So copy this line and just paste it in, because we are going to put back our new function that we run directly back here again. So let us do our non-ASCII function. So the non-ASCII function. So in this line, we are going to remove the non-ASCII characters and copy it again, paste that, and let us do, okay, after the non-ASCII one, we have the lower function, and then we have to remove stop words and email. So let's go down. Sorry for scrolling so fast. Right. So after the non-ASCII, we are doing the function lower, and then email addresses like we just saw. Copy and paste it, and we are running the function email address, and then remove stop words, copy, paste, and we are calling the function remove stop words. And last one, if we just go up, right, so this one was the email addresses, and then the last one we want to do would be, we have the remote digits and special characters as well to go. So we'll do punct, remove digits, and special characters. Okay, so after this one, paste, this would be the regexp tokenizer. So it's punct, and then two more. This was the remove digits, and then the last one was our function to remove special characters. Okay, so this is not confusing. You just have to look at each one step by step. We created each function before, we understood each one, and we saw our sample text for each one, and we just put all together instead of running each one by one, because every time we run one, we would clean the data a little bit. So after this one, we remove the non-ASCIIs, and after this one, we make everything lowercase. But if we ran all together, you'll see the drastic change. Oh, and before continuing, we have one tiny mistake. Again, forgive me, please. In this entire thing, what we wanted to do was to apply the pre-processing functions to our dataset. And we initially started to do exactly that. We applied our functions to our dataset and the column, the respective column. We did that here again to df.text.apply. We apply the function, and this is the function. But I so retardedly copied and pasted these, and I did not put the dot apply. So right after the new tweet, kindly put dot apply, or we would not be applying our function at all. So this would remind you to always put your dot apply when applying the function that you earlier wrote. So dot apply. So let's just copy this and paste it in. 1, 2, 3. Okay, great, beautiful. Run this. Perfect. And remember what this looked like here. So let's create a new cell right under there and copy this same row and paste it. But remember, when we ran this, I can bump this up on top here for you. Let's move that up right? So you don't confuse this. So this was before we applied our functions. You notice there's all these capital letters. There's our username. Then there's some jumbled text here. Then there are definitely some non-ASCII keys here, similar to, remember, our Greek letters. There's a hashtag, and then here is our link. So all these things are dealt with in this function. So let's see the new outputted new tweet that would be in this column. So to see the new column for the first row, we go to new column. Okay, so this was this bit. So this is on the first column. And to see what's in this row, in the new column, we go to change this to our new tweet. And then run it to see the difference after running this. Okay, it's a drastic difference. So first things first, we had our remove users applied. So this was no longer here. Everything is lowercase. So everything is, totally lowercase. Then email, we don't have any email addresses here. Non-ASCII, okay, so it removed all these non-ASCII keys and also the special symbols, because these would not have been removed in the non-ASCII. They would have stayed. And these would have removed only for the non-ASCII keys, like our Greek letters. It removed our link, it removed the hashtag, and remembering the stop words function, it also removed our stop words. So it removed this and is, considering those unnecessary, not contributing to the meaning of our text. Okay, so you get an idea now how to pre-process text in a very realistic manner, because in the future when you have to do pre-processing and cleaning on datasets, and you'll do this numerous times, this is a typical way of how this is done. It was both a teaching section, this entire section was very detailed teaching section with many bits, many functions, one by one, slowly being done, but in the end, it's very, very usable, and it's exactly what you will be doing on real-world data when you have to pre-process and clean them. So it is a very good lesson for both introducing you to cleaning text data, but also it's a great lesson to put you in a path to cleaning realistic datasets in the real world. Because whether you are advanced or a beginner, you will have to be doing text cleaning, performing certain things like removing digits, removing non-ASCIIs, and you need to understand how these functions are done, because sometimes later on we would learn to do these in a much shorter way, where in about 1 or 2 lines alone of code we can do it without writing the individual functions. It wouldn't always be this long and so tedious, because we have much shorter, sophisticated ways of doing this in future, but we need to learn the basics of it. So I hope you enjoyed this. And if we were to run our datasets again, you will have our new tweets, but this time it would be all the functions already run on it. So it's totally cleaned. You notice it's all lowercase, and they're all nicely cleaned up with stop words removed, links removed, and all the symbols, everything is gone. So it's only left with meaningful words. And if you want, you can do some more of these df columns and check out the before, which is you can do df with the text column to see the before, and then you can do a df new tweet like what we did here to explore how some of the tweets were changed. I'll do one more for you, and then you can explore on your own if you desire. So I'll just copy and paste this. So let's do a random one. It goes up to over 3,800. So let's look at number 3,800. Okay, so it's a very short tweet. That Coachella 25 lineup, that Coachella 2015 lineup though, apparently it was good. And 3,800, well, it's not much to see on this one. All it did was remove the stop word and remove the hashtag. Also on the stop word up as well. I'll do one more and hopefully we get a longer one. We can do 1,000. Okay, so it's a nice long one. Hashtag, hashtag. Hashtag is a lot of hashtags. And then a phone number, a username, and then we have a colon, capital letter. Let's see what our new column holds. Okay, so we removed the hashtags and we have Coachella discount tickets on deck. Well, the hashtags were removed here, and then we took out the phone number, and then we removed the username and some of our stop words. So it's pretty good, and I hope that you had a good learning process. It was a sort of a long section, but it's very, very informative, and it may be a lot to remember, but I'm hoping that you remembered all the concepts of it. So in future, when you need to clean text and you need to pre-process them, you can keep the completed Coachella Tweets IPYNB notebook. So you can download the second IPYNB notebook for the section, which is the Coachella Tweets Complete IPYNB notebook, and keep that for future references when you have to do pre-processing, just so you can remember what to do until it becomes like second nature. Okay, so that's it for now. Hope you had a great time, and see you in the next section. Name entity recognition. How is it used, and why do we even need to learn it? One important application of where NER is used is in question answering systems. If I were to ask a question asking who is the CEO of Google, part of the question processing includes determining the type of answer required. That's called answer type detection. That's answer type detection. And what answer type detection means, it's simply when I'm asking who is the CEO of Google, I'm asking for someone's name. So what we need from this, the answer type that you detect from this question type, is you need a person. And name entity recognition means that we need to identify the entities in our text, and in this case, the entity that we need to produce would be a person's name. So in order to answer the question, we need the name entity type of the answer. One other example, if I were to ask what country is the pyramid of Khufu located, we are clearly asking about a location. So the answer it's asking you what country. So the entity type is some sort of country. So that means that the entity type is actually a location. And when it's a location, for instance, a country or a city, that's tagged in with NER, the tag that we use would be geo. When we get into the lesson, you will get a list of the types of entities and the tags. So this is just one example. When you go through text and there's something like Egypt or Cairo or France, that would be tagged as geo because it's indicating that the entity is a location. So that's one example of why we need name entity recognition. Later in the course, we discuss chatbots and question answering systems in quite detail, and we do practicals on these, so you would understand these in much more detail later on. But for now, let's focus on name entity recognition. Essentially, a chatbot has three general aspects. The first one is called intents. Then secondly, we have entities. And thirdly, we have responses or some sort of action. So for my chatbot, the intent is merely what is the human want? What is the intention of the human's question? So what it is that they want. What the human wants. So what is the human saying? So it's purely the intent of the question. Very straightforward. And when the chatbot sees the text or the question from the human, it needs to process it and figure out the intent. So the intent classification and processing, that's part of what we cover. But right now we are focusing on the entities. I'm just showing you how NER falls into the topic of chatbots and their application and why it's essential. Because when we go through certain topics like NER or parsing, for instance, to generate parse trees, you may wonder, why is she talking about all these boring things? How does this have to do anything with deep learning or machine learning? But they are very important concepts, so let's just get back to the lesson. So similarly to the question answer system, the chatbot needs to determine what entities are being asked about, right? So what is the person saying? Yes, we need to know the intent. Like if I were to ask about the weather, that's the intent. I want to know something about the weather. But what about the weather? I want to know about the weather in London. So that entity is London, meaning it's a location. And in the chatbot, the response is merely that we want to provide an answer to the intent, the question at hand. So the best way to get an example of the entities aspect of it would be to look at a question. Which city in England is George traveling to tomorrow? Now we have the intent, entity, and the answer, well, the response. The intent would be, okay, we need to know which city in England is George traveling to tomorrow. So we want to know George's location tomorrow. So we need to know George's location tomorrow. Now the entities that are being asked about, now when you look at it, just George's location tomorrow, that needs to be processed and broken down so we start to understand the context of the words, because remember, as a computer, you need to figure out ways to create that word similarity relationship and figure out as much as possible about what the word means. So with George's location tomorrow, the entities being asked about are person, because that's George, and then location, and we need to have that location that he will be at tomorrow. And then tomorrow is actually referring to a date, so we need to provide the location for tomorrow, because we can't take it for granted that when we just say tomorrow that, the bot knows that we're talking about tomorrow. So it needs to understand that tomorrow is a date, because it needs to put it into context, because it needs to understand that this is not just a word, because we did not specify where would George be on May the 22nd of 2021, because if it was specific like that, we can follow a date format and the computer can realize easily, yeah, that's a date. But when it comes to the word tomorrow, it needs to understand that it's some sort of date we're working with. So these are the entities that we need to take in consideration for the response. And the response can be something like, George will be traveling to Manchester on May 22nd, 2021. Because now it specified the person, the city, which is the location, and the date. And if later on now, when we do our practical, it will actually label this and tag this in different colors for us and see that this was a person, and this was a date, and this was, well, geo, because we label places and cities as geo. So that's it for our brief overview on just some simple examples of why we need NER and why we need to learn it. So now it's time to join me in the next lecture as we start our practical project using spaCy. This is the first video of our NER name entity recognition project using spaCy. There is a resource for this video called NER_spaCy_lecture. It's the incomplete IPYNB notebook, and as usual, the completed NER notebook will be at the end of the section, so be sure to download and open up before we start. Let us begin by doing our imports, and we import spaCy, and from spaCy we import displaycy. From collections we import counter. The next import is rather important. We are importing the trained pipeline, Spacies trained pipeline. So we import, we're doing the small one because there are 3 sizes. In the completed notebook, I have the link actually right in this area. You will see a link says Spacie pipeline notes, and it will take you to this link. It's the Spacie models notes, and here you can see the trained pipeline section. We have not just English, we have it for Chinese, Danish, German, French, and there are different sizes. Not all languages have the same sizes. English has small, medium, large, and then this one with transformer. French, I believe, yes, we also have 4. Lithuanian has 3. Greek has 3 as well. So let's go back to the English trained pipeline, and we will be using the en_core_web_small. The SM is a small. You can see that the size here is only 13 megabytes. The medium is 44 and the large being 742. For quick processing time, we're going to go with the small one depending on the size of your project and the extent of it. You choose accordingly. And what we mean by there's a trained pipeline, it has these components, which is a token to vec, a tagger, a parser, NER, and lematizer, and the NER is the one that we are interested in today. So we import that en_core_web, and we go with the small one, and after importing it, we must load that. So let us define that variable as NLP equals to, copy this, paste it, simply put .load. Let's try to run this model on some sample text. Our sample text will be doc, which is equal to NLP, which is what we define here, NLP, and we want to run that on some sample text. Obviously that's not the sample text, so we need to put something in here. I've typed it out for you here, so you can copy this and paste it into your sample text. But if you want to see where I got it from this NASDAQ article. So the article is about Nintendo's profits. It said that there was an estimate at how much profits they expected from the Switch sales. Now they did make a profit on their 3rd quarter, as their profits were 6%, but that profit was still less than the estimated profit of their sales from Switch consoles. And the reason I chose this particular example is that if you have a bunch of articles, thousands of articles, and your objective is to look at the trends of sentiment for a certain industry or certain company over a period of time and correlate that to their stock prices. So it's a stock price correlation based on news articles for a specific company. So if we wanted to go through NASDAQ, Financial Times, Bloomberg, CNN, CNBC, BBC, and just a bunch of news, if you have thousands of articles, yes, you can get the general sentiment on the article if it's generally positive or negative, but an important part of NLP is that we need to extract information from text. So if we were to have, so having this entire article, but not being able to differentiate one type of entity from the other is not as useful. So the whole point is that we need to go through this article and be able to pick out what is an organization, or what is a sum of money. So in this case, we would like to extract Nintendo as an organization. 175 billion yen will be a sum of money. There's also Switch, which is different from the noun Switch, which is not the product. So in this case, Switch is a product, and not just a word just meaning to switch two objects. Then we have Thursday. We have some words that indicate time or time of the year, months, and so on. So we copy this entire thing, or you can copy it from here and paste it into the section where we are supposed to have our sample text. Just make sure it's all lined up. Okay, NER equals to square brackets, regular brackets, x dot text, and x dot label with an underscore. Then we do a loop which says for x in doc.ents. So what this is doing here, this little statement, it's actually doing quite a bit, because at first we loaded the model, the trained spaCy model that comprises of our tokenizing, token2vec, parsing, and lemmatizing and tagging, and that's all in one because so we passed that onto our text body. Then our new variable NER wants to take this doc after passing our text into our model, and then this x.text and x.label, we want to get for every token, we want the NER label for it. So what does the doc.ents do? The .ents, this method, we are passing that onto our document, onto this variable. So this .ents property is actually the standard way to access entity labeling, like the entity annotation, because it allows you to use the ent.label attribute. So what the .ents does is that on our text, it produces a sequence of span objects. And think of the span objects as a sequence of tokens. And that sequence of tokens, we now iterate over and over. So let's see what happens, what it actually does. Let's do an output. Okay, so remember I said that it will go through the text, and well, first of all, the model will send it through the pipeline, and the pipeline will do all the parsing and whatnot. Then after that, we run the .ents method, and it allows us to utilize the label attribute, and we'll iterate over that text, and then it would be able to determine, okay, yeah, this is the label for our token, and then it will go through each token to see if it's an entity. So we have Nintendo as a person. That's actually not correct. This is correct. It's a percentage, but then again, it got Nintendo company as correct as an organization, because in this here, Nintendo Q3 profit, it means the Nintendo company's third quarter. So it's not a person. It treated it as a noun, as a proper name for some reason. So that's not correct. Now, spaCy is not the only way to perform NER. This is one of the methods. It's really good, it's very convenient, and it's quick. But there are other methods. So later in the course, we do a second method of NER, and you see the difference. For now, let's just focus on spaCy. Let's see what else it gave us. So this Thursday, third quarter, this was recognized as a date. Cardinal was a number, which is 6% driven. The year and shopping season, also dates. Money would be all these three because it's talking about a few billion yen. Refinitiv is actually a company, it's not a person. So that should have been an organization and not a person. How about we explore some more spaCy attributes? Our variable tag would be equal to, very similar to what we did here, square brackets, regular brackets, x, comma, and now we use the attribute methods, x dot ent underscore iob underscore. So the dot ent underscore iob underscore is a spaCy attribute, so we are trying to use this method on our data, or on our tokens. Then we're doing a second attribute, x dot ent underscore type underscore for x in doc. And what this is, the .ent underscore IOB underscore, actually, let's do an output first, so it's better that you see it first before I do the explanation. Actually, we have one error. It's ENT, it's not end, it's ent underscore type underscore. Run that, see the output. Okay, notice there's a slight difference from this output to up here. In the first one, when we did the text label and the dot label underscore attribute, you notice that we got the label, we got the token, the text token, and the NER label. Simple enough. But in this case, we have the name, but you notice that it's split up. So in this case, we had Nintendo third quarter, Nintendo Q3 in one, but in this case, we have Nintendo, and then we have Q3 on a second line, and then we have these letters between. So there's a B, I, and O. So the IOB gives you a code for the entity type, and there are 3 codes for the entity type, and you notice there's B, I, and O. And what the B stands for, this means that the token begins an entity. This is a really good example because we have Nintendo Q3, and Nintendo got B, and you notice that Q3 got I. That code I, that means that the token is inside of the entity, and in this case, Q3 is inside of the entire entity, because the entity is Nintendo Q3, so it's in the middle, it's not the first one. And you notice that all of those that got the O code, they here. For instance, profit rises, switch misses estimates, what else? Said, operating, profit again, rose. These are not present in this batch. So what that's showing you, that O is a code for outside of any entity. So I means it's inside an entity, B is the first part of an entity, and O means outside of any entity. And the other attribute, ENT underscore type underscore, simply just gives you the named entity type. And we did this for every token in our document. In this section, we will be doing some really fun stuff. We will be using a tool to scrape Twitter to get Twitter data. And this tool is called Twint. Twint is an OSINT tool. And what exactly is an OSINT tool? So OSINT stands for Open Source Intelligence Tool. So in the intelligence community, the term open, it generally refers to what you call overt. I'm sure in movies you would often hear the term covert. Covert affairs or covert operations. Covert means undercover. So overt means directly the opposite, out in the open. So in our case, we are using open, overt, publicly available sources of information. So the opposite of that, which is our covert or clandestine sources. So we're not getting into that much of cool stuff as in anything covert, so we are sticking to our OSINT tool. So Twint in this case would be the tool, the OSINT tool that we will be using to gather our data for the rest of this section. But apart from Twitter and using Twint, there are many different ways that you use OSINT. So generally, OSINT, or Open Source Intelligence, is a multi-factor sort of methodology for collecting and analyzing and making decisions about making data accessible and being publicly accessible data. And this publicly accessible data in the intelligence world would obviously be used for some sort of intelligence context. And apart from Twitter, there are many other sources and then also many other types of intelligence contexts. Context meaning we can use it in political analysis or in a political arena, even in a pandemic situation where you want to maybe find out about how to gauge the responses from a policy that was implemented. Did the public react? How did the public react from implementing that policy? So it can help us learn about the responses and compliance with regard to new changes in public health policies for pandemics. And then again, we can also use that intelligence in a context for marketing. It's very popular in marketing and advertising because you would like to find out how something may have been performing, a product, or what customers were seeing. One typical example is to look at sentiment analysis and go over reviews, but you can get a lot more creative and elaborate than that. Also, we can go into finance in the more of the stock market world, and we don't even need to stop at stocks. You can start to analyze cryptocurrency feedback. And last but not least, you can look at national security and applications of using OSINT in anti-terrorism and also homegrown radicalization. I don't want you to think that it's limited to something like social media or Twitter. Yes, our example is using Twint for Twitter data, but there are several other sources of open source available data out there. So some of the sources include print media. For instance, very useful and very informative news headlines. Then obviously we have the internet, where we are able to also access news, online publications, blogs, discussion groups. There's something called user-created content. That's, for instance, if a citizen creates their own videos and they post it, whether it's TikTok or YouTube or any other platform, and then Facebook and Twitter or even Instagram. So you have different things that you want to analyze, different types of text data, but not just text data, you actually have images as well too. So you can visually analyze those. But for our course, we are focusing on the text data. So we will be wanting to look at things like the Facebook titles of posts, and the comments. So for instance, the example I gave before with the political analysis, you can look at Facebook comments and try to gauge the political bias prior to an election. It can be quite effective compared to only looking at call-in telephone polling. And then when it comes to Facebook posts, you can have an idea of if there's an increase in certain types of hateful online slander. Other types of data aside from the internet also includes publicly available government data. One example of that can be crime statistics or even consumer price index, and you have commercial data and also financial data. So join me in the next lecture as we get started into understanding a bit more about what Twint does and how to use it. Hi, we finally start the practical part of this section where we scrape Twitter using Twint. So fire up a new Colab notebook and you can rename it Twint. You would have the completed notebook attached at the end of the section. At the end of the section, not the end of this video, at the end of the section, which is in the next few videos, you will have the copy of the notebook, the completed notebook with the finished completed working code. But I do advise that you go over step by step with me so you just understand what it is that we're doing properly. The first thing we do would be to mount our Colab notebook to our Google Drive. So we do from google.colab import drive and then drive.mount G drive. Copy this access code and paste it into our notebook. So this authorization code gives us access to link them. And then let's go to the other cell. Now I want you to do a change directory. And what that means is that we want to navigate to a certain particular directory. So go to your Google Drive and create a new folder and call that folder Twint Udemy. Create, and let's return to our Colab notebook, and we want to change directory into that directory into that folder we just created. So let's do a cd and /content /G drive and my drive where we want to go, and in this case it would be Twint Udemy. What this shows you is that we are now working in this location. And to verify that we did indeed change to this directory, now this was this change directory, so it changed, so we went into this directory. But to verify that we did, you can do what you call a print working directory, which is pwd, print the working directory, run it, and it tells you that yes, this is where we are. So we are in my drive and in this Twint Udemy folder. I will actually show you in two ways where that is. So when we navigate to here, this folder, then you go to G drive, you go to my drive. My drive would not be here, you would not see it before we mounted this drive. But now that we mounted the drive by running this line of code, this folder is now visible. You can check for yourself before that this folder was not here. And then you see inside the My Drive an entire list of folders, and that's the same list that we have on My Drive here, where we have the Udemy, the Twint Udemy folder. This is our folder that we have here as well too. Where is it? Right, Twint Udemy. Okay, good. So now we are where we're supposed to be. Inside this folder is actually empty. I will just show you that it's empty. So let's list all the files located in that Twint folder. Let's list it's empty, there's nothing in there. And to show you that that's true, we created the folder and it's totally empty. After we run a couple of things, the folder will have something in it, and then I will show you what we did. But for now, let us continue by just doing our pip installs and our imports. So the first import we do is something called Nest Async IO. So we do a pip install for Nest Async IO. In the completed notebook later on, you would have a link in that's a resource for Async IO if you would like to read up more about it. But for now, just understand that the reason we are installing this package is quite important. Twint uses Async IO, and Async IO is a library that is needed to write asynchronous applications, things happening at the same time, back and forth together simultaneously. And what Async IO is that it can help when you have a lot of requests that you want to send out and you're there waiting in order to get the response. It's, for instance, if I were to send out a lot of emails in an hour, and then my email inbox is able to receive the replies over the period of the next 3 hours, then that's basically what it helps to do. It helps to manage that request so it can send many requests and then later collect all the answers. Okay, so the reason we are doing the first install to be Nest Async IO. What is the function of Async IO? Without getting too technical and deep into this topic, just understand that Twint, the Twint library, uses something called an event loop. And the event loop is at the very core of any Async IO application. And this event loop, it's not allowed to be nested by Async IO. So Async IO does not allow this event loop to be part of any nested loop. And if you're not sure what a nested loop is, I explained that in the Python for Beginners section. The reason we have a nested loop situation going on is that we have Twint, which is the Twint library using an event loop, and then also you have the Jupyter kernel in which our notebook runs on. So our notebook actually is running on its own event loop as well too. So when our notebook is running on its event loop, we also have Twint library running its other event loop in it. But Async IO is not going to allow that nested loop to happen. So for this reason, we need to pip install Nest Async IO. And the reason, again, that we are using async.io is that if you get more into web scraping and you familiarize yourself with REST APIs or GET and POST requests, then you will be using async.io all the time. You'll use it quite often, where you send requests and you wait to get responses, and you'll understand that more if you get more into the web scraping element of it. But because this is not a web scraping course, I will not elaborate on it. But for now, just understand that we are using this package so that we can deal with the inability of async.io to allow us to do this nested loop of Twint's event loop being run within our notebook's event loop as well. And then, so install that. I have already installed it, but I'm doing it for you for the purpose of this class, so my requirement is already satisfied. But you go ahead and run it, and then after that, the next thing we run would be to actually pip install Twint. And where we are sourcing Twint from is actually from here. This is the GitHub repo for Twint, and Twint again was written in Python and it's open source, so it's all here for us to use freely. I included the link for this in the resources for this lecture, together with, I also included this link actually as well in the resource attached to this lecture. So you can either copy this here from this website, or you can copy it from the resource that I gave you. This is basically Twint. These are all folders here, and they give you bits of explanation here about Twint. And there are other ways that you can install it. If you're familiar with using Git, you can carry on and you can do your Git clone. But for this lecture, we will just be copying this. So copy this, and let's head back to, right, and remember to put the exclamation before you paste it in, to install Twint. Essentially what just happened was that we downloaded a folder, and if you remember when we went to the GitHub area here, you saw that this Twint folder right here, if you click on it, you see there's a bunch of scripts here, and what we needed to do was to be able to basically download this, and that's what we did with this line. But we still have some more configurations to do. But just to assure you, if you go to the working directory that we assigned ourselves to just now, and you open that working directory, you will see a directory. I actually renamed my folder to test output, but in your case, this folder name would just be the same thing from the tutorial, which is, so in our working directory named Twint OSINT, or Twint, whatever you named it, you will see this folder called Twint, which was not there before. So if you click on it, then if you look here, you'll see some very familiar folders. There's automate.py, setup.py, your readme file, Elasticsearch, Twint, and if you go to here, you'll see similar names. It's the same files that we took from before. There's the Twint, Elasticsearch, readme, automate, and the setup files and the requirements text. So that's what we did. We downloaded that into our directory. And if you go to Twint, you have storage, and then, okay, so let's go back to our Colab notebook, and let's just write in a couple of lines of code just to configure the file directory that we will be working in. So let's move directory, let's move the src file /twint dot. So we are going to do 2 quick lines of code, and that will be rm rsrc. So we'll be removing this file. So we're going to this file first, and then we are removing one particular one. In my case, I have already run it before, so I am just going to go to my new cell. We want to do our regular import, but before we do our import twint, like how we would normally do our import packages, I want to do a magics command, which is called load extension. And what we are doing an auto reload. And an auto reload, you are doing that because it automatically reloads modules. So that's essentially what this line is, auto reload, and we are calling that, we are doing the magics command for auto reload. Import sys and sys.path.append, and we are appending to that twint folder twint/, and that's the same folder that I just showed you in our Google Drive. And now we can actually do our import twint. There's another import we'd like to do. Well, apart from importing pandas, then we want to import, remember before we downloaded, we did the pip install for Nest Async IO. We do the import now for Nest Async IO, and then Nest Async IO dot apply, right? So what we're doing here is that we are remembering that we want to make sure that we don't have any compatibility issues between our notebook, and without this, the incompatibility problems with the two loops, with the event loops, will cause us to get something called a runtime error. So if you ever were to practice this on your own and you want to do it first without importing your Nest Async IO, when we run our algorithm, you will see all these continuous errors marked. Actually, you know what? I will show you myself. So I'm not going to actually import this now. I will comment that out. So to do a block comment, you can do command /, and I believe on Windows it would be control /. So that way you can do two lines at once. So we'll come back to uncomment this out. So I'll just show you the error you get without Nest Async IO. And the reason I'm showing you this is because I actually tried to teach a couple of other persons how to use Twint, and they were sort of new, not brand new to Python, but they were a bit beginner level on Python, and one of the problems that drove them crazy actually was this incompatibility error with the runtime errors. And it can drive you crazy when you're not sure what it is you're doing wrong, because everything else should be correct. So join me in the next lecture as we continue directly from where we left off right here, and we start with a new Twint configuration. Topic model, instead of using the news headlines, and run the topic model on the tweets for your city. And if you don't want to do even a topic model, you can do a sentiment analysis. So I hope you enjoyed this entire section where we were able to pull our own Twitter data, and you can get really unlimited with this. You can go up to thousands. Honestly, you don't need to cap it off at 5,000. You can remove the limits, and you can leave it to run as long as you want for whatever period of time for the entire year. So have fun with that, and I see you in the next section. Today we will be looking at neural networks. Artificial neural networks are made up of artificial neurons. But what exactly is an artificial neuron, and what role does it play in machine learning or deep learning, and for that matter, even NLP? The best way to conceptualize neural networks or an artificial neuron is to think about it as being a mathematical function that's modeled after a biological neuron. This is a picture of a human leg with the hamstring muscles the instrument that a doctor would use if you were testing a person's reflexes. And then we have a very basic model here of a human brain and the nerves that goes from the muscle to the brain and then back down to the muscle. So what's happening in this picture is that upon stimulus, when the doctor hits your knee, that sensation or that message sends that from the muscle, would send that pulse through that sensory neuron, and then it would be processed. And if there's some sort of significant weighting, as in if the message seems important enough, because that's what happens here, the brain would be getting thousands and thousands of simultaneous sensory neuron messages, and it has to figure out, should we forward this or not? So if this message is important to be forwarded, meaning that we need to output some sort of reaction, then it outputs that message through these motor neurons. Motor neurons, because they need to send that message to the muscle so that it can mechanically move and kick your knee up, kick your leg up. So basically the neurons have, the biological neurons in our human body, they have three basic functions. The neuron receives some sort of information or a signal, and we would address that in our artificial neural network as an input, which is the information that says something just hit us in this spot. And then the second thing that a neuron does is that it processes these signals. So the second process would be determining, should we forward this information? And then the third thing that happens, that the third function that the neuron is responsible for, is that it has to communicate that signal that was processed to either another neuron, or, well, other neurons, or to muscle. And in this case, the third function that a neuron has to do is to communicate that it processed exactly what this sensory neuron conveyed to it. The last function would be to communicate to the muscle, hey, you need to kick that knee up. And the artificial neurons and the neural networks that we will be discussing throughout this course and throughout any deep learning study that you do is all based, it's a mathematical model based on this concept, which I personally think is extremely interesting and even magical when you come to think about what we're trying to do with machine learning and artificial intelligence. You can view the upcoming lecture as I've provided a really nice animation taken from Sesame Street that gives you a really nice, interesting overview of the biological neuron. So let's have some fun and just look at that really interesting little video coming up. And then after that video, for the rest of the section, we get more into the serious aspects of artificial neural networks. In this video, we will be looking at the Sesame Street animation that demonstrates how the biological nervous system generally works, and basically explains in a more delightful, playful manner what I explain here.
Dr. Nancy Einstein explains the itch, or how Wilbur's brain works.
Let us watch Wilbur's brain in action. Here you see a pesky fly about to land on Wilbur's neck. As the fly's furry little feet land on Wilbur's skin, they cause the ends of special little nerves in Wilbur's skin to say...
So essentially what the bug is doing is that this sensation on the skin is the input, or like we explained previously, the sensory neuron would be receiving one of the first function of the neurons would be to receive the signal from the outside, and the sensory neuron is receiving the information from the outside.
Itch! Itch! Quickly! A message is sent to Wilbur's giant message center in his head. Wilbur's brain. A decision is decided. The itch should be scratched. Like a flash, a message is sent down to Wilbur's arm. Lift! Lift! Like lightning, another message is sent to Wilbur's hand and fingers.
So what's happening here was the second phase when the signal was being processed. And then the third phase is when you need to output some sort of message. If you need to output something, and in this case it's outputting that we need to lift the arm in order to scratch that itch. So that is the three functions of the biological neuron.
On the highway of the nerves, through the spinal cord, through the shoulder, up the arm, through the elbow, all the way to Wilbur's hand. Move them fingers. Scratch, scratch. And he does.
So hope you enjoyed that. And then in the next lecture, we will be moving on to seeing the comparison between the biological and the artificial neuron. First, let's start by looking at the structure of the biological neuron. The main parts that we will be looking at is the three main parts of the biological neuron, consisting of the dendrites, the cell body, the axon, and the synapse. So you can ignore the other parts. The mitochondrion, if you recall from biology, it's considered like a powerhouse, one of the functions of it, but that's not relevant for our lecture today. Let's look at the dendrites. The dendrites are responsible for the input. So consider this the point of where the neuron receives the information and the input signals from whatever outside stimulus or outside source of information. And then we have the cell body. This is the second main part of it, and the cell body is also referred to as the soma, S-O-M-A, and the cell body is responsible for the processing of the input that comes in from the dendrites. And after being fed all that input, inside the cell body or the soma processes to figure out whether or not a neuron should be fired to trigger some sort of output signal. And in order for the synapse to receive that output signal, we have the third part of the neuron, which is the axon. And the axon is responsible for transporting that message from the cell body to the synapse. If the message from the cell body was needed to be transferred to a motor neuron, for instance, when the example we had with the cartoon, when the boy had an itch and he had to raise his arm, or the reflex test when you're hit on your knee, you need to trigger the relevant cells to know, okay, yeah, we need to move that knee, and that the axon is responsible for transporting that message to the synapse. Think of the synapse area as the output, and that output is the connection between the axon and whatever other neuron dendrites are needed to receive that output in order to tell that motor neuron, yeah, you need to move or you need to raise that leg muscle. Our biological neuron can receive multiple signals, thousands of signals at once, and it can have more than one set of dendrites. So when the cell body has to determine whether or not a neuron needs to fire an impulse, yes or no, should we have a trigger or not, that ability to fire depends on a total sum of the inputs. And biologically, we have inhibitory signals and excitatory signals. An example of a biological excitatory signal, which is a type of input, is epinephrine or dopamine. So if our body gets a trigger, it gets an input to trigger some sort of fight or flight reaction, that output would stimulate that neurotransmitter epinephrine. And when we produce epinephrine, it increases our heart rate. The synapse reaction causes our heart rate to increase. We can gain muscle strength. It can even increase our blood pressure. And the reason this happens is that it's preparing our body to respond and to deal with some sort of strenuous activity. And another excitatory input is, like I mentioned, dopamine. So whatever triggers our dopamine, that gives us a sense of reward and we are more likely to repeat that activity. That's actually one of the reasons a person can be addicted to something as simple as food. Certain types of food, like if it's high in fats and sugar or salt, a certain combination, like fries and burgers, it's why you can be more addicted to eating that as opposed to broccoli, because it triggers something in your brain, that dopamine, like, oh my god, I love this, and we want to repeat that behavior. I also mentioned inhibitory inputs, and an example of that is serotonin. So the inhibitory reaction, if we are prompted to produce serotonin, it generally, one of the examples is that it can reduce anxiety. So if it senses that, if our body gets a reaction that, okay, yeah, we're getting too anxious for something, our brain has a response to help us deal with that anxiety, and serotonin actually can help us sleep as well too. Now, if we were to look at this diagram here, we see this is just a sketch of the same thing over here. So here we have the dendrites, which is the input, and then we have our cell body, which is the processing unit, to figure out if something's going to happen or not, if we need to raise an alarm or have some sort of inhibition effect. And then the axon sends that message to the relevant neurotransmitter. And this is the artificial neural network. This is our artificial neuron. And you are seeing a similarity with the structure over here. For our artificial neuron, we have our inputs, and these inputs are transferred to our processing area, and then it's outputted. And you can actually see from this basic model that the artificial neuron is a mathematical model to the biological one, because in the processing unit here, we have some mathematical calculations that go on that I would explain later on. But for now, I just want you to see the similarity. So now that we have an idea of the similarity, in the next lecture, we elaborate on the same artificial neuron and even see how this can relate to a natural language processing or text-based example. Continuing on the topic artificial neuron, the artificial neuron is also referred to as perceptron. This is the standard diagram of an artificial neuron, and it shows the basic functions of the perceptron. And similarly to the dendrites, the perceptron has its inputs. You can have as many inputs as possible, and then it feeds in the input. Well, think of it as an input layer. This information layer, what we call the input layer, it passes the inputs through to the neuron in the way that the dendrites would. And you would notice that we have these W's, and these are all weights associated with each input. And then we have the activation function. Think of it like the soma, the cell body, where the processing of the input happens. What it does is that it takes the sum of the input multiplied by the weight and passes that through an activation function. So like I said, it's a mathematical model to our biological neuron. And depending on what happens in here, depending on the activation function, it gives a binary output, whether yes or no, whether or not a neuron would be outputted. So the four essential parts of the perceptron is the input layer, the weights and the bias, the activation function, and then the output layer. In the next lecture, I explain the weight and bias in more detail, so don't worry about that right now. And also in later parts of the course, I would also revisit the topic of weight and bias when we get into more examples of deep learning. But for now, I would like you to just understand the perceptron, the layout, the main four parts of it. And now I would like to give an example of how on earth this ties into NLP, or the analysis of text data. One example would be determining the sentiment for movie reviews. The sentiment meaning if it's good or bad. So the input would have our movie reviews. So after watching a movie, we can have hundreds and thousands of movie reviews for a particular movie. It would be too much for a human to go through and do overall score of the movie. So we have the input, which will be all our reviews, our movie reviews, and then each one will have its weight and bias associated with it. Don't get confused with the weights again, I will explain that shortly. Then when the inputs and the weights is passed through the activation function, it tries to figure out, okay, does these words of that review, if the review says I love this movie, it has to figure out and calculate how positive that statement is, I love this movie, and the keyword here me being love. Later on, when we do word embeddings and cosine similarities, you would understand how the algorithm has an idea of the context or the meaning of that word. Then it figures out if it's a good or bad review, so it outputs that sentiment. So we get the sentiment analysis for all our movie reviews, and it will tell us if it's good or bad. That's if we do a polarity type of sentiment analysis. That's based on good or bad, but we can also do a more granular sentiment analysis, and it can output the emotions. If generally people were angry or like extremely upset about the movie or generally really like it, so it's very positive. So that's essentially classification, and we do text classification later on in the course. One of those examples would be the text classification section, where you're introduced to classifying reviews for the first time on Steam reviews, so you can look out for that later on. So join me in the next lecture where we learn a bit more about the weight and bias within our perception. Welcome, and I'm particularly happy to invite you to this lecture because you will be doing a wonderful practical example where you would learn text classification, and we'll be doing that sentiment analysis on Steam video game reviews. We will be using Spacie, and it's a really nice, fun, practical example, and it will be rewarding because you have been working through the theory diligently, and I would like to reward you with more of a practical, and this way you'll be more confident with your Python and your data science understanding. So before we get into the practical, let's just do a quick overview. Our practical for learning text classification includes some hands-on experience with supervised learning. Supervised learning is when you have to first train your model with already existing labeled data. So just think about it. If you have to train yourself to learn to distinguish between a crab and a fish, right? You would learn it with a lot of examples where you know what a crab is, what a crab looks like, how it has this many legs, it has this hard shell, and you learn all these things about the crab. And then you learn about the fish. It's softer, he has gills, he has a tail, he doesn't have all these legs. So you learn over and over as much things as possible about the crab and the fish. But what if you learned too little about the crab and the fish? Like a child would not be sure. So you want to be more certain, which would be a more accurate inference. So I can accurately say, yes, that is a crab because I learned properly what a crab is. That is basically what supervised learning is based on, which is why we need a labeled set of data to teach the computer what, in this case, what is a good review on a game as opposed to a horrible review where you would not recommend that game. Then we look into feature extraction using a bag of words, and the extracted features from the Steam game reviews will be used for training our model. So essentially what our bag of words will be doing, we will be using that form of architecture. Forgive my spelling here, that's just supposed to be feature. And our bag of words would be creating a vocabulary of its own unique set of words within the training set. So what is this training set and testing set that you will hear me speaking of all the time? let's think of our entire data set of our Steam reviews as one big bunch of data, and we are going to partition that data set into a train and test split apart, right? So now, what train test split what we will be doing in our algorithm in our practical coming up shortly would be, you will see the code for all of this, so I'm just trying to get you to understand it without the Python being involved. So we will have a line of code later on where we do something called a split 0.8. When I type that, and you type that with me later in the code along, what that means is that, before I explain this, let me show you our dataset that we will be working with in the practical. So this dataset that has 17,000 entries, we're only seeing 25 here, but in total it's 17,000. And let this file cabinet represent that 17,000. So we're going to take 80% of this and put that as our training data. And then 20% of that 17,000 would be over here, now testing data. And if this entire thing, which was our data set, has all the answers and all the info needed for our biology test, then your teacher would give you all of this work to learn over and over. So what if you had to learn, not biology, but what is a recommendation compared to, so for your biology test, you are given all these descriptions of what is a crustacean, what is a whale, what is a mammal, and it's a lot of information that you're reading over and over, and your teacher is teaching it to you the same way our model will be learning over and over. And the test data now is, the reason we have this test data is that, imagine you have some answers to a test, but you don't have something to correct it with. Then you wouldn't know how to assess that model. You wouldn't know if it is correct or not, right? So what we need is that you're given a question, whether or not something is a crustacean or not. You're given a description. When you guess that it was crustacean, and then over here you guess that it's a whale, we will be able to look back at our tagged data set to know that, oh yeah, it's correct, it wasn't a crustacean. And yeah, it was correct, it was a whale. But if in this one, the correct answer was supposed to be crustacean, but I said whale, it would show me that we don't have 100% accuracy, meaning that the model did not learn it well enough. So like, you did not learn it well enough. So essentially that's what train and test data is. So I hope you understand this basic concept. And if you get a little bit confused, if you got a little confused there, don't worry, because we will be doing train test split a lot during machine learning, and you will become so comfortable with this concept, both theoretically and in Python. So just rest assured, this is just for your familiarity. And then when we get into the practical, you're going to have some fun. So follow me up in the next video and open up your classification _ steamreviews.ipynb Google Colab notebook, and let's head into the practical. Following up directly from our last video on text classification introduction, we are jumping straight into our classification _ steamreviews.ipynb Google Colab notebook. So go ahead and open that up, and we'll be doing our text classification with Spatie. Okay, note that it's with Spatie and not NLTK for this example. We will be making a classifier that can detect a positive or negative Steam review. So essentially this would be telling us if the review recommended the game or if it did not recommend the game. So essentially it's a binary classification, only using two, as in a yes or a no. So some uses of this would be to calculate the most recommended games by our users. This can stem all over from Steam video games to Amazon to even buying cannabis. It's very useful. So let's go ahead and get started and just reconnect. So this is an image from Steam website. If you're not familiar with it, you can just go check it out. And let's start by doing our typical import for our libraries. So let's import libraries. And the first one we will be importing would be import pandas as PD. So we'll just put a note that this will be needed like when we're doing our data processing, or even when we want to read in our output files. For instance, when we call a pd.read_csv, we're using pandas for that. And if we don't run the import here, you'll end up getting some errors. So then we want to import spacey and import matplotlib.pyplot as plt. This would be for some of our data analysis, for our exploration. I just want to show you some visuals. And import seaborn as SNS. And just for some styling aspects, sns.set style equal to dark grid. Close that off. Okay, it's all good. sns.set. Some more visual aspects. Font scale would be 1.3. That should be fine. Okay, and then we go to the area where we load our data set. To load our data set, let's import it. So from Google Colab, import files. The file that we want to get, so we upload from our local drive, upload files.upload. We will get a prompt to run that. So choose files and go to your folder with your datasets where you downloaded your Steam Reviews dataset. Here we go, steamreviews.zip. It will take a couple of minutes just to load it up. Okay, now it's 100%. We just want to unzip that. So it's very simple. Unzip the name of the file, Steam Reviews. I have already done it before, but if it's your first time, you wouldn't have to do this, but I'm replacing it with the file from before. Yes. Okay, and we have our train.csv file. So now let's read that file into and save that to our data frame, which would be pd.read_csv into the name of our files, which is train.csv. And like I said, you can name this anything you want, and it's just the variable df, which is our pandas data frame. And let's take a look at how our dataset actually looks. So df.head, just give us the first 5, and actually let's take a look at a bit more. Let's look at the first 15. And here we have our column names, our features, the review ID, which is the individual ID for each review, the title of each game on Steam, its corresponding year, the review from the user named user review, and then the user suggestion, which is binary. It's a negative or positive. So 1 being, yes, I am a user who bought this game and I liked it. I gave a good positive review, and the data set has labeled it as positive. Similarly, this negative review was labeled as 0, so it's negative. So we have a large amount, so let's actually see let's explore the dataset a bit more. Now the columns that we're interested in would mainly only be the user review and the user suggestion. So let's just make things simple and choose to display what we're only interested in. So our data frame is now equal to df square brackets and then another set. Put the name of the columns that we're interested in, which is user review, and the second one is user suggestion. Okay, and let's actually do one step further and to drop the null columns. So because we're interested in these two columns in particular, we wouldn't want any of the rows where either one of these fields is empty. So let's drop any where these columns have no information. So let's do a drop na brackets, and just to display that, df.head. Okay, so we only have the two columns that we want, and we wouldn't see it here, but wherever they would have had no columns, empty data in the columns, it would have been dropped. Now to do some more exploration on our data set, how big is this data set? So let's see how many rows there are, how many reviews. To see how many reviews we have, let's do a df.count 17,494 reviews, as well as 17,494 user suggestions, so they all match and nobody has any empty fields. So it's fairly, in data sets we can get really huge, so in relativity this can be considered small, but we do have quite a lot of reviews to work with. Now, out of this 17,494 reviews in total, how many are positive and how many are negative reviews? So let's see how many games out of all of these were actually recommended and actually positive reviews. So how are we going to do that? Let's do a df1 is equal to df.user dot value counts, and run that function on our data frame. Great, we have 9968 positive reviews, so whichever games in total, we have a total of games of over 9,000 that were positively reviewed, and then we have 7,500 negative reviews. If you want to, part of our data exploration, it's nice to have a visualization of it. So let's do a visualization so that way we can actually have a nice visual on how this is distributed. If there's a balance, from the numbers we can tell, but a visual is always best. So let's use Seaborn, and that starts off with SNS dot factor plot brackets x is equal, which is our x-axis, and you choose the info that you want on the x-axis, and in this case we want the user suggestions to be on the x-axis, so that would be user suggestion, and we want to describe our visualization a bit more. So the data that we're using is from our data frame named df, okay? And what is it that we want to do with this user suggestion, with this information? We want the kind of visualization is based on a count, because we want to count all of these values. And our size, let's choose 6, and you can play with these values after to see how they change, but for now this is fine. And the palette, which is my favorite part, Just how we change the colors. The palette is equal to, there's a range of colors we can use, and I'll show you how we get the key to know what to put in this field. So it's just .rainbow underscore R. Actually, let's just put just underscore rainbow. The reason I'm telling you that I'll show you an index with this after is because when I now started doing data science, even though I was familiar with Python, certain things like this, I would wonder. The reason I'm showing you maybe where the index would come from, like where I got this word from, is because when I started data science and I was new to the field, I was versed in other languages, more C++ and whatnot, and I was a beginner with Python and I wasn't that used to it. So when I encountered things like this, I would get so confused and be like, okay, so how did this person know to put that? I mean, it's not normal. Normally I would think palette, okay, I may want red, but if I were to put red, I will get an error. So how did this person come up with just rainbow? So a lot of these things are not memorized in my head. I will show you how I got this, okay? So if you want to show this plot, plt.show the plot, and close that off. Oh, I'm sorry, we have one tiny mistake. Just put an equal sign there. I'm sorry. Okay, good, and let's run that. Oh, very well then. We have a much nicer visualization now compared to just these boring figures, and what it shows us is our distribution balance of data. If you ever encounter a distribution balance where it's very off, for instance, if our negative reviews, which is in green, was only all the way down here, and our positive reviews were all the way up here, meaning it's almost 10,000 positive reviews, and if we only had 1,000 negative reviews, that would have been too much of an off balance to consider. So some alterations would be needed, but in this case it's fine. We have roughly the 7526 in the negative values and 9968 in positive values. So that's our nice visualization, and let's jump into our actual text categorization. Okay, good. Now that we have analyzed our data a bit, as in we checked it out, we explored it, we have an idea how it looks, how much data there is, the distribution of it. Join me in the next video following directly from here, so don't close off your notebook. We're going to start off directly from right here. So join me in the next video where we start actually using spaCy and we create our text categorizer. Moving along from our visualization of our dataset, let's jump straight into using spaCy to create our text classifier. So scroll down on your classification_Steam reviews notebook to the header. Start using with spaCy to create our classifier, and when you find that, right below anywhere there, just create a new cell, and we've already imported spaCy. So let's go and now load up our spaCy.load, and we're using the small English. Yes, we'll use the small set for now. Okay, and we're creating nlp.pipe_names. Now what we're doing here is that we will be using this spaCy text categorizer class. Before I get to that, the text categorizer is a spaCy pipe, and as you recall, pipes are classes for processing and transforming tokens, like we understand from before with tokenization. So the text categorizer that we'll be using would be a subclass of a pipe. Now, what I'm going to show you here, now let's run this and you'll see what I mean. So the output below here shows the pipeline has a tagger, a parser, NER, but it does not have a classifier. Okay, so because it does not have a classifier in this built-in pipeline, we will now create the TextCat pipeline, and it will be built using a component of spaCy for text classification. So this will be added to this pipeline, and we will use the add pipe function for this. So now when we go to build that, you'll see what all this means. It will come together. So just scroll down to, you see where you have bow right here, create a cell right below there, and here we are going to create the classifier. And like I mentioned before, we are adding the built-in TextCat component to the pipeline. Okay, so TextCat, our object, is equal to nlp.create underscore pipe in brackets TextCat, and config some configurations, exclusive underscore classes will be set to true, comma, let's choose our architecture, and our architecture can range between bag of words, or we can even get more into it, but to do some more accurate architecture, but let's go with bag of words, and right, close that off. Now to create the text classifier, you see here we're using two solid names there, exclusive classes and architecture. So we're adding this to our model here, right, our NLP model. And exclusive classes are used when you are dealing with Boolean cases, and we are dealing with Boolean because in our case a review is either negative or positive, so it's quite practical for our use today. And when it comes to architecture, before I get to that, now the default for exclusive classes are usually set to usually set to false, so we're setting it to true. And what happens here is that you're making the categories mutually exclusive purely based on Boolean yes or no, true or false. Okay, and the architecture, it's simple. It is a type of Unicode, and the default is ensemble. So it's ensemble, but that is, I'm not going to get into that now because it requires some knowledge on neural networks. And a second option for architecture is actually a simple CNN based on neural networks. And later on in the course, when we get more advanced and we do some deep learning and we do neural networks, we'll do a lot of examples with those, and one really nice long example in particular. So for now, because we're familiar with bag of words, we will choose that architecture. It's faster than Ensemble and using neural networks, so it's faster and simpler to use, and it's quite sufficient for this project, but the other methods are better, but we'll use bag of words for now. Continuing with our nlp.addPipe, and the pipe we'll be using what we're adding is TextCat, and we're setting that to true. And just to see the nlp.pipe names, now what we're doing here is adding the pipe to this pipeline. Okay, so we are expecting to see TextCat, which is our text categorizer pipe. Oh, I'm sorry, let's put a correction, an equal sign after your config. Okay, excellent. We have now added our new feature to our pipe. Well, not feature, my bad, but we're adding our TextCat to our pipeline. Okay, so you can take a break for now, and join me in the upcoming video where we finish off this exercise and we train our model. So have a quick break and join me in the next video. Continuing in this next section, what we're adding is our labels to our text classifier. It's very simple. What we're doing is that where there's a 1 in our data set, recommend would be for a game that has a score of 1, and don't buy, we want to label that to the reviews that got a negative review. So it's either a game is being recommended in a review or the review is saying, no, we're not recommending this, don't buy. So you can label this anything you want. You can put something simple. You can put yes and no. Positive and negative. The labels don't matter. What matters is the syntax. So continuing to just add in the labels to text cat. Adding labels to text cat. Why is that in caps? I didn't mean to. So text cat dot add labels. It's so close to English. It's really nice. And we're putting recommended. Okay, you can put yes. It's okay. That's fine. But if you're following along with me in the code along, put recommended, because I don't want you to have any errors later on with syntax, because we'll have to call on this, and if it doesn't match, you'll get an error. So the second label will be textcat dot add label, and let's call this one don't buy. Good. Simply run that. We get an output of 1 because it's a Boolean situation where it's either positive or negative, in this case binary, 0 or 1. And good. Now that we've created the labels and we've made the addition with the proper text cat added to our pipeline, now it's time that means that our default model with textcat is ready, but we have something else to do where we need to actually prepare the data in a format needed for our training. So we're going to write a function called load data, and that would take a list of tuples as input, because you want to be able to actually put the information row by row. That's what we're going to be doing next. So each tuple would contain text and label value. What that means is that, in simple terms, each tuple is a row, okay? And each tuple that we're concerned with, which would be the reviews and the suggestions, each one would hold text and label. So those are standard names for it. So our user review falls under our category text, and our user suggestion would be under label. Okay, so that's what we're referring to here. So that's what I mean here when I say that each tuple contains the text and the label value 0 or 1, and the code below would demonstrate how to convert our reviews data set into this desired format. Okay, let's just continue now with that. So what we're doing in this block would be converting the data frame into a list of tuples, and don't worry if you can't visualize it, the output will make you understand what this block is about. So our data frame, tuples, right? So we're putting our data frame into a form of tuples equal to df.apply. We're applying lambda, okay, because generally we use lambda applied to rows, not really columns. So we're using it when you are performing a functionality, in this case our load data function. So we are applying lambda to be able to access more than one column at a time, because we are interested in these more than one column. So that's why we're using lambda here. And continue, so we're using lambda for our rows, and we have row with our respected columns that we're interested in, which would be user review, and secondly our other row would be user suggestion. Okay, and the axes that would be on would be 1. Okay, and now it comes to train. What we're using to train would be df tuple, so that would be training it based on the information held in the tuples, and that would be dot to list. Okay, and train, let me show you a group of 10 of this square brackets, okay, not curly, sorry, straight square brackets, 10, just delete this here. Okay, so I'm showing you here the training data that we will be using that was put into a nice list of rows in the format that we can use for training. Okay, so now you can understand what we wanted. We have our data frame converted to a list. So we have the text. It's quite a bit long if we scroll here, but basically this is the entire text for our user review. That's the format, so it's row user review, and then continued we have it row user suggestion. So it will be 1, 1, 1. This one was 0. So let's take a look at it. Somewhere between light-hearted, happy parody, and afraid of the dark. So you are tasked with the daunting survey, so and so and so. So let's take an example here. This got a score of 1, so it was a recommended statement. Great game. It's a cute little horror game that progressively gets darker and scarier. It has a nice sense of humor too. I've played it a little and I've watched several people play and I love it! Exclamation mark. Another one here, great and well-made game, 10 out of 10, enjoyable with playing. So these were given positive reviews. As you can see, they are positive reviews. So this is the form that we will be using to train our data on. And now we're going to create the load data function. Okay, so we needed to do this before we do our load data function. So it's in a good format now. We've lined up our tuples the way we need to, and now let's load the data accordingly to these said tuples. So exactly what we just did here. We're going to build on this and load data onto a structure like this, okay? So under this section, the load data function, what we're doing next is that we are passing the training data as input to our load data function. So bear with me as we type out our bit of, so let's import our library, which will be random. You'll see why we'll be using random later on, right a few lines after. So df load data, this is our load data function, and let's set a limit to 0.8. And does that sound familiar to you? It should, because in our intro video to this this lecture, I explained to you what the split of 0.8 meant because of our test split data. So we're splitting our data set of reviews into 0.8, which is 80% of it. So we are going to train our model using 80% of the data from our reviews data set. So let's give our training instructions. So train data, we'll be using train. And if you recall, train was created here with a format that we altered to list our tuples. So we're using this set of data in this format, this list, as our training data. Okay, so that's what our training data will be using. Train, and we want to shuffle the data. So that's why we imported random just now. So it's random.shuffle. Train our training data. Okay, and as you would recall, I explained a moment ago the text and label, the standard names representing the column for the user reviews and the column for the user recommendations. So the text and the label would be zipped together, our train data. Okay, and let me just put a note for you here that get categories for each review is what we're doing. So in case you review this and need to practice and can't remember, let's call this object cats in square brackets and curly. Do you remember the label that we use? We put recommended, and like I told you before, it's a boolean. We're using boolean, so in this case recommend was positive, so we set that to bool yes. Okay, and continuing with our other label, which was don't buy, we're setting that obviously to the opposite, so that will be not bool, and that is also y. And okay, I think that's it. No, I'm sorry. After the curly brackets, you put for y in labels, and good. Now, one more quick note. What we want to do now with our splits, we're splitting the training and evaluation data, right? Remember I explained this in the lecture before. If you can't remember properly the difference with the training data, you can't visualize it in your mind, you can just go back to that video, or if not, we will do more examples with train test splits later on in more examples and more projects, so just go along with me for now. And evaluation data. So our split, this is how we're doing it. It's integer length of our train data, and this would be our split of the 0.8 that we mentioned earlier, and we are returning the texts that were in our column user review, text split, our object cats split, and also our text split and cats split. So you notice it sort of takes a format of how you would look at usually an XY output for X-train, Y-train, and X-test and Y-test. It's similar to that format, so you can visualize it in that manner. Following along, we put the number of training samples. Let's set that to, our total was about 17,000 and something, so the 80% of it, we'll set it with, we needed for setting a limit soon after this, so let's put 13,995. If you're not sure how I got that number, it's 80% of our total data, so this is the training size, the sample size. And then we want to call the load data function, okay? Because if we don't do this and we just run it, nothing will be loaded, and nothing will happen for feeding into our model. So it's not enough just to write the function, we have to call the function. So let's train, for our train texts and train cats from right before on top of this, you want to, oh actually sorry, we need to add on our dev text and dev cats. It's a format for when we call our function, how we load it on. So it's load data, and we're setting our limit to the number of samples for, sorry, that's n text. That's the number of samples for training data. That's our limit. And one last line, we will be processing the final format of the training data. So to process that would be the train data equal to list zip train text square brackets curly, and remember cats that we defined earlier, right? It'll be cats, our text categorizer for cats, train cats, and then we train data. Let's do the same thing that we did before, just to give you an overview for about 10 tuples. You can always pause the video and go over line by line just to make sure that you've got everything correct. Run that and you'll understand the syntax a lot more, the logic behind what we were doing here. So as you recall over here, when we converted the data frame into our list, okay, so think of our data frame in this format, and we have our columns and our rows, and we wanted to change this format into this format. Oh, I'm sorry, I scrolled too much, right, into this format. So it's no longer columns and rows. We have our list of tuples with our text and then our recommendation or yes or no. And now further, we want to go and load some data. We want to load our data function in this format, which is exactly what we've done here. And it's random. So let me just show you. If you look here at the reviews, we have great game, fantastic graphics and game engine. Second one is I love this game. I've already spent countless hours, and obviously this is a good positive, and this is also a positive review. So they're both true for recommend, which means that we're training it to know that this text, this review, is a recommended positive review. Okay, and now here we have an example of my internet isn't very good. I enter the server, so and so and so. I've been kicked from the server. Your internet is too stable. This person didn't have a good experience playing the game, or maybe even a good experience with Steam. So they did not recommend it. So it's a false recommendation. You got a true Boolean output for don't buy, meaning it was a negative review. And another example here, actually before we do that, let's just run it again. And because of the random state that we introduced, we have another random set here that so we're choosing our training data randomly, so it's not like the first 80% always, it's random. Another example I'd like to show you, okay, trying to log into Facebook, but it does not work. I'm trying, this person wasn't even able to log in properly, and obviously they recommend don't buy. Now that we've had our training data organized, now we get into training the model. Just scroll to the part where I have mini batch function, because in order to train our model, we will be using Spacy's util.mini batch function. And how this works essentially is that it iterates over a batch of items. Actually, before I explain, let's just get into typing it up and I will explain as we go. So from Spacy.util, like I just mentioned, Spacy.util import mini batch and compounding. Let's put some notes here. The number of training iterations we will be using would be n, and these are integers, and okay, so that's what this is. It's the number of iterations, and let's set that to 10, because like I said, the mini batch function iterates over a batch of items, so we're setting that to 10. We'll see how it works. And now this is important, we are disabling other components. What components are these? I'm going to type it out and then I'll explain it for you. Let's call this object other pipes. It's equal to square brackets pipe for pipe in NLP dot pipe names. As you recall, NLP.pipe names resulted in an output for these 4 different, we have tagger, parser, NER, and textcat, because we added on our text categorizer to the pipeline. But what we're doing here is that we are disabling these other pipes. We are disabling the tagger, the parser, and the NER, the entity recognition element. I will show you why we're doing this, because what was the point, of having it, and we're just going to remove it now. It's actually quite important. NLP.pipe names, if pipe textcat, our text category, our text cat that we created before, if pipe is equal to close that, and with our NLP.disable pipes, to disable the pipes, we're talking about our object other pipes, and what we're doing here, let me put a note for you, we're only training textcat, and let's just indent optimizer NLP.begin training. If we don't have this and we were to train our model and everything, but we don't actually begin it, the result may give us a 50-50. So instead of getting a true and a false, where we have a number to differentiate true, so true may be 0.9 and here will be 0.1, it will be 0.5 and 0.5, it will be 50-50 if we actually don't begin it, because we'll be testing without our trained model. So that's what this line means. An output, just so we know what's going on, let's just print anything here. You can put training the model, it can take some time, like 10 minutes. So wait until it is finished. I find that sounds a bit harsh. Let's put, please wait until it is finished training for moving on to test. Okay, so you can put anything else you want there. And okay, so let's actually perform the training. A for loop, because this is when we start our iterations. So naming our iterations here is simply not enough. We actually have to create our loop. So this is our loop for I in our range of n iter. So within our range of 10, so we'll keep looping for that number, whatever value we chose there. So for these conditions, our losses, let's set losses. What this is that losses it's a type of dictionary, and it is taking an optional record of the loss that occurs during training. Okay, and the batches that we were speaking of, because remember it iterates over batches of items, so our batches uses mini batch is train on our train data. The size of be equal to compounding. What size means here is that size is an iterator allowing the batch size to vary on each step of our loop. So think of you are learning what a review, you're learning what is a recommended review, what is a positive review, and you're trying to learn and differentiate between a positive and negative review. So what you are doing in this loop here with the size, where you're iterating and allowing any batch size over each step, you are learning over and over, and you're taking notes each time. So think of yourself as the model learning on this training data. So our compounding size, it's like I said, it's varying for each batch. So let's put numbers of 4, 32, and 1.001, 2 brackets, make sure it's 2, and for batch in batches, the text, like I mentioned before, with text and label, text and annotations equal to zip our batch, and do an NLP dot update, and for our text and annotations set the parameter SGD would be equal to our optimizer that we outlined before, and drop would be 0.2. Our losses would be equal to losses. Okay, let's just review. Yes, that looks good. Oh, I'm sorry, we have one mistake, an equal sign there. Okay, now everything's good. Now we run. Okay, so it outputs here whatever we had put printed here. So it's training the model right now. This can take a while. So give it about 10 minutes or so, go get a snack, take a break, and return to your machine, and you'll have your model all well and trained. We continue to work in our same Google Colab notebook for our classification of our STEAM reviews. We are almost finished with this project, and you have just trained your model, and as you notice, this has stopped spinning, so it has finished train. So let's do a bit of testing and see the type of result that we will get. Keep in mind that our testing here is not being done on the test data. Remember, we did a split 0.8 and 0.2 where we trained on 0.8 of it and we left 0.2 to test. Okay, this is not that 0.2% of the data. That 0.2 will be used in our evaluation, and that evaluation will be done in an optional video after this video. So for now, what we're entering here, this text, it is actually unseen data. So it's not the testing, it's not from our initial data set, it's what we refer to as unseen data. Okay, so let us test the model by, I have already provided you with some sample sentences. You may recall that we used NLP.pipe names earlier, and then we disabled all except our new TextCat pipe that we created. So I'm going to show you this. I'm telling you this for a reason. So let's run this cell. What we're doing is that we're taking this object, which is our text. You can put any text in here. Our doc is equal to our NLP that we created before with our pipeline, our TextCat pipeline, and it would run our TextCat on our text. So that's essentially what we're doing. Okay, so let's look at the text. The game was boring and we did not have any fun at all. I was very much so disappointed. And we have a very large score for don't buy. So that shows you that this is a negative comment. So this review is not recommending that particular game. And you notice for recommended, which would have been the positive Boolean, we have a very small number that's close to 0. So in this case, it was a very distinct negative comment. So it wasn't iffy. So let's try one more. The game was long and it was not too bad, but I had much better expectations, and it's sad to say I was very much so disappointed. There's a bit of repetition here, so let's change that to I would not buy this game if I were you. Again, it's a heavy weighting for don't buy. We're getting quite a good performance for our bag of words architecture. And it's not recommended, so it's very negative. It is a very negative comment. And I want to show you something here. This comment, it's best exciting flight simulator ever. But let's change this ever to common letters without the exclamation mark. Okay, let's see what we get. Now it is positive. It is a positive statement that is recommending that, yeah, it was a really good flight simulator game. And the recommendation, the positive review of 0.89 is a significant difference as opposed to the 0.1. So let's change this to caps with 5 exclamation marks and run it. You see that difference? It was 0.89 and now it's 0.98. So it's even more of a clear distinction that this is positive. And you notice that was a change because of the punctuation and the capitalization. The reason I told you before that we were disabling the other pipes, which was the parser, the tokenizer, and the NER, those pipes were disabled because if we had them included, then it would not have considered these differences which we need for that extra emphasis on our words. So we were only wanting the words that people actually, how the exact way that they typed it. So let's try one more time. So let's try a few more just to experiment with. Whoa, it was awesome. I was not disappointed at all. We used this a few times. Let me show you something else. It was awesome. I showed all my friends. I did not regret spending money on this game. Now, this is a bit iffy because you have words like it was awesome, wow, exclamation marks, but at the same time, you have the words not and regret. So I'm wondering, would we get a negative or positive review? Would it be like close to 50-50? Oh, actually, it was correct. That's very good because there's a chance that depending on how you do your model, quite often in NLP when we're using the more basic models, you don't have the best accuracy, and something like this may have been even interpreted incorrectly and be considered a negative comment only because it made a mistake with the words not regret spending money, and it was correct because it is a positive statement, and so be it. We got a very good accuracy. Let's try one more. It is not a good game. We thought we would have had more fun, but it was too long and we never finished till the end. But there we go. So even though this one would end up weighing as a negative outcome, it is not as negative as this one here, because this one they said I had much better expectations. It's sad to say, so maybe it's because of the word sad and whatnot. I would not buy this game. It's very distinct, so it was clearly a highly rated negative comment. And in this case, it is negative, but you notice it's not a big difference to the recommended one. So it's slightly negative, but it's not a case of black and white negative. So it's not a good game. We thought it would have been more fun. And let me just change it up a bit so we see the change. And you can experiment with the testing as much as you want and see the different output that you get. Now let's make it a little tricky. I admit it was more fun than the first part released last year. Okay, and let's see the outcome that we get here. Okay, so in this case, you notice that this overall is not really a recommendation. It's more of a negative statement. But in the end, we end up getting a positive result. So in this case, this could be considered a false positive. Before I continue, in some of the previous videos when we were dealing with this project, I mentioned to you a color scheme when we were doing our distribution balance, and we used Seaborn. So I just wanted to show you how I got this just rainbow value, and it's not something I know offhand for you beginners. So I put an error here on purpose. So I removed the W, and you're going to get an error. And when you have an error with your palette, you will get an entire list of all the different variables that you can choose, all the different descriptions. So each one of these is a different palette. So we just had just rainbow. Let's try just earth. And it's some earthy colors. We'll go back to rainbow and let's give it another error so we can try something. So you can adjust yours to suit, and remember just to make this become an error, spell it incorrectly, and choose any one of these from here. We had rainbow at first, and if you do just underscore rainbow underscore R, you get it reversed. So it was blue and green, and just put it back to original, we get the green and blue. So you can go around and play with your palette. If you are anything like me, I spend really long making my visualizations pretty. We will be doing more visualizations throughout the course that are more complicated and more informative. That's it for this chapter on classification with Spacey for our sentiment analysis on Steam video game reviews. So if you're not joining me for the evaluation, we can jump on to our next chapter.